Welcome to the course. I'm Daniel and I'm so excited to teach you how to write big data applications with Spark and Scala in this course. This video will serve as a short introduction to how this course is structured, how to approach it, and how to set up the initial files. So first, check out your welcome message. It contains important information about the course. I might also personally reach out to you to check your progress or address any questions or concerns. Speaking of questions, if you have any, post them in the Q&A forum or attach them to the video lectures. I'm pretty responsive and I never leave a question unanswered. For anything else, shoot an email to daniel@rockthejvm.com if you want me to organize some corporate training for your company or your team, or if you want me to build a course or anything else really, just shoot an email. Alright, so that was the administrative bit. Let's talk about the technical things that you will have to install on your computer for this course to run smoothly. First, we will need a good IDE installed on our computer, and for that I will recommend IntelliJ IDEA with the Scala plugin. And the Rock the JVM fans will probably have one already installed from the other courses. If you don't have one already installed, go to jetbrains.com. And here, click on IntelliJ IDEA. Click on download and go ahead and install the community edition for Java and Scala. The setup should be straightforward and shouldn't take more than a few minutes. Also, at the first launch, the setup will ask you if you want to install the Scala plugin to IntelliJ, which of course I recommend you do for this course. So if you don't have IntelliJ IDEA installed already, go ahead and pause the video and install it now. After you've installed IntelliJ IDEA with the Scala plugin, I will ask you to install Docker on your computer because the project that we will use in this course contains some Docker containers that we will interact with from our Spark applications. So go ahead and go to docker.com. And if you have a Mac or a Windows machine, go to Products and install Docker Desktop over here. So click on this blue button and download Desktop for Mac and Windows. The setup should, again, be really straightforward. After the setup is done, you should see this tiny little cute icon here in your system tray, either on the upper right-hand side on a Mac or in the bottom right-hand side or wherever you have your taskbar on Windows. Now, if you're on a Linux OS, go to Resources and then click on Docs, or go to docs.docker.com. Click on this Get Docker button, and then here on the left-hand side, click on the Linux and expand this range of operating systems for which Docker is supported. Pick yours and follow the instructions here. The documentation is generally pretty good. If you don't have Docker already installed on your computer, pause the video and take a couple minutes to install it now. Now, a word for Windows users. Docker will not work unless you have a feature known as Hyper-V on your Windows operating system, which is available in the professional version of Windows 7 or later. So make sure you have the right version of Windows installed on your computer before you install Docker. After you've installed IntelliJ IDEA and Docker on your computer, go to github.com/rockthejvm/spark-essentials, where we have the repository for all the code that we will write in this course. Now, once you navigate to this page, there's a bright green button here to clone or download this repository, which I recommend you do for this course. Now, this is a code repository which has intermediate states for all the lectures that we write in this course. So if you navigate or do git checkout any of these tags, you will get to the state before this particular lecture. If you're not a Git user or don't know how to work with Git, there is an equivalent way of getting to an intermediate state of the code by clicking on this releases link and then navigating to whatever state of the code you want to download, and click on this zip link to download the code in the state that it was in before this lecture. In this particular case, the Spark SQL exercises. Now, once you download the repository and you do git checkout start, it will look something like this in IntelliJ. So open that in IntelliJ and it will take a couple of seconds and it will load the structure that will look something like this. Now let me go ahead and explain the structure of the project. The main place where we will write the code is going to be the source folder, and we have here under source main Scala, I already have a playground folder where I will invite you to play around with the Spark as you progress in this course. I already have a very simple Spark application that you can right-click and run right off the bat. And if you run this and the code compiles, then this is a sign that IntelliJ has successfully downloaded the appropriate libraries that we are going to use for this course. I'm actually going to stop this application because it takes a few seconds to start up. Now, speaking of libraries, they will be set in this file over here, build.sbt, where we have all the library definitions that we are going to use in this course. And for this course, we are using Spark version 3, which is the very latest Spark major version, and we're using Scala version 2.12, which is the latest Scala version that is compatible with that version of Spark. As the technology progresses, I will be constantly updating the course with the latest version of the relevant libraries. Moving on, we have some Docker related files. So we have this Docker Compose YML, which contains the definition for a Postgres Docker container. This is a database that we will use to interact with Spark in a couple of lectures later in the course. We also have a shell script called Docker Clean, which will simply eradicate the Docker containers that you've built on your computer. I will teach you how to build them in a couple of minutes. Then we have a shell script called psql.shell, which will simply connect to the Postgres Docker container and will allow you to run SQL queries against the database, which is come preloaded with a good amount of data. And the data is here under the SQL folder. So this db.sql is a huge file loading the Postgres database with a lot of data that we can then import into Spark. So this is the SQL folder in the project. And then we have the Spark cluster folder, which contains some configurations for the Docker-based Spark cluster that we are going to spin up. So there are a lot of files in this project. You don't need to care about most of them. You only need to care about source, main, Scala, and this is the place where we will create our packages and we will write the code. Speaking of the source main, we also have the resources folder where we have the data folder and a lot of data that we're going to practice Spark on. So we will explore the data folder as we progress through the course. Now, let's do our initial setup to set up the Postgres container and the local Dockerized Spark container. So go ahead and open a terminal window on your computer and navigate to the Spark Essentials folder where you downloaded the repository for this course. And do the following. Do docker-compose up. At first try, Docker Compose up will take a good few minutes to download the Postgres image and start up the Postgres container. I already have one installed and my Docker container is already running. It takes a couple of seconds to spin up the Docker container once it's been built. So be patient and download the Postgres database. Pause the video if you need to in order to finish the process of downloading and spinning up the Docker container. After you've done that, navigate to another terminal window on your computer and go to the Spark Essentials folder and execute the psql shell script. So do ./psql.shell. And if the Docker container was installed and spun up correctly, you should get this shell with the Rock the JVM database already connected. And you can inspect the tables and you can do SQL statements on the database by running these commands. For example, if I do \DT, I will describe all of the tables in this database. This is already set up for you. You don't need to do anything about it. The next stage in the Docker setup is to open yet another terminal window or tab on your computer, navigate to Spark Essentials, and this time navigate to Spark Cluster. In Spark Cluster, you have a file called buildimages.shell. I want you to make this file an executable by doing chmod +x buildimages.shell. But I've already done that, so do this on your computer and then execute it. So do /buildimages.shell. It will take a bit of time, much like the Postgres container, but be patient until the process has finished. After you've done that, you should be able to execute the following command. In this folder, you can do docker-compose up and --scale spark-worker equals, for example, 3. And if you hit enter, this should start up a Docker-based Spark cluster. We will interact with it later in the course. At first, it should take a bit of time, but later in the course, we will see that it takes only a few seconds. It's already started in my computer. Good, so that was the setup. Now, as your things are downloading, you probably want to follow along with the video. So let's talk a little bit about the course structure. First, we will do a small bit of Scala recap just to make sure we're all on the same page at the same level of Scala knowledge so that we can work with Spark smoothly. Then we will dive right into Spark using the structured API with data frames. And almost half of the entire course is focused on this chapter because it's so important. Then we will explore Spark types and type-safe processing with datasets, with a lot of work again, and obviously with discussing the trade-offs between data frames and datasets. Then we will do Spark SQL, and we will use Spark as a quote-unquote database, and we will see how Spark can run any SQL statements on data of any size and shape. Then we will explore Spark low-level APIs with resilient distributed datasets, and we will see how important that is because every Spark job will essentially boil down to RDDs. In total, we will write almost 2,000 lines of Spark code from scratch. So we have a lot of work ahead of us, but I promise you it will be very rewarding at the end. Now, before we dive into the actual work, join me in the next video where I'm going to discuss how you can make the best out of this course. Alright, welcome back. Now that we've set up our IDE, let's talk a bit about how to get the best results out of this course. So first, I recommend you go through the course in order. I designed this course specifically for you with a clear deconstructed sequence of topics to click along the way. Of course, you have lifetime access, so you can always revisit an older lecture. A lot of the lectures have exercises and coding practice. I will prompt you to pause the video at those times and think through the exercises. Doing the exercises yourself will basically triple the chances that what you'll learn here will stick, so it's important that you do the exercises yourself. Even if you don't have any idea of how to do them, just let the video play and we'll solve them together. We'll write a lot of code in this course, which brings me to my next bullet. I will be completely upfront and tell you this course will be a challenge, even for experienced engineers. So I want you to approach this course energy-rich, with a high level of focus and commitment. This is not a course that you can watch while you're eating and just say, okay, I get it. Some topics here are big and split in between multiple videos, so I recommend you do 1 to 2 hours of focused work in any one sitting. Now, because the course is difficult, it's completely fine if not everything makes sense at the first pass. That's normal, okay? The approach that I recommend, and this is how I've seen the best results, is that when you find a topic that's overwhelming, you spend some time outside of this course, doing some day-to-day work with your small project or at your job, and then come back to the lecture again. This will help break your mental patterns and approach the topics with fresh eyes. Which brings me to a very important point. Trust the process. I designed this course specifically for you, and I've been teaching this for years, so you're in good hands, and I will be guiding you along the way. And finally, my most important point. Have fun, people. We're playing with some really cool mental models, so feel free to be creative and improve the code that we write in this course, and even improve the solutions that I give. Give yourself the freedom to say, wow, this is awesome, because it is. This technology is awesome, and you will learn to rock it. So take a comfy seat, and let's get started in the next video. Alright, welcome back. Now that we've set up our IDE and our project, it's time to do a small recap of the Scala fundamentals that we are going to use in this course. So here I am in the project that we've just created, and under the source main Scala folder, I'm going to create a new package. You probably remember this structure from the other Rock the JVM courses if you've taken them. So for each chapter in the course, I create a new package, and for every lecture, I create a new application. So under source main Scala, I will create a new package. I'm going to name this Part 1 Recap. And under Part 1 Recap, I will create a new Scala application, and I will name this Scala Recap. I'm going to make this an object, and at the end, I'm going to say extends app. All right, now let me enter presentation mode so that you can see my code a little more clearly. All right, so I assume that for this course you know the Scala fundamentals. For example, declaring values and variables. And you probably remember the structure for doing that, for example, by saying val a boolean. So this is the name of the value, and you can optionally specify a type by colon and then the type, and then on the right hand side of an equal sign you will put in the value that you associate to this name. So this is how you declare a value. Obviously you can declare a variable, and you probably know the difference between the two. You also know about expressions in Scala, for example the if expression. So if I say an if expression, for example, I can say if 2 is greater than 3, then I can say bigger, else smaller. The if in Scala is an expression in that it evaluates to a value, either the string bigger or the string smaller, which brings me to my next difference that I expect you to know already from Scala fundamentals, which is instructions versus expressions. Instructions are the fundamental building blocks of imperative programs like C++ or Python or Java. Instructions are executed one by one, and a program is just a sequence of instructions. Expressions are the building blocks of functional programs like Scala programs, and expressions are evaluated, meaning that they can be reduced to a single value. Instructions or instruction-like expressions in Scala are denoted by the type unit. So for example, I can say val the unit is the result or the value of printing something. So printing something to the console returns the unit type. Besides printing this string to the console, the value of this expression is unit, meaning no meaningful value, or void in other languages. All right, so you know about the very basics of defining values, expressions, and types, including unit. You probably also know about defining functions. So functions are defined with def, the name of the function, parameters with name, colon, type, and then equals, and then the function implementation. So this over here, the number 42, is the whole expression, which is the implementation of this function. All right, you also know that Scala is object-oriented. And object orientation in Scala is done with single class inheritance. For example, if I define a class called animal, that is a class, and I can extend that by saying class dog extends animal. In Scala, there is also the concept of a quote-unquote interface known as a trait. So we have trait called carnivore, for example. And inside traits, we can define abstract, that means unimplemented methods. So we can say def eat with another animal. And this will return, for example, unit. So we can leave this method unimplemented, and we can then say that class crocodile extends animal, and then we can mix in one or more of these traits. So we can say with carnivore. And inside, we're obligated to actually implement these abstract methods. So we can say def eat, and I can say println crunch. Also in Scala, we have the concept of a singleton object denoted by the keyword object, and we can have a singleton here. By doing this, in one line, I've defined both the type my singleton and the single instance that this type can have. So this is the singleton pattern. Now, these singletons can also be expanded with additional curly brace and with additional implementation with methods and members. Now, a particular feature of the Scala language is that if you have a class or a trait and a singleton, an object, with the same name in the same file, that's called companions. So I can say object carnivore. And in this case, the trait carnivore and the object carnivore are called companions. And Scala offers some nice features. For example, the classes or traits and the singleton objects can see each other's private members, and so on and so forth. We discuss more of that in detail in the Scala Beginners course. Now, besides the standard object orientation, Scala has an advanced type system. And just for this course, we are going to only be concerned with basic generics. For example, if I define a trait myList, I can annotate that with a type argument. I can say that this list can be applied to any type, and this type is denoted generically with this name A. Now, Scala has some advanced features related to generics, for example, co and contravariance. For example, if I put a plus sign here, then this myList is called covariant, and we discuss in detail in the beginner's course and most importantly in the advanced course what these contravariance signs mean and what they do. All right, we're not going to be concerned too much about contravariance or covariance in this course, but it's just good to know. Now, a very interesting feature of the Scala language is its method notation. So if I say val x equals 1 plus 2, I can also say val y equals 1 dot plus applied to the argument 2. So there's two things here. First of all is that plus is actually a method, and Scala is very permissive with method naming. Secondly, any method which has a single argument can be infixed like that in this operator notation. We discuss method notations, including pre- and postfix notations in the Scala Beginners course. We're only going to be concerned with infix because that is the most popular. All right, so that's with object orientation. Let's discuss functional programming now. So functional programming is all about working with functions as we work with any other kind of value. And in the Scala Beginners course, we learn that functions in Scala are actually instances of a trait called function 1, function 2, all the way to function 22. So if I define a incrementer as function 1 of int and int, we can instantiate this function 1 trait by saying new function 1 of int and int, and we can supply an implementation on the spot with def apply. And we can say that this incrementer can be applied to an argument of type int, and we can return x plus 1. Now, this function 1, function 2, function n trait is actually sugared in Scala with the type int arrow int. So we can say new int arrow int with this implementation, or we can simply say x arrow x plus 1. This is called an anonymous function or a lambda in Scala. When you define a lambda, you're actually instantiating one of those function n traits. And after you've defined your function, you can actually call it. So for example, incremented equals incrementer applied to 42. And this will return obviously 43. Now, as I mentioned earlier, functional programming is all about working with these functions as values. So you can pass them around, you can return them as results. For example, I can say val processed list as list123 dot map, and then you can pass in this incrementer function. And this will return a new collection. So we have in almost all collections in Scala, we have the functions map, flat map, and filter, which are all called higher order functions, meaning that they can receive functions as arguments. So this kind of construction should already be familiar to you. We're going to use these higher order functions quite a lot when we process datasets and resilient distributed datasets later in the course. So we now know that Scala is an incredibly rich language, and one of the most powerful language features is pattern matching. And let me define a value called unknown, which is of type any. This is important for compiler reasons, and this is just for demonstration purposes. I'm going to give this a value of 45, and I can turn this number into an ordinal description, for example. So I'm going to say ordinal equals unknown match, And inside the curly braces, you can add cases here. So for example, I can say case 1 and then put an arrow first, case 2 second, and case whatever. So this whatever is an underscore right over here. I can put in unknown. Now this ordinal value is now a string because the compiler automatically infers that all the cases return the string type, and so the ordinal is inferred to be of type string. Now, in the Scala Beginners course, way at the end of the course, we discuss a lot of patterns. Pattern matching is more than just this switch on steroids that I've added here. Pattern matching is also good for decomposing values or decomposing collections and binding every part of the pattern to names. So this is an incredibly powerful structure. And it's also met in real life, for example, by trying and catching exceptions. You probably remember the try-catch structure by now, so we can say try, and inside we can put in some code that might throw an exception, for example, throw new null pointer exception, and inside the catch, we can add a number of cases. So case E of type null pointer exception, then we can return something else. And we can also add some other cases and return something else. So these cases over here are still done with pattern matching. So the catch is done via pattern matching. There are also a bunch of other use cases for pattern matching in real life code. For example, the generators in for comprehensions. So for comprehensions, you probably know of them also. They are syntactic sugar for chains of map, flat map, and filter. All right. Now let's go to some of the more advanced stuff. Let's talk about futures. Even though we won't be using futures explicitly in this course, futures are important because they abstract away the computations on separate threads. So let me show you what I mean. First of all, I'm going to import Scala concurrent execution context implicits with a capital I and global, which is an implicit value used as a platform for running threads. And this will allow us to create futures. For example, I'm going to create a future as future. So notice I'm using the type that is the apply method of the companion object of the future class. So I'm going to import Scala concurrent future. And here I'm going to run some expensive computation, which runs on another thread. And I'm going to return a value. Futures are typed with the value that they contain after they've been completed on whatever thread they run on. And in order to process the value of the future, we can use the functional methods similar to the collection methods. So we can say map, flat map, and filter on these futures, or we can call onComplete on the future. For example, I can say a future.onComplete. And here I can run a pattern match on the possible values that this future can be completed with. And the future can be completed with either a success containing the value, or it can be completed with a failure containing some exceptions that might have been thrown on that thread. So I can say a future.onComplete, and I can say case success with a capital S, success with the meaning of life, for example. And I should import success from Scala util. And I can do something with this value. And it's important to note that the action here is a unit expression. So I can say print line, I've found the meaning of life. The $sign here, I haven't mentioned it. This is for an S interpolated string. Notice the S token here before the start of the string, meaning I can inject expressions or values inside this string, and Scala will take care of formatting the string correctly. And in the other case, I can add a failure with an exception, and I can print line, I have failed, and I can inject the exception inside. I should also import failure, again from Scala util. And this is how we can check for the completion of this future. Another very cute Scala feature is partial functions. Now, it's often the case that we write things like a partial function equals, for example, a function that takes an argument as an int, and then you do pattern match on the possible values of that int. For example, saying x match, and in case we get a 1, we return 43. In case we get an 8, we return 56. And in case we get anything else, we return 999. Now, this whole structure here can be reduced to what is called a partial function between an int and an int, meaning the return type of this function. So we can say that this partial function is of type partial function of int and int. And instead of doing this whole pattern match structure here, we can simply say equals and then open and close curly brace, and inside we can put in some cases here. Obviously, this is done via pattern matching. Now, besides doing all this pattern matching for free, partial functions also have a bunch of nice utility methods, for example, or else, and then, and so on and so forth. We discussed this in detail in the advanced Scala course, but just as a reminder of partial functions. Now, one of the most powerful features of the Scala language and of the Scala compiler is implicits. Now, in the advanced Scala course, I spent a good few hours on implicits alone. I'm just going to spend a good few minutes here just to remind ourselves what implicits are and how they work. First of all, implicits are automatically injected by the compiler. So auto injection by the compiler. Let me show you what I mean. If I define a method called method with implicit argument, which takes an implicit x of type int, and it just returns, I don't know, x plus 43 or something like that. And I define an implicit value, implicit int equals, I don't know, 67. Then I can simply call method with implicit argument just like that, and this value 67 is automatically injected here into the argument list by the compiler. So it's as if the compiler automatically completes this with 67 for me. Obviously, I can also pass this argument explicitly, but I can also let the compiler figure that out for me. So implicit call. So this is one. So this was the simple case where we had basically a more powerful version of a default argument, but implicits are much more powerful than that. Let me show you implicit conversions. And in particular, I'm going to show you implicit defs first. That is implicit methods. Let me show you what I mean. So I'm going to create a case class called person. You know about case classes, right? They're basically lightweight data structures that have a bunch of utility methods already implemented by the compiler. So let me create a case class called person with a name as a string. And I'm going to define an implicit def. And I'm going to name this from string to person. And I can pass an argument as a string, and I can return a person with that name. Now, let's also assume that this case class person also has a small method called, let's say, greet. Probably remember this example from the advanced Scala course if you've taken it. So this greet method just prints line hi, my name is name, and I'm going to inject the name in an s-interpolated string. Now, once I've done that, I can simply say the string Bob dot greet. Notice that the compiler automatically allows me to call this method greet apparently on this string, but what the compiler automatically does for me is that this string is automatically converted into a person by calling this method. So the compiler automatically does from string to person with Bob, and then calls the greet method on that. So the way that the implicits work is that when you write a line of code that looks like this, where you call a method on a type that normally does not have that method, then the code will normally not compile, but the compiler is very kind and it will automatically search for every single possible implicit conversion that will allow your code compile. In this case, it will automatically wrap this string into the person case class and it will call the greet method on that, and thus the code can compile. Another way of doing implicit conversions is done by implicit classes. So let me create an implicit class called, let's say, dog, with a name as a string. And this dog, let's say that it barks. So I'm going to add a method called bark, which prints line bark. I don't know. Something like that. Now, because I've defined this dog elsewhere, I'm going to rename this class to be a cat so that we don't have any more conflicts. Now, once I have an implicit class that looks like this and it wraps a string, in my case, I can do much the same thing as I did with a person above. So I can say, for example, Lassie dot bark. And the compiler will do much of the same thing. It will automatically convert this string into a dog with that content as an argument, and it will call the bark method on that. Implicit classes are almost always preferable to implicit defs. Now, when it comes to implicits, and in particular implicit arguments for methods here, the way that the compiler figures out which implicit to inject here into the argument list is done by looking into three areas. First of all is the local scope. That means explicitly defining an implicit value here in the same scope where the method is being used. This is called the local scope. The second place is called the imported scope, which is what we did here when we worked on the future. So this global value over here is an implicit execution context, which will be injected here into the future apply method right over here. So if you don't do that, the compiler will signal the fact that the implicit is missing. So no implicits found for parameter execution context. So this was the imported scope, and then the third place that the compiler looks for implicits is companion objects of the types involved in the method call. So for example, if you're doing list of 1, 2, 3 dot sorted, which takes an implicit ordering as an argument, the compiler will look for an implicit ordering either in the companion object of list or in the companion object of the type, which is int, involved in the method call. And fortunately for int, we already have implicit orderings. Now for our custom types, we can define other implicits for those types as well. And the list for persons, for example, will automatically work as well. We discussed this in detail in the advanced course. We don't need to dive into too many details here. We just need to know about the local scope and imported scope for the purposes of this course, because we're only going to use just a few implicits when we're converting data frames and data sets. So that will be all. Alright, so I hope this small Scala recap served as a good refresher. Even if you are a seasoned programmer in Scala, it's still good to remind yourself of what Scala is capable of from time to time. I'm Daniel, and I will be waiting for you in the next video. Alright, welcome back. Now that we've refreshed our Scala skills, let's talk about Spark a little bit. And in this video, we're going to talk about Spark first principles. So, what is Spark and why do we care about it? Well, Spark is the most popular unified computing engine and set of libraries for distributed data processing at scale. That was a mouthful. We are going to understand what this definition means throughout this lecture and throughout the entire course as we start to use Spark APIs. We're also going to talk about big data a lot, which means that we will have volumes of data that cannot fit on a standard computer. So you'll need a cluster of computers that can process that data, and Spark was built specifically for this task. So I mentioned that Spark is a computing engine. What do I mean by that? Spark supports a variety of data processing tasks. That means Spark can do data loading, it can do SQL on that data, it can do machine learning, it can do streaming, it can do graph processing, and so on and so forth. Spark has hundreds of libraries for data processing. But it's unified in the sense that it has a set of consistent and composable APIs, and Spark supports multiple languages. And all the APIs look very similarly, if not the same, in all these languages. We're going to write Scala in this course, but Spark also supports Java and Python and R out of the box. It's also unified in the sense that Spark can do optimizations across the different libraries, so not within a set of libraries. So if, for example, you're doing machine learning tasks on top of some datasets or data frames, and they are obtained with Spark SQL, which is another set of libraries, Spark is smart enough to optimize your code and optimize the execution of that code on the cluster across the machine learning and the Spark SQL libraries. Spark is a computing engine, meaning that it's completely detached from where the data resides and how the data is being fetched. Spark also supports a set of libraries used for data processing. Spark comes standard with a set of libraries including SQL, machine learning lib, streaming, and GraphX out of the box, but there are also hundreds of open source third-party libraries for specific use cases. Alright, now let me talk about big data for a second, because that's the motivation behind developing Spark. So computing power and data storage are two sets of technologies that have gone on pretty separate paths in recent years, meaning that CPUs, single cores, are only incrementally faster as we are approaching physical limits of developing transistors and of dissipating heat, whereas data storage keeps getting better and cheaper. At the same time, gathering this data keeps getting easier and cheaper and more important for companies. Just to give you an example, a 12 megapixel camera is now $3 or $4 that you can inject into a device. Also, companies are starting to put more value on gathering data. It's actually unwise, almost irresponsible, to ignore the data in your business. So gathering data has become even more important. So data needs to be distributed and processed in parallel because the computing power cannot keep up with this vast amount of information that we're just about to gather. Standard single CPU software that we've written so far in the past decades cannot really scale up, and we need new software, and thus Spark was born. So let me give you a small piece of history of how Spark came to be. Spark was initially developed in 2009 at UC Berkeley as a PhD project by Matei Zaharia and some other researchers at Berkeley. At that time, MapReduce was the de facto standard of large-scale distributed computation, but it was really inefficient for large multi-step data processing applications and machine learning, meaning that every step of the way, with each data transformation, you needed another data pass, and you needed to write that and deploy it as a separate application on the cluster, which was really, really inefficient. So that's how Spark was born. Spark was initially developed as a simple functional programming API on top of these data transformations, and was heavily optimized for multi-step applications. Spark is also designed for in-memory computation and data sharing across nodes, operations that are known as shuffles. We are going to see those in the course. Later, the Spark development team figured out that Spark could be easily used for interactive data science, meaning Jupyter notebooks or Zeppelin notebooks, and ad hoc computation, meaning that you could create a data transformation and just inspect the results once. And so Spark Shell and Spark SQL were created. And later, the development team figured out that this Spark computing engine was so powerful and so composable that it could be easily extended with other libraries. And that's how they created the ML lib, the streaming API, and GraphX, along with putting the Spark project to the Apache Foundation and helping hundreds of other developers to contribute with extra libraries. All right, so this is all very interesting, but why on earth should you learn Spark in the first place? Well, Spark is the most popular engine for data processing in parallel that there is at the moment of this recording. It's being used at hundreds of companies, it processes petabytes of data daily, and it's super well maintained and documented. So if you need a parallel data processing engine, as an engineer, this is your go-to place. Now, for your career, Spark will be a boost. It's one of the most sought-after technologies, the salaries are through the roof, or if you want to do Spark by yourself in consulting projects, the sky is the limit. If you want to do data processing for companies that are not smart enough to analyze their data, or if you want to help other software companies improve the performance of their Spark applications, you can go as far as you want. It's not uncommon for me to see Spark consultants earning as much as $10,000 a day for consulting projects. And in this course, I will teach you not only how to use the Spark APIs and do your thing with your own data, but how to approach data-related problems so that you can extract meaningful value and meaningful insights out of that data so that you can draw some action items out of it. This is the true secret value of this course, because let's face it, Spark is just a technology that's working now, but who knows what else is going to come up. Maybe there's Apache Flink, maybe there's Apache something else, maybe some Microsoft or Google or some other company is going to come up and figure out a better way of processing data. But the insights, the principles, the ideas, and the timeless skills that you will learn in this course will stay with you throughout your entire career. Alright, so with that motivation out of the way, let's talk about some misconceptions about Spark that usually come up, and I want to clear them early. So, first of all, Spark is not concerned with where the data is or how the data is being fetched. Spark can read files, it can read from Azure stores, it can read from Amazon S3, Hadoop, Cassandra, Postgres, any other kind of database, or Kafka message buses, or anything else. Spark is not concerned with data sources, it's only concerned about how to compute new data out of it. Also, Spark is incorrectly assumed to be part of the quote-unquote Hadoop family. Spark has nothing to do with Hadoop. It interacts very well with Hadoop and HDFS, but Spark is its own thing, its own engine, its own libraries, etc. Alright, now let's talk a little bit about the very high level Spark architecture. Now, at the very low level, Spark has a number of primitives that allow it to process data at scale. The most important concept is RDD, that is resilient distributed data sets. We're going to learn RDDs later in the course because that's the more complicated part of Spark. We are going to focus most of our time in this course on the higher level APIs, also known as the structured APIs, because that will get you to insights related to data much quicker. So we're going to learn data frames, data sets, and we're going to operate with Spark SQL. Now, above this high-level structured APIs layer, there's another layer for application-level libraries. So we have structured streaming, MLlib, GraphX, and other hundreds of libraries developed by the community. And in this course, for the Spark fundamentals or essentials, we are going to focus on the high-level structured APIs because that will get you productive in your day job or in your data analyses. And we are going to dive a little deeper into RDDs later in the course to understand the complexities behind the parallel data processing. So that said, let's not waste any time and let's get to it in the next video. All right, good. Welcome back. It's time we started writing some actual Spark code, and we are going to start with data frames. All right, so we're back to our project, and because we've started a new chapter, I'm going to go ahead and create a new package for it. So under source main Scala, I'm going to right click, and I'm going to say new package. I'm going to name this part 2 data frames. This chapter is all going to be focused about data frames. So under the part 2 data frames package, I'm going to right click new Scala class, and I'm going to add a data frames basics application here. So make sure this is an object and make sure it extends app here. All right. Now, in order to actually run an application on top of Spark, we need a Spark session. So this is what we're going to do in almost all of the lectures of this entire course. So this is probably going to become muscle memory, but here's what I'm going to write. I'm going to say val spark equals spark session dot builder, and this will create a new Spark session when we call get or create at the end. But before we call get or create, we are going to add a bunch of attributes to this Spark session. So I'm going to add an app name, and for every application I'm going to give it a suggestive name, which will show up in the Spark UI later in the course. We're going to investigate Spark UIs much later. So we are going to name this application. I'm going to name this data frames basics. All right. And after that, we are going to add a config. You can add many config calls, as many as you like. And for every config call, you set the value of one attribute. So we can say .config, and we're going to write spark.master. And the second argument is going to be the value of this configuration, which is going to be local. And for all the testable applications that we are going to write in this course, the configuration for Spark Master is going to be local because we're going to execute the Spark applications on our computers. Now, when we get to the projects later in the course, after the lectures, we are not going to configure Spark Master to be local, but we're going to pass in a configuration for Spark Master and whatever URL the node is going to be when we deploy the Spark application. But on that, later. So at this point, we've created a Spark session, which will be our entry point for reading and writing data frames. So with that being said, let's go ahead and read our first data frame. So this is creating a Spark session, and the following is going to be reading a data frame. So val, let's call us first df for data frame, and we're going to say spark.read, which is a data frame reader. And then we are going to call .format. And for the purpose of this example, we are going to read a JSON file. So we are going to pass in JSON as argument for format. And let's say we would like to read the cars.json file from the source main resources data. So I'm going to pass in the JSON format. I'm going to also specify an option, which is much the same as a configuration for the Spark data frame reader. And I'm going to add infer schema with camel case. So infer schema, and the value of this option is going to be true as a string. And I'm going to then call the load method. And inside the load method, I'm going to pass in the path of the file that I want to load. So in this case, source main resources, and then data, and then cars.json. So what we've done here is we've instructed the Spark data frame reader to read a JSON file with infer schema true, meaning that all the columns of this data frame are going to be figured out from the JSON structure, and the path of the file is here. Now, the result of this chain of this call is a data frame. And the first thing that we can do with this data frame is, for example, to print it out. So let's say first df.show. When you call show, you will see in the console a tabular-like format for this data frame. So we're ready to actually run this application. Give it a second to compile. And notice we have a bunch of output from the Spark session. And at the end, we have our first data frame printed out as a table. So notice here that we have acceleration, cylinder, displacement, horsepower. So these are all attributes for cars. If I go ahead and try to open cars.json, you'll notice that every single item in this file is a line containing a JSON describing a car. The car is described by a name, the miles per gallon, cylinders, displacement, and all this kind of data. And Spark is able to figure out the structure of this data and to display it as a table here. Obviously, we have more cars than just the 20 that we are printing to the console. So Spark instructs us that it's only showing up to 20 rows, but we have way more cars here. We have hundreds of cars. All right. So let's get back to our code and let's congratulate ourselves for doing our first operation with a data frame. So this is showing a data frame. We can also print the description of its structure, which is known as a schema. So we can say firstdf.print schema. The print schema returns, watch what we're going to see. It returns the description of all the quote-unquote columns of this quote-unquote table. So we have acceleration to be a double with nullable true, meaning that it can contain nulls, cylinders, displacement, horsepower. So this schema is essentially the description of every column in this quote-unquote table and the type of the values that this column can contain. So Spark figured out that the types of these columns are double, long, strings, and so on and so forth. So Spark is able to parse that automatically. All right, now we've printed a data frame, but what is a data frame? Well, a data frame is essentially this schema, which is the description of the attributes of the data, and a distributed collection of rows, which you can see in this table, that are conforming to that structure. So for example, if I do firstdf.take 10, this will take the first 10 rows out of this distributed collection. So you can think of a data frame as a distributed collection of rows that are conforming to this schema. So I can do for each print line in much the same way as we're calling for each on any other collection, and we're going to see some interesting stuff. So the show method prints the data frame in a table-like format, but the print line is going to show us something else. So basically every single row is essentially an array of things, of data, which can be either numbers or strings or dates or anything else, basically. A row can contain anything, but it has to conform to the schema that a data frame has. So when you say firstdf take 10, you get an array of rows. So this is how we can get rows out of the data set. Now, I also want to talk about the schema because Spark has a very interesting way of managing this information about a data frame. So Spark types describing the data, which you see here as double, long, string, and so on and so forth, are explained by some case objects that Spark uses internally. So this is not known as at compile time, but it's rather known at runtime when Spark evaluates the data set. So let me describe our first Spark type. So if I declare the double type or the long type in Spark, I can say val long type equals long type with capital case. So look at this way. The org Apache Spark SQL types long type, and this O mark meaning that it's a case object. So the long type is a singleton that Spark uses internally to describe the type of the data inside a data frame. And we're going to be using these case objects to describe schemas in data frames. And there's one of these case objects for every possible type that you can imagine. So for double, we have double type. For string, we have string type. For dates, we have date type, and so on and so forth. Especially for complicated types, which often describe data frames with multiple columns, not just a single column, we have struct types. So let me define my first schema as a struct type. So I'm going to define my cars schema as a struct type. And this struct type is also from org Apache Spark SQL types. And the struct type will contain an array of what we call struct fields, again from org Apache Spark SQL types. And these struct fields have obviously some apply factory methods that contain the names. For example, I'm going to give this guy a name. So the struct field describes a column, and the column has a name. and the type, which in this case is a string type, okay, make sure you import the right string type from org Apache Spark SQL types, otherwise your code may not compile correctly. And the third optional attribute is whether this struct field, whether this column contains nullable values, whether this column contains nulls. So I'm going to say nullable equals true or equals false. Usually the default argument is true, meaning that it can't contain nulls. All right. So in order to describe a data frame, you'll have a struct type with an array of these struct fields that describe every single column. Now, in the playground file, I already have my cars schema written for you so that you don't need to write it manually and mistype one of these column names. So I'm going to shamelessly copy this from the playground application and paste it here, because I assume you got the picture. So we need to import the right types, and we should be good. So this is the schema of a potential data frame. So this is how you can create a schema by yourself, which is often useful in practice. In practice, you shouldn't really use infer schema because Spark may infer the wrong types for you, but more on that later as best practice. Now, this is how you can construct a manual schema. If you want to obtain the schema of an existing dataset, you can say val cars df schema equals cars df dot, or how do I call this? First df. Okay, first df dot schema, which you see it's a struct type over here. And if you print this out, so if I do print line cars df schema, you will see essentially this kind of description that I wrote above. So let me execute this application just for you guys to convince yourselves. A few seconds for Spark to execute, and notice that the schema of this existing dataset is a struct type containing all these struct fields in sequence. All right, so this is how you can obtain the schema of an existing dataset. Now, in production, when you read a data frame, you shouldn't really use infer schema true. That is because in practice, we might end up parsing dates, for example, in an incorrect way. So this kind of date format, for example, is not really standard. It's not ISO standard. So if you take a look at the data frame schema description, when you do infer schema, you'll see that the year is a string rather than a date. This might be important in practice when you are operating with dates. So this is why in production, you shouldn't really use infer schema, but rather you should define your own schema and force the data frame to conform to that. And if you get any exceptions at parsing, then you would need to make your data frame conform to that schema or do some additional parsing configurations if you want. All right, so let me show you how to read a data frame with your own schema. So let's define another data frame. Let's call this cars df with schema to be spark.read. So remember what we did earlier. We said spark read and then .format JSON. And then instead of the option to infer schema true, we are going to pass in our own schema. So I'm going to say schema, and I'm going to pass in cars df schema. And then I'm going to also load from the same path. So I'm going to say .load, and we should be good. If you ever want to print the cars df with schema, it will show the exact same thing as the other data frame. Now, I want to show you how to create rows and data frames by hand, meaning actually inputting values yourself in code. So it's pretty rare that you have to do that, but it's very useful for testing purposes. So if I want to create a row, I will need to use the row apply factory method. So row is a class from org Apache Spark SQL, So we will import that, and in the row constructor you can pass in anything that you want. So the row apply factory method can take any bits of data that you would like, and you will obtain a row object. As I mentioned earlier, rows can contain anything at all. So let's input the data for one of the rows in the data set for Chevrolet Chevelle, and in the playground application I already have a bunch of rows, so I'm just going to copy one of these because I don't know all the data by heart. So you see here that I'm constructing a row with all these objects here as bits of information. Now you can also construct a data frame manually from a sequence of rows, actually from a sequence of tuples of these bits of information. So you can say, let's call this create df from tuples, and let me fetch my cars as a sequence of tuples, and in my playground application I have a sequence of rows, but I'm actually going to delete the row apply factory method, and I'm only going to keep the tuples. So in my application here I'm creating a sequence, and instead of rows I'm actually going to leave just the tuples. So I'm going to delete the row constructor here, and I'm going to use an IntelliJ trick. I'm on a Mac, so I'm going to hit Shift Option, and then by double clicking on Option and holding it, I will hit my down arrow, and then I'm going to delete from all the cursors at the same time. So this is pretty neat, Sublime-like style. If you already know these tricks, it's very, very useful. Otherwise, you can simply delete every one of these rows in turn. So right now I have a sequence of tuples, and I can construct a data frame out of them. So I'm going to say val manual cars df as spark dot create data frame, and notice that this create data frame method is heavily overloaded. We are going to use this method over here with a sequence of things where the thing, which is a tuple in our case, derives from product as a trait. So we are going to call create data frame from cars. Now, there is no option to specify your own schema because the types of the tuples being known at compile time, Spark can automatically create a schema for you. And if you print this manual cars df, you will see all of these entries over here. Now, there is an important note and a distinction that I would like to make early. The schemas are only applicable to data frames, not to rows. So notice that rows can actually contain anything they want. There is no structure imposed to rows, but otherwise data frames have schemas. So I'm going to say note. DFs have schemas, rows do not. Now, I also want to show you a few nice tricks for creating data frames out of manually constructed tuples with implicits. So I'm gonna create DFs with implicits. So I will do import spark.implicits._. Notice I'm importing implicits underscore from Spark, the lower cap Spark, which is our Spark session, which is an object, right? So I will import the implicits from this Spark object, and then I can say val manual cars df with implicits as being cars dot to df. Notice that the sequence has already been enhanced with the to_df method, and optionally we can pass in column names this time around. So we can say cars to df, and we can pass in our column names, which in our case are name, miles per gallon, cylinders, displacement, horsepower, and what else? This is probably the weight, this is probably the acceleration, year or date of whatever appearance, and the country of origin. So we have weight, then acceleration, the year of origin, and then the country of origin. All right, so we can pass in the column names. In the previous call, when we called spark.createDataFrameCars, the schema was auto-inferred from the tuples, but we had no column names. So just to show you how these data frames are being constructed and what schemas they have, let's print the schemas for both. So I'm going to say manual carsdf.print schema, and then manual carsdf with implicits.print schema, just for you guys to see how the schemas are being inferred by Spark. All right, so notice that the manual carsdf, which was being constructed from the tuples, has this schema with the column names _1, _2, _9, because those are the members of the tuple. If you remember from the Scala Essentials, we describe the members of the tuples by _n. Whereas the manual carsdf with implicits has the schema with the correct column names, which we passed here in the cars.toDF call. All right, so what we learned? We learned how to create a Spark session, which will be the entry point for all our Spark applications in this course. We learned how to create a Spark session by calling the builder method, giving it a bunch of configurations, and then calling get or create. The Spark session is our entry point for creating, reading, and writing data frames. Speaking of data frames, we learned how to read data frames from files by calling Spark read, and then passing in a bunch of options, and then we learned how to do our first operations on data frames by calling show, print schema, and processing the rows of the data frames. Speaking of rows, we learned that rows are unstructured pieces of data, and the information about the structure of the data is applied to the data frame in the form of a schema, which is the description of the fields known as columns and the types for all of those columns. We also learned about Spark types and how they are known to Spark at runtime rather than compile time. All right, you've learned a lot. Join me in the next video where I'm going to give you your first exercises. All right, nice, welcome back. You've learned about data frames. It's time you do your first exercises. Good, so we've covered quite a lot. Just to warm up, let's give you guys our first exercise. So, I'm actually going to give you two exercises. First, I would like you to create a manual data frame describing smartphones, in much the same way as we're describing cars here above. And for smartphones, you can add any details you want. For example, you can add the make, the model, the processor, or the amount of RAM, the screen dimension, the camera megapixels, and anything else that you would like or you would find relevant. All right, so I want you to create a manual data frame describing some smartphones and printing them out to the console by calling the show and the print schema method. Secondly, I would like you to read another file from the data folder. For example, you can work on the movies dataset. So you can load the movies JSON in much the same way as we're reading the cars JSON file. For example, the movies.json. And I want you to print its schema and count the number of rows by calling the count method. So feel free to pause the video now and work through these exercises yourself. And I will come back with a solution in just a few seconds by the magic of video editing. All right, so I hope you did that. The exercises are pretty easy, and their goal is just to get you warmed up with creating and using data frames. So let's go to the first exercise. Create a manual DF describing smartphones. Well, let's create a bunch of smartphone rows in the form of tuples in much the same way as we did with cars previously. So let me create a val called smartphones, as a sequence of tuples. And it'll probably vary depending on what you think is relevant for smartphones, but I'm just going to add the make, model, and maybe the platform, Android, iOS, whatever, and the camera megapixels if I remember them. So here goes. I will add first Samsung and Galaxy S10. Platform is Android, and the camera megapixels is, I don't remember. It's like 12 or 25, or I don't remember. Megapixels aren't really that relevant in this day and age. Maybe even has multiple cameras. I don't remember. So I'm just gonna give this Samsung Galaxy S10 just a meager 12 megapixels for one of its cameras, for what it's worth. Let me add an iPhone. So iPhone X. That's the model, but let's add the make here. So there's Apple and iPhone X. The platform is iOS, and the megapixels, I don't know, 13, whatever. I remember it has multiple cameras as well. And the mother of all phones, Nokia, and let's add 3310. For those of you old enough to remember, the 3310 is one hell of a smartphone. It has the best platform, and it has exactly 0 megapixels. So let's just consider these smartphones and let's create a data frame out of them. So I'm gonna create smartphones df as smartphones.2df using those implicits. So 2df is a method for enhancing the sequence type, and we're only left to pass in the column names. So this is make, model, platform, and megapixels, camera megapixels. You can alternatively create a data frame using the spark.createDataFrame with your smartphone's sequence of tuples, but you will lose the column names. All right, so we can simply say smartphones df.show just to make sure that we created the data frame correctly. And we have our first exception here. So we have Scala.any. That's because I have nullable here. Let's give it a 0. We'll deal with null types later in the course, so don't worry about that. I'm going to teach you everything about handling nulls. All right, so we have here our data frame printed as a table. So we have Samsung, Apple, Nokia with all the data that you inputted over there. So this is how we can create a manual data frame. You saw this earlier, and now you've done this yourself. Now for exercise number 2. So this was exercise number 1. And let's do exercise number 2. Read another file from the data folder, for example, the movies.json, and print its schema and the number of rows. Well, let's call movies.df as spark.read. You probably remember that. And then you call format, and the format is JSON. And then we call option with infer schema true, and then load from where? We have source, main, resources, data, and movies.json. So this is how we we read the data frame, and then all we're left to do is say moviesdf.print schema and print line moviesdf.count. Moviesdf.count will compute the number of rows in this data frame. So in here we can say the movies df has, and I can inject this guy as an s-interpolated string, rows. Okay, so let's execute this application and give it a couple of seconds for Spark to initialize. It should be pretty quick. So the movies DF has 3,000 rows, and the movie's schema is pretty big. If you try to input your schema manually, it will probably take a while. So that's why I used infer schema true. Now in production, as I mentioned earlier, you would not use infer schema true, but rather you would input your own schema. Now for movies, this is pretty unfeasible to do in a couple of minutes. So I'm just using infer schema true because all I want to practice here is just reading data frames. All right, so those were your first exercises. Congratulations. But there's more coming, and I can't wait to show you in the next lecture. Good, welcome back. You've dealt with your very first data frames, but it's time to understand what data frames actually are, how they work, and some rules associated to them. So, what are data frames really? You can think of data frames as some kind of distributed spreadsheets with rows and columns. So you can think of a data frame as a table, which is split in between multiple nodes in a Spark cluster. Very importantly, the information that each Spark node receives is the schema of the data frame and a few of the rows that compose the data frame. Now, in more technical terms, data frames are distributed collections of rows conforming to a schema. And you saw what a schema was earlier. A schema is a list describing the column names and column types. And we've dealt with our first schemas. We wrote our struct types with struct fields describing every single column with the name and the type. Now, it's very important to know that these types are known to Spark when the data frame is being used, not at compile time. We will learn later in the course how we can make these types available at compile time with type-safe data sets, but that will come later in the course. The schema can hold an arbitrary number of columns for data frames that can be arbitrarily wide in the number of columns. But all rows have the same structure, and as we discussed earlier, rows themselves do not have schemas, but they conform to the same structure. Now, these collections of rows need to be distributed because either the data is too big for a single computer or it takes too long to process the entire data on a single computer. That's why Spark uses partitioning. This is a new term. Partitioning means that the data is being split into files and then shared between nodes in the cluster. Partitioning will impact the processing parallelism of your data. More partitions, for example, may mean more parallelism. But if you have, for example, 1,000 partitions, that is 1,000 small files that compose your data frame, and a single node to process them all, the parallelism will still be 1 because you only have one node to process your data. Conversely, if you have one partition and 1,000,000 distributed nodes in your Spark cluster, only one of those nodes will have access to the partition, and so your processing parallelism will still be 1. The way that we do partitioning is a big performance topic in Spark, and we will learn how to do that in the more advanced courses of this series. Alright, more things about data frames. First of all, they are immutable, much like most collections in Scala, meaning that they cannot be changed once created. If you want to modify them, you will create new data frames via transformations, and most of this course we will deal with lots and lots of transformations. Speaking of transformations, there are a bunch of transformation types. We won't be dealing with these super technical terms too much, but it's good to know them. A narrow transformation means that one input partition will contribute to at most one output partition. So the partitioning is not changed in a data frame. For example, if you do a map, that will transform the data frame row by row, and so the partitioning is not changed. Whereas a wide transformation will involve one or more input partitions to create many output partitions. So the partitioning of the data frame is changed. For example, if you do a sort, that will involve exchanging data between partitions in between nodes in the cluster. These operations are known as shuffles, which are data exchanges between cluster nodes. Shuffling occurs in wide transformations, and it's a massive, massive performance topic because it can impact the time that your job takes by orders of magnitude. So it's a very hot topic in Spark performance. This is an important problem in Spark, and we will come back to it quite often throughout this entire series. Alright, now let's talk a little bit about how data frames work at runtime. First of all, let's talk about lazy evaluation. Lazy evaluation is a mechanism for Spark to wait until the very last moment to execute the data frame transformations. Now, as your application gets more involved and you do more data frame transformations, Spark will do planning before actually running any code. So Spark will compile all of the data frame transformations and dependencies into a graph before running any code. So Spark will know beforehand every single step that it will have to take, including data exchanges between nodes, before it actually starts loading or running any code. There are two plans that Spark will compile. First of all is the logical plan, which is the data frame dependency graph, plus all the descriptions of the narrow and wide transformations that Spark will have to execute. So Spark will know in advance every single step. Also, Spark will compile a physical plan, meaning that Spark will optimize the sequence of steps and it will know which node will execute which parts of the transformations. Now, because Spark knows all the steps in advance, it's able to insert optimizations into the plans as well. For example, avoiding multiple passes over the data, or pushing down predicates in SQL, or chaining multiple predicates or multiple where clauses into one, and so on. Now, speaking about transformations, I also want to insert another term here, which is actions. So we're going to discuss transformations versus actions. A transformation will describe how new data frames are obtained. So when you do, for example, a map on a data frame, that is called a transformation, versus an action which actually start executing Spark code. So when you call an action, which is, for example, show or count, that will actually trigger Spark to evaluate those data frames. All right, so I've introduced a bunch of terms that I'm going to refer to throughout the rest of this course. If you get confused about any of them, feel free to get back to this lecture. In the meantime, I will be waiting for you in the next video. All right, welcome back. In this lecture, I'm going to teach you how to read and write data frames in various formats to and from various data sources. But that was too long of a lecture name, so I've just named this lecture Data Sources. The objective here is twofold. I'm going to teach you the general structure of reading and writing data frames, and I'm going to show you the various quirks and various configurations for all the formats that you can write and read data frames. And I will show you how to use files and databases as 99% of the use cases where you will need to ever read and write data frames from. Alright, so I'm back in our project, and for this lecture I'm going to create a new application under the Part 2 Data Frames package. So new Scala class, I'm going to name this Data Sources, make it an object, and extends app. All right, now the start of our application is defining our Spark session. So I'm going to define Spark as Spark session.builder.app name, and I'm going to give this app the name Data Sources and Formats. I can afford a longer name, and then I can config Spark master to be local. This is really important because otherwise your Spark job will not run locally. And then get or create. So I've defined my Spark session and I'm now free to read and write data frames. Now I'm going to open up the previous data frames basics code, and I'm going to copy the schema and the reading of the cars data frame. So I'm going to copy the cars schema here in our application. And I need to import everything. So under org Apache Spark SQL types, I'm going to hit an underscore to import every single type. And I'm also going to go ahead and copy the code that we used to read our cars data frame. So our first df over here. So I'm going to copy that over here as well. All right, I'm going to name this cars df. Now, in this part of the lecture, I'm going to show you the general structure of reading any data frame from any data source so that you are flexible in whichever data source you end up using. So, reading a data frame will need the following. So, we'll require a format, in our case JSON, it will require a schema, which is optional because we saw in the previous lecture that we can either use infer schema true, or we can say .schema, and here we can pass in our cars schema if we want it. So this is how we can enforce a schema into reading a data frame. All right, so we have format and schema, or infer schema true, and 0 or more options. So we saw earlier in the previous lecture that we used option, for example, infer schema true, which in our case in the code that I've written over here is conflicting with the explicit schema enforcement. So I'm going to delete the parameters here, but rather I'm going to use other option. And particularly useful for reading a data frame is the mode. The mode decides what Spark should do in case it encounters a malformed record. For example, if a JSON does not conform to the schema, or if the JSON is simply malformed. And there are various options for this mode. We are going to use fail fast in this case. The other options for this mode are drop malformed, which will ignore faulty rows, and permissive, which is default. So if you don't specify a mode, implicitly the mode will be permissive. And the fail fast will throw an exception for Spark if we encounter a malformed record. And finally, we can call load at a path, which can be either a file on your computer or a file anywhere else, for example, in an S3 bucket on Amazon. So you can put in an S3 / whatever path your data frame resides in, or you can add the path as an option. So you can say option for path, and then you can pass in the value for that path, and at the end simply call load. So this is an alternative way of reading the cars data frame. This code that we wrote is essentially equivalent to what we wrote earlier in the lecture, but this mode failfast is probably the only new concept. So I'm going to demonstrate how this works and how Spark will eagerly crash if we malform a record in our cars data frame. So let me go to cars JSON, and let me take one of the records here and just change, for example, its type. So for Buick, I'm going to change the miles per gallon to unknown, which is a string as opposed to an integer or a number it's supposed to be. So when Spark tries to read this data frame, it should crash eagerly, but I will need to call a show on the cars data frame, because if you remember, loading data frames and data frame transformations are lazy until I actually call an action. So I'm going to say carsdf.show, which is an action and will trigger Spark to actually load the dataset and print it to my console. So I'm going to right click and run, give it a few seconds to compile and for Spark to execute. And we should see a stack trace here, which is a failure. And just to prove that the failure was caused by the mode, look at this. Malformed records are detected in record parsing. Parse mode fail fast. So this is caused by our option here at the data frame loading phase to crash eagerly when we encounter a malformed record. If we hadn't specified this, the mode would have been permissive, and Spark would have parsed the dataset and just ignore the record with the invalid value. So I'm going to remove this show, and I'm going to restore my data frame back. So I'm going to Command Z or Control Z until I get to the initial state. Now, another way of reading a data frame, instead of passing all these .option, chain calls, is to use an option map. So if I say, for example, cars df with option map to be Spark read, and then again format JSON and .schema car schema, but let's use infer schema true this time. I'm going to do options plural And look at this method. It takes a map between a string and a string. So we can say map and pass in all my options in here. So I'm going to say mode thin arrow fail fast, path thin arrow this guy, and then infer schema true. And this is the equivalent of passing many dot option calls, but rather passing all the options in the same map. This also has the advantage of allowing you to compute your options dynamically at runtime. So this is an alternative with options map. Now, writing a data frame is very similar. So you will need a data frame writer and do dot format and pass in a bunch of options if you want. So you can say load here at the end or save in case of writing. So let me show you how to do writing. All right, let me close that out. So writing data frames has a very similar structure to reading data frames in that we have this builder style pattern. So let me show how to do writing. So we can say carsdf.write, and this returns a data frame writer. So notice that we're calling a write method not on the Spark session as we did on read, but on the data frame that we're writing. So this returns a data frame writer, and we need to provide a number of information bits. So writing dfs requires setting a format, much like reading, requires setting a save mode, which in this case can be override, or append, or ignore, or error if exists. These values specify what Spark should do if the file that we're writing to already exists on our file system. So for this example, I'm going to use overwrite. And the format, I'm going to use JSON as well. So we need a format, we need the save mode, we need a path where we need to save the data frame to, much like reading. So I'm going to add it here. And finally, 0 or more options. So let me write this down. So carsdf.write, I'm going to use .format JSON. Then I'm going to say .mode. And there are a bunch of static values that we can use here. We can either use the string overwrite, but a more type-safe version of doing that would be save mode dot overwrite. And then we need to specify the path, or to say option path, and then we can say source main resources data cars duplicate dot JSON, and then finally we call save. Alternatively, instead of providing this option, we can pass in the path as an argument to the save method. And inside this builder pattern, you can pass in as many options as you like. In particular, for writing, we have options for sorting, for bucketing, and for partitioning, which are pretty advanced, and we will touch upon them later in the Spark series. Now, just to show you how this application would work, let me go ahead and run this. And let me show you how the written data frame looks like under our source main resources data, because the structure might come across as a little surprise. So notice here, cars dupe JSON, the path that I specified here in the write, in the argument for save here on the writing code, is actually a folder. So cars dupe JSON is actually a folder that contains a bunch of files. So the file with the actual data is this guy, part with the unique identifier .json over here. So if you double click on it, you'll see that the data looks very much the same as the original cars JSON. Also, as part of this data frame, we have the _success file, which is just a marker file for Spark to validate the completion of the writing phase of the data. and some CRC files to validate the integrity of the other files. Now, if the data frame is large, we talked about partitioning earlier, and we mentioned that each partition is its own file. So if you have a huge data frame, if you're working with big data in practice, and you're saving a data frame, you will see many more of these part unique identifier.json files if you're saving a big data frame. So this is just one because our data frame is quite small. Alright, so we've just discussed the general structure of reading and writing data frames from any data source at all. Now, I'm going to continue in the next video where I'm going to discuss the various flags that you can set for each of the data sources and for various formats. So coming up in the next video. Alright, we're back to data sources. Let's see what else we got. Cool, we're back to our project, and in this video I'm going to show you the various formats that you can use plus the various flags that you can use for each. So I'm going to start with JSON because we've been dealing with it so far. So JSON flags. Now, I'm not going to read another data frame by creating another val. I'm simply going to use Spark read. So I'm going to say Spark read and then format JSON, and I'm going to pass in a bunch of options here that are specific to JSON. For example, you can specify a date format if the schema that you want to apply to the data frame has a date type. So right now our car schema has, for that year, which you remember it was a date, we have string type. But if we used a date type, Spark will attempt to parse the string into a date by a defined format by us. So we can say .option, and we can say date format. And if we go to cars.json, you will see that the year date here is in the format year-month-day. So we can specify a date format in that style. So we can say YYYY for the year, dash month month, and dash day day with lower cap d. Now, the date format only works with an enforced schema because otherwise Spark doesn't have any clue on which fields to attempt parsing for dates. So you must specify a schema. And I'm going to apply cars schema. But in this case, we need the year to be a date type. Now, if we specify that the car schema is of date type, the earlier data frame that we read here will be unable to parse the year because we haven't specified the date format. And if we don't specify a date format here in the form of an option, Spark will try to use the standard ISO date format. Now there's something that I wanted to mention here on dates. Dates are particularly useful for data science and for data processing in practice. And so parsing dates is a sensitive topic in Spark because if either the date format that you specify here in the form of an option or the date in the form of a value is incorrect, then Spark will put in the value null for that particular cell, which might cause problems in production because you might turn up a lot of nulls. So make sure you have the correct date format and the dates in your data frame are written correctly. So I'm going to mention the two things here. So couple with schema. If Spark fails parsing, it will put null. There are also timestamp formats that you can use. So for more precise times, up to second precision, you can use timestamp format instead of the date format. Now, specific to JSON are also use single quotes or allow single quotes. And you can put in the value true here to treat the double quotes the way that you treat single quotes in JSON. So if you have a JSON that's formatted with single quotes, you can use this flag here as well. And finally, a very important flag is compression. because data frames are usually big and compression can actually save quite a lot of space. So you can use compression, in this case uncompressed, which is the default value if you don't specify the option, but the other values are bzip2, gzip, lz4, this is the format for 7-zip, snappy, and deflate. So if you compress your JSON files in one of these formats, Spark is able to decompress that automatically. And finally, we can do a load from source main resources data cars.json. Now, the final thing that I wanted to show you is that instead of using .format and .load at the end, you can remove the format and you can simply say .json. So the Spark data frame reader has a first class .json method. All right, cool. So that was JSON. Let's talk about CSVs. So CSV is extremely popular. You probably saw quite a bunch of CSVs so far. Now, you would think that CSV, because it's such a simple format, that it would be easy to parse and to turn into data frames. But CSV is actually one of the biggest pains in the neck in practice, because CSVs are so flexible that they can support different kinds of separators, line encodings, character encodings, and so on and so forth, that it's extremely hard to correctly parse CSVs from the first try. This is the reason why CSV actually has the most possible flags here under the Spark data frame readers. I'm going to mention a few that I think will be the most helpful to you. And for this example, I'm going to read another data frame here. I'm going to read stock CSV. So notice that this dataset is pretty simple. We have 3 entries per row, a string, a date, which is in a very wacky format, and a double. So it's small enough that it warrants its own schema. So we can say val, let's call this stocks schema, is a struct type with an array. And we have 3 struct fields here. So struct field with the name symbol, which is a string type. We have another struct field, which is called the date. I think that's the date. And that is a date type. I'm explicitly mentioning a date type here because I will attempt to parse the dates in a very similar fashion that we did with JSON earlier. And another struct field that we have price, and that's a double type. All right, now let's try to parse the stock CSV into a data frame. So I'm going to say Spark read, and then I'm going to pass in the schema, which is stock schema. Obviously we need the format, so format CSV this time, and we can pass in a bunch of options. In the same style as we did with JSON, we can pass in a date format. So I'm going to simply paste it here with the same 2 mentions here. We need to couple the date format with the schema, otherwise Spark will not know which fields to try to parse. And the format here will be month, 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 a space, day, day, and then y, if I remember correctly. So we have 3 letters for the month, at most 2 letters for the day, and 4 letters for the year. So this will be our date format this time around. Now, the CSV specific options, for example, are header true. Why is that? Well, CSVs may or may not have a header. And if you're parsing a CSV file with a schema, you need to make sure that the names of your columns are exactly the same as the names of the columns in the CSV file. So the header true ignores the first row because that's the column names, and Spark will use the column names to validate against your schema if you specify it explicitly. Another CSV specific separator is sep, which specifies the actual separator for the values. So here the default value is the comma, but in practice you will see semicolon separated values or tab separated values, whatever you want. All right. Now, we also have the option to specify the null value, which in my case will be the empty string. Null values are important because there is no notion of nulls in CSV. So this will instruct Spark to parse this value as null in the resulting data frame. Now there are a bunch of other flags that you can use for CSVs. For example, escaping restricted characters, for example, the comma, because of course you can have values that have a comma in them, to specify multi-line values, to specify quotes, and so on and so forth. There are a bunch of options on CSVs, but these three are the most important that you will probably use all the time. And finally, you can do .load, and you can say source main resources data stocks CSV. So you can specify .format and .load, or you can simply say .csv. The data frame reader has a first-class method for reading CSVs. All right, so we discussed JSON and CSV. Let's talk about Parquet. Now, I haven't discussed Parquet yet, but Parquet is very important. Parquet is an open source compressed binary data storage format optimized for fast reading of columns. And it works very, very well with Spark. In fact, it works so well that Parquet is the default storage format for data frames. One of the advantages of Parquet is that it's very predictable. So you don't need so many options that you had on CSVs, but rather you can simply say Parquet and you will know that it will be stored in the right format. So for this example, I'm going to do a writing. So I'm going to say carsdf.write. And for writing, you already know the mode, and I'm going to use overwrite. So save mode overwrite. And I can simply say Parquet. Add a path. So source main resources data, and I can say cars.parquet. Now you can use a .parquet, or you can simply specify save, because the Parquet format is the default format in Spark, so you don't really need to explicitly say format Parquet. Although that is permitted as well, but it's pretty redundant. It doesn't do anything because Parquet is default. So you can say carsdf write, mode, save, and Spark will save the data frame in Parquet format. Now, let me go ahead and run this application just for you guys to see how it would look like. So I'm gonna right-click run, and I should be looking for another folder here under this source main resources folder. So I have cars.parquet, which was written as a folder in much the same way as the carsdupe.json was written earlier. And the cars.parquet has a very similar structure to the other data frame. We have the _success, this is the marker file, and we have the snappy parquet file, which actually composes the data. Now, if you click on it, you won't see anything because it's binary compressed. So you won't see too much here, but you will see something very interesting. If you open this folder in Explorer, I have a Mac, I do reveal in Finder. If you're on Windows, you will reveal in Windows Explorer. If I reveal in Finder and you look at the snappy parquet file, you'll look at something like 12 kilobytes of data, whereas the carsdupe.json file has 73 kilobytes of data. So you're looking at 6 times the compression in snappy parquet. In practice, you will even see higher compression, maybe 8 to 10 times. So no matter how cheap data storage is nowadays, if you're working with big data that is petabytes of data or even beyond that, compression can actually play a role, and it maybe, just maybe, can save you $1 or $2. All right, so let's get back to our code. You saw Parquet in action. Let's talk about text files. Text files are super easy. Let me go to my source main resources data and let me create a small text file. I'm going to call this sample file or sample text file .txt, and I'm going to put in a bunch of text. This is Scala and I love Spark. So if you read a text file, every single line in this text file will be considered a value in a single column data frame. Let me show you. So I'm going to say Spark read text, and I can actually pass in a path. So source main resources data sample text file .txt. And if I do show on this data frame, you'll see every single value on a new row. So give this a few seconds to run. The other data frames are still being written here. You see the files were overwritten. So look at this guy. So this is my data frame, and the only column here is called value, and every single value in this column is actually being written on a separate row. So this is pretty straightforward. Now, the final thing that I want to show you before I give you a couple of exercises to practice this is reading from a remote database. And we've talked at the beginning of the course how we set up our little Postgres Docker container. Now, reading from a remote database and passing the data to Spark is a common pattern because to analyze big data, data is often being migrated from databases to Spark for processing. So I'm going to show you how to do that. Now, before I run any code, I should start my Postgres Docker container. So go to a terminal window and navigate to the Spark Essentials folder where you downloaded the course materials and run docker-compose up, which, if you remember, will start the Postgres container. Now, I'm assuming you ran docker compose up earlier in the course when we set up our Docker containers so that you don't set up our database just now. If you're setting up your Postgres container just now and it's adding the data as we speak, then put a pause on the video and wait for Postgres to insert all the data. But now I have my Postgres container already waiting to accept connections. All right, now let me get back to my code. So to read data frame from a remote database, the structure is pretty standard. So I'm going to say Spark read, and I'm going to specify format JDBC, and then I'm going to pass in a bunch of options. So I'm going to say option, and there are some standard options that you need to specify in order for the JDBC driver to work correctly. So I'm going to say driver, and this is the class name which will act as the driver for connecting to that JDBC Postgres. So we have org Postgres SQL driver with a capital D. In practice, when you connect to another kind of database, you will use another kind of JDBC driver. All major databases will have a JDBC driver for you. It should be easy to download. Now, we need to specify an option for the database URL. And in our case, we have JDBC :Postgres, Postgres SQL, :// and we have localhost at 5432. This is the port where Postgres was set up. And we have / the database name, which in our case is rock the JVM. Another two mandatory flags are user and password. So user in our case is Docker, and password is also Docker. So you need to pass in two option calls here, password Docker. And finally, you need to pass in the table name. So you need to pass in option with db table. This is the flag name, db table. And our table that we want to import is the employees table, which is public.employees. And after we specified all these flags, all we're left to do is say load. We don't need any path because we specified everything else prior. And let's name this data frame employees df. And let's go ahead and show employees df just to test the connection to the database. So I'm going to say employees df.show. Let me go ahead and run this. A few seconds to start and connect to the database. And we have our first 20 employees fetched from the Postgres database. So you see here that even though connecting to a database and migrating all of its data might seem a little scary, once you specify the right options and the right flags here, you probably notice that it's not actually that scary or that hard. Cool. So you saw JSONs, CSVs, Parquet, text files, and reading data from a remote database. Now, just to practice what we've learned in the past good few minutes, let's go ahead and write our small exercise. And for this exercise, I want you to read the movies data frame. You've read it earlier. It's this movies.json file. I want you to read it as a data frame, and I want you to write it as three different things. As a tab separated values file. So this is a CSV with separator as a tab. I want you to write it as a snappy Parquet. And I also want you to write the movies data frame as a table in the Postgres database in a table called public.movies. Okay, so this should be pretty straightforward. You should read the data frame and then write it in these formats. So I will give you a second to write this exercise yourself, and I will get back with a solution. All right, so I'm pretty sure you did the exercise perfectly. So let me go ahead and provide a small solution for it. So first of all, let's read the movies data frame. So movies df will be Spark read JSON at source main resources data movies.json. Now I don't need to specify any other flags because infer schema is already true and I don't need any other flag. All right, so this is the movies data frame. Now I want to write it in a tab separated values file, so TSV. I will need moviesdf.write, and I need to specify the format to be CSV. I need to mention the header to be true. So option, header, and true, just to maintain the column names. And then I will specify another option for separator, which in my case is going to be a \t. So this is the tab separated values. And then I'm going to say save to source main resources data movies.csv. So this is how we can save the movies data frame into a tab separated values, which is, in fact is a CSV with the tab as a separator. Cool. We don't need any other fancy options here for movies df. Let's go create the Parquet file as well. And this should be the easiest. So movies df dot save dot write dot save, and I'm going to put in source main resources data and then movies.parquet. We mentioned earlier that saving doesn't require any format if you want to save in Parquet, because Parquet is the default storage format for data frames. You also don't need to specify any compression because the default compression is snappy. Cool, so this is how we can save in Parquet, and then save to database. We can simply say moviesdf.write, and then we can say option, not option, but format JDBC, and then specify all these options over here. In good practice, you might want to save these values as reusable variables or reusable values. So let me go ahead and extract them. So I'm gonna take this guy and say val driver equals this guy and pass in here the URL and then pass it here, the username, and pass in here, not Docker, but user. Take the password, pass it back, and then reuse all these values inside. So I'm going to say dot option, and we have driver as driver, and then the URL, and then the username and password. You can simply copy these guys from above. So I'm going to say here, password. And then the only difference to the previous JDBC interaction is the table name. So I'm going to say option db table. In our case will be public.movies. And instead of doing load, I'm going to do a save. All right. So let me go ahead and run this application to make sure that I've written correct code. So give it a few seconds to execute and write the previous data frames and so on and so forth. And we have a bunch of things. So we have movies.csv, which is a CSV file with tab separated values. And notice that the empty string signifies a null here. Okay, and all the values are tab separated, there's no comma, and so on and so forth. So this is basically a tab separated values file. And then movies parquet, we see a snappy parquet file. We can't really read it, but if you can read in between the lines, we can see some Terry Gilliam, Steven Spielberg in between these encoded parquet values over here. So I'm going to trust that the parquet file was correctly written. And as for my database, I'm going to go to my terminal and go to my Spark Essentials folder in another window in my terminal while the Postgres Docker container is still running. And I'm going to execute ./psql shell script, which will automatically connect to my Postgres container. And I'm going to try to select star from public.movies. And we have values here in the movies table, which means that I've correctly written my data frame to my Postgres database. So there you have it, folks. You're now masters of reading and writing data frames to any data source in any format. I'm Daniel, and I will be waiting for you in the next lecture. Yo, welcome back. I'm Daniel, and in this lecture we will start to learn how to process data frames with columns and expressions. So the goal of this lecture is to have you guys operate on data frame columns and obtain new data frames by what is called projections of data frames. And after that, I'm going to teach you how to operate with data frames with complex expressions and obtain new data frames as results. Good. So we are back to our project, and for this lecture, obviously, I'm going to create a new application. So under part 2 data frames, I'm going to say new Scala class. I'm going to name this columns and expressions, make it an object as usual, and extends app. And let's do our boilerplates. So we will create the Spark session. So Spark equals Spark session.builder. And then we will give this an app name, and I'm going to name this df columns and expressions, and then configure it with master local. So spark.master local, and then get or create. So this is our Spark session, and we will read our first data frame from the resources folder, I'm actually going to read the same cars.json we've been operating with earlier. So I'm going to say val carsdf equals spark read, and then with option infer schema true, because I don't want to bother with the schema. And then I'm going to say .json at the path source main resources data cars.json. And let's show it. So carsdf.show, just to make sure we've loaded our data frame correctly. Give this guy a couple of seconds to warm up and start the Spark application. All right, so we have our data frame over here, so we've read it correctly. Now, on this data frame, I'm going to show you first how to create columns. So columns are special objects that will allow you to obtain new data frames out of some source data frames by processing the values inside. So I'm going to create my first column. And I'm going to write carsdf.call, and the call method takes an argument, which is the column name that we want to obtain. For this example, the column name out of the data frame, and the result of this call is a column object. This column object will be used in select expressions, which I'm going to show you in a second. So this column thing is just a plain JVM object that has no data inside. We can obtain new data out of the original data frame by selecting this column. So we can say, let's call this car names df as carsdf.select. And with the select method, you can pass in one of these column objects. So I'm going to pass in, for example, first column. And when you do select, you obtain a new data frame out of the original data frame, because we mentioned earlier that data frames are immutable. So if we do car names df.show, we will see just the car names to the console. So I'm going to run this application again, give it a few seconds. And we see here a data frame with a single column called name, and we have the names of all the cars here. We're just showing the top 20 rows. So this is how we obtain new data frames out of the original data frames by using this select method. The technical term for selecting in this fashion is called projection. So we are projecting the data frame into a new data frame which contains less data, that is, fewer columns. You might have heard the term projection from the theory of databases if you've operated with SQL before. Now, the select method that we've called here is one of the most powerful methods that you're probably going to ever use in Spark. We are going to use select a lot in this course and in the following courses in this series, and you're surely going to use select a lot in your real life as well. And right off the bat, I want to show you various ways that you can select columns in data frames, because you're going to use that a lot. So we can pass in as many columns as we want. So for example, I can do carsdf.select with carsdf.call, and you can pass in a column name. And you can pass in as many of these as you want. So I can duplicate this and I can add acceleration, for example. So you can pass in as many of these column objects as you like, but specifying carsdf.call is tedious in practice because data frames can have a large amount of columns. So we can do simply call, but this is a method from a package called org apache spark SQL functions. The plain call method does the same thing as carsdf.call. There is a small difference between these two, but it's not worth pointing it out yet, but we'll talk about it when we discuss joins. So right now you can consider carsdf.call and plain call to do the same thing. There is another method that does the same thing, that's called column, which is more explicit. So you can use, for example, column weight in pounds. So col and column do the exact same thing, and there are fancier ways of selecting columns. And for that, we will need to import Spark implicits. So you can use Scala symbols, for example, single quote year, which returns a Scala symbol, which is auto-converted to column. So this is one way, one of the fancier ways. You can also do dollar and then double quotes in the same style as we do s-interpolated strings. And for example, I can write in horsepower. So this is a fancier interpolated string. Returns a column object. And finally, we can do expr. So the expr is a function in the same style as call and column. It needs to be imported here. And expr takes a string as an argument. For example, I can get in, what are some other columns? Let me go to cars.json. And we have, for example, origin. Let's take one of those. So expr origin is a powerful construct known as an expression. And in this case, returns just the origin column. So these are various ways that you can select parts of the data frame. And we've selected columns and expressions here. We'll talk about expressions a little bit later in this lecture. Now, another very common and very popular way of selecting columns in Spark is to just pass in a bunch of strings. So carsdf.select, and for example, I can do name and year. So these strings are column names, and this will return another df. Okay, now you cannot really interchange between these two. You can either pass in column objects and expressions, or you can pass in column names as strings. So use one of these two select methods. So what am I doing here? Assume we have a data frame where the columns brown and green in the picture are those that I want to select. You remember that data frames are actually split in partitions in between nodes in the cluster. So when I select two columns or any number of columns from a data frame, those columns are being selected on every partition on every node where the data frame resides. And after select, I will obtain a new data frame with those two columns that I wanted, and that will be reflected on every node in the cluster. This is an example of what we earlier called a narrow transformation. That means that every input partition in the original data frame has exactly one corresponding output partition in the resulting data frame. All right, back to our project. So selecting column names is the simplest version of expressions that we can use in Spark. Expressions are a powerful construct and will allow you to process data frames in almost any fashion that you like. Let's start with some very simple examples. So let's call the simplest expression as carsdf.call weight in lbs, the weight in pounds. So when you do carsdf.call, this returns a column object, which is a subtype of an expression. So this is basically the simplest expression. But after you obtain a simple expression, you can then chain it with various operators. Let me give you an example. Let's call this weight in kilograms expression. So let's assume we want to transform the original data frame with the weight in pounds expressed as weight in kilograms. So we can say carsdf.call weight. Let's pass in the right name here. So weight in pounds, and then slash 2.2, which is the approximate division factor from pounds to kilograms. Now, the result of this construct is, probably surprising, a column object. Now, this column object describes a transformation this time around, because every value in the weight in pounds column will be divided by 2.2. And the way that we can use this expression in a select statement is pretty simple. So we can say, let's call this val cars with weights df as carsdf.select and let's pass in the call name, the call weight in pounds, and this weight in kilograms expression. And if we show this data frame, let's call cars with weights df.show. Let me collapse the menu because I don't need it. We will see a 3-column data frame with names and weights. So we have a data frame with name, weights in pounds, and weights in pounds divided by 2.2. This is the name of the 3rd column, which you can set by putting a dot as weight in kilograms after this weight in kilograms expression. So you can call the as method and you can give the resulting column a name. And if you run this again, the name of the 3rd column will be weight in kilograms. So this is how we can do expressions in Spark. Notice that. So we have weight in kilograms as the 3rd column. Alternatively, instead of creating these complex expressions, because in practice you will create very, very complex expressions, you can use the expr method that we saw earlier. And in expr, you can pass in a SQL-like string. So for example, you can pass in weight in LBS, which is the column name of the original data frame, and then space divided by 2.2 directly in the string. So if you select something like this, you will obtain a new derived column. So you can say as, let's call this weight in kilograms 2. And if you run the application again, you will create a 4-column data frame this time around, and the weight in kilograms and weight in kilograms 2 are going to have very similar, if not identical, results. Now, expr has different implementations from the division operator on columns. So this is why you see these values slightly different. Now, in practice, we see lots of transformations on data frames where we have an original data frame, then .select, and inside we have lots and lots of expr calls, just expr calls. And for this particular use case, the very interesting select expr method was invented. So we can say val cars with select expr weights. Let's call this like this. And then df equals cars df dot select expr. And you can pass in a number of expressions inside. So you can pass in name, you can pass in weight in LBS, the pounds, and then you can pass in weight in pounds divided by 2.2, again, directly in the string. So this is a shorthand method for selecting and then expr name, expr weight in pounds divided by 2.2. Instead of doing that, you can simply call select expr. You can pass in as many expressions inside here as you want. So these are expressions, and throughout the entire course, we will see lots and lots of these expressions. Let's do some data frame processing now that you know what expressions and columns are. The first thing that I want to show you is adding a new column to an existing data frame, and obviously obtaining a new data frame as a result. So I'm going to say carsdf.withColumn. This will extend the original data frame with an additional column. So the withColumn method takes a column name. Let's call this weight in kilograms 3, and then you can pass an expression. So for example, you can say call weight in pounds and then divided by 2.2. So this is an expression that will be associated to this weight in kilograms 3, and the result of that is going to be a new data frame. So let's call this cars with kilograms 3 df. Okay, so this is how you can formally add a new column. You can also rename an existing column. So this is adding a column. Let's call it renaming a column. So let's call this cars with column renamed equals carsdf dot with column renamed, and you'll take the existing name and the desired name as arguments for this method. So you can say weight in lbs, and then weight in pounds as the desired column name. lbs, I never understood the abbreviation for pounds, but who am I to judge? Now, speaking of desired column names, you might be tempted to use space or hyphens in column names, but when you use these column names in expressions, because expressions are arbitrarily large, they can contain spaces or hyphens, and in this way you can break the expression compiler. So for escaping characters like that, you need backticks. So you can say cars with column renamed dot select expr, and if you want to select this desired column name, you need to put in backticks inside the strings. So you can say weight in pounds with backticks like that. So when you're doing expressions, be sure to escape reserved characters like spaces or hyphens inside backticks, because the compiler will then figure out that this weight in pounds is a single symbol, and it will treat it as one. Finally, on the column topic, if you want to remove a column, there is the drop method. So we can say cars with column renamed dot drop. Let's call cylinders and displacement if you want no engine info, for example. So if you want to remove one or more columns, you need to do drop. So these are pretty straightforward. Let's talk about filtering. Filtering is a big deal in databases and in data science and in big data as well. So there are various ways that you can do filters. For example, you can do carsdf dot filter, and let's assume you want the cars that are not originally from the USA. So you can say call origin, and the not equal operator for a column object is equal, not equal. So this is the operator that you want for not equals, because not equals, this guy would have come into conflict with the standard Scala operator. So you can say call origin not equal to USA. So let's call European cars df. So this is how you can do that. So you can do filter, or you can do where, which does the exact same thing. So let's call this European cars df2 equals carsdf dot where. There's also a version, or there are multiple versions of filtering and where with expression strings. So for example, you might want to see American cars df equals carsdf dot filter, or where it does the same thing, and you can pass in an expression string. For example, you can say origin equals USA, and for USA, the string, you need to pass in single quotes in the expression string. So the expression here needs to be USA like this. And if you want to do the equals filter on column expressions, so in this kind of construct, you will need to do triple equals like this, so as not to be mistaken for the double equals operator, which is standard Scala equality. Finally, on the filter side, I want to show you how to chain filters. So let's call American powerful cars df. As I'm going to copy this guy, and I'm going to use the triple equals for American cars. And after you've done a filter, you can do as many other filters as you want. So you can do filter, or where, and you can say column horsepower is bigger than 150. And you can chain as many of these as you want, but there are nicer ways to do that. For example, I can copy this around, and instead of doing many filters, I'm actually going to combine two expressions, two filters like this, into a single filter by using the AND operator. So I'm going to put in some parentheses in between these small filters, and I will chain them with the AND method. So when you do AND, let's call this df2 so that the compiler doesn't yell at me. When you do AND, you can chain multiple filters like this into a single bigger filter. And I've put in some parentheses to be extra explicit, but you can remove them because the AND method is infix. And this looks more like natural language. Also, you can use an expression strings. So if I want to copy, for example, this guy, let's call this American Powerful Cars df3 as cars filter origin equals USA, and you can pass in as many filters inside the string as you want. And you can say and horsepower bigger than 150 inside the same string. Let's do a couple of last things. So one of them is unioning. That is adding more rows. So we've discussed about columns and expressions, but we haven't discussed how to enhance the data frame with more rows. And inside the source main resources data folder, I have a morecars.json data frame with 2 additional cars that I would like to add to our original data frame. So let's create an additional data frame. Let's call this morecars df as Spark read option infer schema true, and then do JSON with source main resources data morecars.json. And let's append this morecars.json data frame to the original data frame. And let's obtain an all cars df. And to stitch together 2 data frames, you would do the union call. So you can say carsdf.union morecarsdf. Data frames in question have the same schema. So that's unioning. And finally, I want to do distinct, which is pretty simple. For example, I can say all countries df as carsdf.select. Let's call origin. So just select all the origin countries of the cars and then do distinct. So if I do all countries df.show, we should be seeing, I think, 2 lines in the resulting data frame. But I have an exception here. Why is that? Well, we have a data type mismatch. So we have origin equals USA and horsepower big integer. Okay, that's me being stupid and not actually finishing up the filter here. Horsepower should be bigger than 150 in the final filter. So if we run this again, it should work. A couple of seconds to run. And we have 3 origins here: Europe, USA, and Japan. All right, we've learned a gazillion data frame transformations. So join me in the next video where I'm going to give you some exercises. All right, we're back to columns and expressions, and as I promised, I'm going to give you some exercises. Let's do this. All right, we're back to our project. So let's write some exercises. So I want you to go ahead and read the movies data frame. So we have here lots and lots of movies, and I want you to do some things with the movies data frame. So I'm going to get back to my code, and I'm going to ask you to read the movies data frame and select 2 columns of your choice. For example, you can create another data frame with a title and I think with the release date. But you can select any columns that you like. All right, so select 2 columns of your choice. This is pretty easy. Then I would like you to create a new data frame by summing up all the gross profits of the movies. So you see here that every movie has a bunch of values here for profits or for box office income. So for every movie you have US gross, worldwide gross, and US DVD sales. I want you to go ahead and sum up these 3 values, so US gross, worldwide gross, and US DVD sales, as the total profit of the movie. So I want you to create another column summing up the total profit of the movie, as in US gross plus worldwide gross plus DVD sales. All right. And third, I want you to select all the comedy movies, because you see here in the movies data frame, we have a genre, the major genre. I want you to select all the movies that are comedies in the major genre. For example, this movie is a comedy, and the movie's name is 1941. Okay, so I want you to select all comedies, but with a twist. I want you to select all the good comedies, and every movie has a rating by either Rotten Tomatoes or IMDb, and we have here IMDb rating 5.6 and Rotten Tomatoes 33. So I want you to select, for example, all the comedy movies with IMDb rating above 6.5 or 6. So let's consider the IMDb rating 6 to be, I don't know, at least mediocre comedy movies. I don't know about you, but this is probably what you would do in real life if you had to pick a movie that you could watch in 2 or 3 hours. If I had 2 or 3 hours and I didn't have the data, I would spend 2 hours watching trailers, and by the time I decide, then I don't have time to finish the movie. But if I had the data, I would probably do a select. So these are the exercises that I want you to write. Now, for every one of these exercises, use as many versions as possible. What do I mean by that? You saw earlier that there are a bunch of ways that you can select columns and expressions and that kind of stuff. For example, if you want to chain filters, if you want to select columns, or if you want to select column derivatives, you have lots of ways to do that. So for every one of those exercises, try to be creative and try to express them in as many ways as you can. All right, so as usual, I will give you a break, so pause the video now, and after the break, I will come up with a solution, and in the meantime, I will expect you to have written the exercise. All right, so you probably found that the exercises are not really that hard, and if you're creative, you probably found at least 3, 4, 5 ways of writing each. So I'm just going to pick a few. Let's do the first exercise. Read the movies data frame and select 2 columns of our choice. Let's read the movies data frame first. Let's call this val movies df as spark read option infer schema true, and then JSON source main resources data movies.json. Let me collapse the menu so we have access to more code, and let's show it. So movies.df.show. I'm actually going to kill all the other shows because that will process all our data frames over here, and I don't want the application to take that much time. So I'm going to run this just to make sure that our movies data frame is read correctly. A couple of seconds to compile, a couple of seconds to run. All right, so we have here our movies data frame, which is quite wide in that it has a large number of columns. So it probably is really easy to select 2 columns. So let's select, for example, the movies and the release dates. So movies release df as movies.df.select, and you can either pass in 2 strings. For example, you can pass in the title. If I remember correctly, that's the name of the column. So this is the title, and let's take the release date. Okay, so release underscore date with a capital D. So this is option number 1. Option number 2 would be to select with these column objects, and there are various ways of doing that. So I'm going to say val movies release df2 as movies.df.select. And I can pass in one of these column objects obtained in various forms. So I can say, for example, movies.df.call title. And for the other column, I can say call release date. And if I want to select some other columns, I can do $string, and then I can get the major genre. And I can do expra with, for example, IMDb rating. Okay, so these are some of the possibilities that you can use, and you can use any combinations of these in a select call. Or you can use select expert, for example. So you can say val movies release df3 as movies df dot select expert. And in select expert, you can pass in the column names. So title and release date. Okay, so these are some of the possibilities that you can use for exercise 1. All right, let's go to exercise number 2. I'm going to collapse the application so that we have more screen estate. So exercise number 2. Now, we need to create another column summing up the total profit of the movies. That is US gross plus worldwide gross plus DVD sales. Well, you can do select with the following options. So you can say val movies profit df as movies df dot select, and I'm going to use some column options, some column objects. So I can say call title and then call, what is that, US gross, and then call worldwide gross, and then US DVD sales. So that's US underscore DVD underscore sales. I think that's the spelling of it. So let me go back. Okay, so it's US DVD sales with a capital S. US DVD sales, and then you can say call US gross. Actually, I'm going to copy all of them. So I'm going to say column US gross plus column worldwide gross plus column US DVD sales. All right, so this is our final column as total profit. And if you want to give it a name, you can put these guys in parentheses and you can say as total gross. Okay, so this is how you can compute the other column here. So let's do a small test here. So if I say movies profit df.show, and let me run this. Give it a few seconds. Shouldn't take too long. So notice we have here US DVD sales null and total gross is null. So you will see lots of nulls here. We will see later in the course how we can treat nulls. There's a dedicated section on that in the course. So we will be able to treat nulls later. Now, because most of our values, most of our non-null values are US gross plus worldwide gross, I'm actually going to ignore US DVD sales because that will pollute my data. So I'm going to kill that out. That doesn't impact the technique of this exercise. So let me run this again. Okay, so we have here worldwide gross plus US gross is total gross. So if you look at these numbers, 146,083, that's basically doubled, and that's 292,166. Although these values do seem suspicious to me that the US gross and worldwide gross are identical, so I'm not really relying on the cleanliness or the accuracy of the data. I'm actually focusing on the technique of the exercise. So as long as the US gross plus worldwide gross is the total gross, I'm fine with that. Okay, so this was one option. Second option would be to do select expert, for example. So you can say val movies profit df2 as movies df dot select expert, and inside you can put in the column names. So that's title, US growth, US gross, and then worldwide gross, and then you can put in US gross plus worldwide gross. And if you want to give this guy a name, you can put in as total gross. So you can put in as total gross, and the column name here will be total gross. So this will be an equivalent way of writing this data frame. So if I say movies profit df2.show, we will see something very, very similar. A few seconds. So we have the same values over here. So this is movies profit df2, and the third major option that I wanted to show you, let's call this movies profit df3, as movies df dot select, and I can pass in title, US gross, and worldwide gross. So this would be your intermediate data frame, which you can save in another value if you wanted to reuse it, and you can add with column. So you can add a column called total gross, and you can put in an expression here. So you can say call US gross plus call worldwide gross. Okay, so this will do exactly the same thing. So that was basically exercise number 2. I think you can combine a couple of these techniques, but these are the major ones. Now, for exercise number 3, where you want to select all comedies with IMDb rating above 6, you will do something like this. Let's say comedies, or at least mediocre comedies df, as movies df dot select, and I'm going to select just the title and the IMDb rating. So it's IMDb underscore rating with a capital R. And I'm going to select where, and I'm going to put in the condition, the column with the name, I think it's called major genre. I need to confirm that. So yeah, it's major genre. So major underscore genre equals, that is triple equals comedy. Okay, and column with IMDb rating is bigger than 6. Okay, so this is one option. So notice this construct, movies df select a couple of columns where a condition. Expect to be almost everyone taking this course. You'll see that this syntax, this construct, looks very similar to SQL. That is, select a bunch of columns from a data frame where a condition, right? And we will explore Spark SQL later in the course. So this is one option. Of course, instead of where, you can use a filter. Alternatively, you can use more where clauses or more filters. So you can say, for example, val at least mediocre comedies df. I'm just going to say comedies df because that's too long. So comedies df2 as movies df dot select, and I will pass in the title and the IMDb rating, and I'm going to put in 2 where clauses instead of 1. So where call major genre triple equals comedy, and I'm going to put in another where clause. So where call IMDb rating is bigger than 6. Or you can say val comedies df3, you can say movies df dot select, and you can pick the title and the IMDb rating again, and you can pass in a single string. So where, and you can say major underscore genre equals single quotes comedy, and IMDb rating is equal or bigger than 6. All right, so this is a single string in the where clause. Obviously, you can combine these techniques. For example, when you select the columns, instead of passing the column names, you can use the column objects. You can use select expert. You can do lots and lots of combinations in between these constructs. So just to test this, let's pick comedies df3 and then show to see what kind of at least mediocre comedies we have in our data frame. I hope we have at least a few seconds to run, and we have quite a bunch. I Married a Stranger, 24/7, The Four Seasons, and we have a few quite good ones, The Casino Royale and A Christmas Story. Good. So besides solving a nice exercise with data frames, you also have some movie recommendations from this course, which in and of itself should probably save your life. All right. So I hope the exercises were useful and fun, but there is a lot more where that came from. So join me in the next lecture. All right, we are back, and in this video we will do some more complex data processing on data frames, and I will be talking about aggregations and grouping. So the goal of this lecture is to teach you how to do aggregations and statistics on your various data frames and how to group them. So in our project, I'm going to start a new application for this lecture. So under part 2 data frames, I'm going to create a new application. I'm going to name this aggregations. Make it an object as usual and extends app. I will collapse my file explorer and I'll do my boilerplate. So I'm going to create my Spark session as Spark session.builder.appName, and I will name this aggregations and grouping .config, and I will configure Spark master to local. And then I'm going to do get or create. Cool. Now, for this lecture, we will be working with the movies data frame. So under resources data, we will be working with the movies data frame. We've worked with it before, so we'll say val moviesdf as Spark read option infer schema true, and then JSON at source main resources data and then movies.json. Cool. Now, I will be teaching you how to do various data processing on this movies data frame by doing aggregations and grouping. And the first aggregation that I'm going to show you is counting. So, for example, I can select all the different genres in the movies JSON. So if I go to movies.json, you see here that we have lots of major genres. You have musical, drama, comedy, and so on and so forth. We will be counting how many different genres we have in our data frame. So I'm going to say val genres count df as moviesdf dot select. So we'll be using select a lot throughout the entire course and in particular throughout this lecture. In this case, we'll be using select to do aggregations, and I'm going to be using a function called count. So I'm going to say count with column major genre. Now we don't have either of these functions. They all belong to the package org, Apache, Spark, SQL functions, and I will be importing count and column. So if I do genres count df.show, we should be seeing a data frame with a single row with a single column called count of major genre, and it should show the number of genres in our original data frame. So I'm going to run this application, give it a few seconds to compile, and then another few seconds to run. Spark used to be a lot slower than this. Okay, so we have a single data frame with a single row. Count of major genre, we have 2926. That's quite a lot of genres. This number, 2,926, are all the values in the major genre column that are not nulls. So all the values except null. Alternative ways of expressing this is to use select expr. So you can say moviesdf.select expr, and in the string you can say count of major genre, which does the same thing. So these two constructs are equivalent. but they count the values inside a single column. If you want to count all the rows in the data frame, you can say moviesdf.select, and you can call the count method on a string, and you can say count star. When you do count star, this will count all the rows and will include nulls. So if I do moviesdf select count star and then I do a show, just to prove how this works, you will see the number of rows in the original data frame. So you will see something like, so it's 3,201, which is the number of rows in this entire data frame. Look at that, okay? So when you do count star, this will automatically include nulls as well. When you do count with a single column, it will exclude nulls. So this is counting all. There are also versions for counting distinct values. So you can say, for example, moviesdf.select, and inside you can call in another function called countDistinct, which takes another column object. So you can say call major genre. And obviously you need to import this, so you need to put countDistinct inside this import as well. So if you're using quite a lot of functions, you can do org Apache Spark SQL functions and then put an underscore there. Okay, so if we do moviesdf select countDistinct and then I do a show, you will see the number of truly distinct genres in our data frame. Few seconds, and then we will see count distinct major genre, and we have 12 unique genres in our data frame. So this is much more realistic. Now, when you want to do quick data analyses on really big data frames, there are approximate versions. For example, you can say moviesdf.select, and there is a function called approx count distinct with the underscore notation, and you can put in a call major genre. And approx count distinct is obviously a part of the functions package, which I'm going to import with an underscore. So this function is very useful for very big data frames on which you want to do quick data analyses, because approx count distinct will not scan the entire data frame row by row, but rather it will get you an approximate row count. Cool, so that's counting. There are also statistic functions for min and max. I'm just going to show you the min, so I'm going to say val, let's call this min rating, df as moviesdf dot select, and obviously there is a min function, which is part of the functions package, and you can pass in a column here. So call, for example, IMDb rating. Alternatively, you can say moviesdf.select expra, and in the string you can pass in the min function. So you can say min IMDb rating. And this guide does exactly what you would expect. It will return a single row data frame with a single column, which contains a single number denoting the minimum of the IMDb rating in the data frame. Max does exactly the same thing. There's also sum and average. So in much the same fashion, you can say moviesdf.select, and you can pass in sum of, for example, US gross, to figure out the total size of the movie industry in the United States. And you can pass in the column with US gross. And in much the same style, you can say moviesdf.select expra, and you can say sum of US gross. Again, this is pretty self-explanatory. It sums up all the values on this column. We also have functions for average, for example, moviesdf.select, and the function is avg with call, let's say, Rotten Tomatoes rating. I think that's the name of the column. Let's get to the data frame. Yeah, so it's rotten underscore tomatoes underscore rating. Okay, and of course, moviesdf.select expra. And I can pass in average AVG with Rotten Tomatoes rating. Awesome. Now, for data science, it's useful to have standard deviation and means. So for example, you can say moviesdf.select, and we have functions for that. We can have mean of Rotten Tomatoes rating. This is a column name that I'm going to pass and call explicitly. And the standard deviation has a function called stddev with call Rotten Tomatoes rating. And if you know data science, mean means average, and standard deviation means how close or how far the different values of the Rotten Tomatoes ratings are to the mean. So a lower standard deviation will mean that the values are closer to the average, and a higher standard deviation will mean that the values are more spread out over a wider spectrum. So if I run this application again, actually I'm going to stop it. I'm actually going to show this data frame just to give you an idea of what these values are and what they mean. Give it a few seconds. And we have the average of Rotten Tomatoes rating, which is the same as mean, is 54. So this is the average rating, 54 from 0 to 100. And the standard deviation is 28, which means that values are pretty spread out in the 0 to 100 interval. So this means that this data frame has both very poor movies and very good movies at the same time. If the standard deviation had a smaller value here, for example, I don't know, 4 or 5, then most of the movies would have been pretty mediocre around the rating 54. Cool, so these are the most common data aggregations that you are going to use most of the time in your Spark day-to-day. Let's talk about grouping. There are various ways of doing grouping in data frames, and it's a very popular operation. Now, let's say, for example, that we want to not only count the number of distinct genres in our data frame, but rather how to compute how many movies we have for each of those genres. And the way that we do that, let's call this count by genre df, is to say moviesdf dot group by, and you can pass in a number of columns here. I'm going to group by a single column, major genre. And after you call group by, then you do an aggregation. So when you call group by, you obtain what is called a relational grouped data set. So you're not working with a data frame just yet. After you call group by, you need to call an aggregation on this group by. So you need to call count. So this construct is the equivalent of the SQL select count star from whatever data frame we have, so from moviesdf, group by major genre, for those of you who know SQL. So this is the equivalent SQL code written in data frame speak in Spark. We'll see later in the course that this exact SQL statement will work in Spark when we do Spark SQL, but more on that later in the course. So when you want to write actual Spark code, you would do something like this. You would call the group by method on a data frame. You would pass in a number of columns, and then you would do one aggregation on that grouped data frame. So if I do count by genre df.show, and I'm going to remove the previous show and run the application again, notice what we get. We get some execution, and at the very, very end, we get a count by major genre. So for every one of the major genres, we get a count of the movies. And notice we have nulls here as well. So group by also includes null. Let's do another example. Let's say we want to compute the average IMDb rating by genre. So we can say average rating by genre df as moviesdf dot group by the same column, so call major genre, and then you can call another aggregation function. So notice we have quite a lot of these aggregations. So I can do average, and I can pass in a column name or many column names. So I can do average by IMDb rating. And this will compute the average rating per genre. So this is one way of doing grouping. This is just another example. An alternative way of doing grouping is by calling the AGG, the aggregation function. So I can obtain the same thing. So let's call this aggregations by genre as movies df. Again, dot group by that column, so call major genre, and then do AGG for aggregate. And inside you can pass in multiple aggregations. So I can say count star, and you can give this guy an alias, a column name. So as, let's say, n movies. And then you can add more aggregations. For example, average of IMDb rating as average rating. So this construct computes both aggregations, so count star and average of IMDb rating, by genre in the same data frame. So this aggregation function is very powerful. Now, at the end of this call, you can also do an order by. And you can pass in a number of columns to order your data frame by. So I'm going to order by average rating, for example. So if I do aggregations by genre df show, let's see what we get. A few seconds for Spark to aggregate my data. All right, so we have the combined data frame, which combines the count of the movies and the average rating for every genre. And notice that our data frame is sorted in ascending order by average rating. So this is how we can do grouping on data frames. Now, if you're okay with it, I want to give you some exercises. First, I want you to sum up all the profits of all the movies in the data frame. This should be pretty easy. Then I want you to count how many distinct directors we have in the data frame. Now I want you to show the mean and standard deviation of US gross revenue for the movies. And try to interpret the results. And finally, I would like you to find out or compute the average IMDb rating and the average US gross revenue per director to find out which director in this movie's data frame is a best-selling director at the box office and which director actually has a good IMDb rating. That is, which director actually makes good movies. So for this exercise, it would be worth doing a sort by either IMDb rating or the gross revenue. All right, cool. So as always, I will give you a break. So pause the video now and try to solve these exercises, and I will come back with a solution. All right, so I hope you did that. Let's take the exercises in turn, as always. So we need to sum up all the profits of all the movies in the data frame. All the profits means if I go to the movies JSON data frame, we have US gross, worldwide gross, and US DVD sales for every single movie in the data frame. So here's how we can do that. Obviously, you can be creative and instead of select, you can use select expra or vice versa. So I'm going to do select. So I'm going to say movies df dot select, and I will do call US gross plus call worldwide gross with a single R plus call US DVD sales. All right. And I will put this expression in parentheses and I will give the resulting column a name, and I'm going to say as total gross. Okay, so when I do select like that, I obtain a data frame with a single column, which computes the total profit for every single movie. And I will need to do another select after that. So I'm going to say select, and I will do sum of the total gross. Okay, and after that, I can do directly a show. So let me run this and let's see what we get. A few seconds for Spark to aggregate my data. So sum of the total gross is this huge number, which is thousands, millions, billions. So it's $139 billion. Quite a chunk of money. Select Expra instead of my construct, but I'm going to stick with this one. Now, for the second exercise, how many distinct directors we have? Well, we can say moviesdf dot select, and we can say count distinct, and I can pass in a column for, I think it's called, what is the name of the column? So we have running time, distributor, major genre, creative type, director. Cool. So we can say count distinct with column director. And then I can do a show. So let's run this guy around and see what we get. We shouldn't have more than 3,000 different directors. At least we have that. So we have 550 distinct directors. Fine. Cool. We will see the average profits and the average IMDb rating for all of them. Cool. Let's do the third exercise. Show the mean and standard deviation of US gross revenue for the movies. I'm going to say moviesdf.select, and I'm going to do mean for the column US gross and standard deviation for the same US gross. Now I'm going to do a show. And let's try to see what the values are, and let's try to interpret them. Spark needs to aggregate my data. Come on, Spark. You're pretty fast. We have an exception. Why do we have an exception? So we have cannot resolve US gross 1. Oh yeah, because I've misspelled my column. Silly me. Let's run the application again. Come on, Spark. Yeah, kind of moves a little faster. Good. So we have average for US gross, we have 4.4 E7. E7 means times 10 to the 7th. So we have $44 million, the average. And the standard deviation is even bigger than that. So we have 6.2 E7, so $60 million. So the standard deviation is actually bigger than the average. So what does that mean? Well, it means that we have lots of movies that are doing very poorly in box office because the average is very low, and the standard deviation being very high compared to the average means that we also have quite a lot of movies that are doing very well. So that was our third exercise. Let's do the fourth. So we wanted the average IMDb rating and the average US gross revenue per director. So we need to group by director. Fine. So let's do moviesdf dot group by, and we will group by director. And then we need to do a bunch of aggregations. So I'm going to use the ag function. We need two aggregations. We need a average of IMDb rating, and I'm going to say as average rating. And we need the total US gross profit, US gross revenue. So we can say sum of US gross as total profit, or total US gross. And then I'm going to say order by average rating, and then I'm going to do a show at the end. So let's run this again. Compiled blazing fast. Let's see how blazing fast Spark is, because it needs to process a bunch of data. So 1, 2, 3. Okay, so we have a number of things here. We have average rating nulls for a lot of these directors, and then we have values in ascending order. So I'm going to show you a little trick. When you want to order by descending, you can pass in a column object, and you can call the desc method. So desc means descending, and there are a bunch of versions for descending and for ascending as well. So you have descending with nulls last and descending with nulls first. We're interested in descending nulls last. We're not really interested in nulls. So I'm going to call average rating dot desc nulls last. And I'm going to rerun the application because that's the more interesting result, I think, that we are after. So let's give Spark some time to execute, and it should be done like now. Cool. So we have a bunch of directors in descending order by their average IMDb rating. And we have Katie Long, Ben Affleck, quite a good actor and director as well. So we have quite a bunch of directors ordered by their average rating in descending order. And notice that their US gross profit is actually not correlated at all with the average IMDb rating, which is pretty true in real life. So congratulations on doing the exercises. It's pretty important. Now, there is something else that I want to tell you before I wrap up this video. The aggregations and groupings that we did in this video are wide transformations. You probably remember from earlier in the course that we discussed about narrow and wide transformations. What do I mean by that? If we have a data frame that looks like this is actually partitioned in between the Spark nodes that are executing the jobs. Now, you can consider the data frame as these chunks distributed in the cluster. Now, if we went to do a grouping, for example, let me color the rows in these data frames. And for example, the blue rows signify the rows in the data frame belonging to the blue group. So when you want to do a group by, you'll eventually end up with something like this, which may or may not have fewer or a larger number of partitions. This is called a wide transformation, when one or more input partitions contribute to one or more output partitions. So something like this. The arrows that you see in the diagram correspond to operations known as shuffles. Shuffles means that data is being moved in between different nodes in the Spark cluster. Shuffling is an expensive operation. So if you have data pipelines that you also want to be really fast, be very careful when you're using data aggregations and grouping. Often it is the case, not always, but often it's the case that it would be best to do data aggregations and grouping at the end of your processing. So a really important topic that you are going to use a lot in your Spark life. I'm Daniel, and I will be waiting for you in the next lecture. Welcome! We are back for another important data frame transformation topic, and this time we're going to be talking about joins. So you probably saw joins before in databases, for example. Joins combine data from multiple data frames or multiple tables in database terms. What I mean by that is that one or more columns from table 1 is compared with one or more columns from table 2. Table 1 is called the left data frame, and table 2 is called the right data frame. And the rows that satisfy your condition are going to be combined, and the rows that do not are going to be discarded. In Spark, joins are wide transformations. You probably remember wide transformations. In order to compute a join, Spark scans the entire data frames across the entire cluster, and so data is going to be moved around between various Spark nodes. So this involves shuffling, which are expensive for performance. But you don't need to be concerned with that at this moment. Let's get to the code. So here I am in our project over here, and as usual, I'm going to create a new application for this lecture. So I'm going to do new Scala class. I'm going to name this joins. I'm going to make it an object and extends app. And I'm going to do my boilerplate. So I'm going to say val spark equals spark session.builder app name, and I'm going to give the name joins, and then I'm going to configure Spark master to be local. I'm going to say get or create. Now I'm going to read 3 data frames from the data folder here. So we will have bands, which describes rock and roll bands or heavy metal bands, and then guitar players, who are some of the most famous guitarists of all time, and then some famous guitar models. And I will load all 3 data frames and I will do various joins on them. So I'm going to get back to my joins Scala application, and I will load the 3 data frames. So I'm going to say val guitars df as spark read option infer schema true, and then JSON, let me put the option here, and then JSON source main resources data guitars.json. I'm going to copy this for guitarists df, and I'm going to load the file guitar players.json, and then val bands df as this guy, and loading the bands file. Cool. Now, having loaded our data frames, let's do a join on them. So let me open the bands data frame and the guitar players data frame, and notice that each guitar player has an ID, a name, guitars, like favorite guitars that they play, in an array, and the ID of the band. And in bands JSON, we have the ID of the band, the name of the band, the hometown, and the year they started. Now, I would like to join the guitarists, that is the guitar players data frame, with the band's data frame based on the band ID. That is, each guitarist has a band ID that is associated to them. So I'm going to go to my joins application, and I'm going to write my first join. So I'm going to say the following. I'm going to define a new data frame called, let's say, guitarists bands df as guitarists df dot join. And in the join method, you will specify the other data frame that you want to join with, in my case, bands df. And you need a join expression. The join expression will be the condition by which Spark will compare the rows in between the 2 data frames, and it will combine the rows together. So inside the join expression, I will use, I'm actually going to collapse the menu so that we have more screen estate. So I'm going to say bands df, and I'm going to say guitarists df dot call, and the band column for the guitarist, so I'm going to say band, should triple equal bands df dot call id. You probably joined various tables when you worked with databases. So in our case, we want to join the guitarist's data frame based on the band ID. So the band value, that is the value associated to the band column, should equal the ID column in the other data frame. So here, the expression here is going to be guitarists.df.callBand should equal bands.df.callID. And the third optional argument to the join method is the join type, which I'm going to discuss in a second. And the default value for this third argument is inner. The inner join will take all the rows from the first data frame, all the rows from the second data frame, and it will compare them based on this expression. All the rows that match this condition will be combined. Everything else will be discarded. So let's see this in action. So I'm going to say guitarists bands df.show. And I'm going to run this application. A few seconds to compile, another few seconds to run. The data frames are really small, so Spark shouldn't take too long. So notice we have a combined data frame here that contains both the information from the guitarist's data frame and the information from the band's data frame. So we have all the columns from guitarists and all the columns from bands. And the rows were combined. Everything else, that is, everything that did not satisfy this condition, was discarded. This is an inner join. So notice that this resulting data frame has 3 rows, whereas we have a missing guitarist, which is, for example, Eric Clapton, which didn't have any band associated to him. He had band ID 2, which is not in the band's data frame. And also we have a missing band, in this case the Beatles, because we don't have any guitarists in our guitarist data frame. When you're writing big data applications, you might want to reuse some of your expressions, which is why it's often a good practice to extract these conditions as values. Let's call this join condition. I'm going to put in join condition here. So these were inner joins. There are other types of joins, for example, outer joins. And I'm going to start with left outer joins. So I'm going to say, for example, guitarists df dot join with bands df, the join condition, and another value here for the join type, which is left underscore outer. A left outer join will contain everything in the inner join plus all the rows in the left table. In my case, the left table is the data frame on which you're calling the join method. So this is the left data frame, this is the right data frame. So the left outer join will contain everything in the inner join plus all the rows in the left table with nulls where the data is missing. Let me show you how that's going to work. So if I do a show here, let's see how that shows up in the console. So we will have here Eric Clapton, the guitarist. So notice that Eric Clapton is now included, but in the columns corresponding to the right data frame, we put in nulls because there was no matching row in the other data frame. So this is a left outer join. There's also a right outer join, which means everything in the inner join plus all the rows in the right table. So in this case, we will see the missing band here, which was the Beatles, and nulls in the place for the guitarist data. So if I copy the guitarist's df and then I do the join with the band's df with the same join condition and I do right outer, you will see something else. Let me stop the application because I haven't done a show. So let me do a show now. And you will see nulls in the left table this time. So notice that we have the data from the inner join plus all the rows in the right data frame, which in my case is the band's df, with nulls in the corresponding other table for a guitarist. All right, so this was the right outer join. Then we have a full outer join, which is everything in the inner join plus all the rows in both tables. Let me show you. So I'm going to copy this expression, this construct, and for the join type, I'm going to use outer. And if I do that, we will see one additional row. So in the end, we'll get a data frame with 5 rows this time around. So look at that. We have a data frame with 5 rows. The first 3 rows are for the inner join. The 4th row is for the left outer join, and the 5th row is for the right outer join. So a full outer join contains everything the inner join, the left outer join, and the right outer join. So I hope this makes sense. This should probably feel familiar, especially if you've worked with any kind of SQL or databases before. There are other kinds of joins as well. So for example, there are so-called semi-joins. So you can do, for example, and I'm going to remove the shows here, guitarists.df.join bands.df join condition, and then I can say left underscore semi. If I do a left semi join, let me do a show, I will only see the rows in the left table, in the left data frame, in this case the guitarist data frame, for which there is a row in the bands.df satisfying this join condition. Let me show you what I mean. So if I run this again, I will see a data frame with 3 rows containing just the data in the first data frame, for which there is a key. There is a row in the bands.df satisfying this join condition. So it's as if I were to do an inner join, but cut out the data from the right data frame and still keep the data just from the left data frame. There is also the notion of an anti-join, which will only keep the rows in the left data frame for which there is no row in the right data frame satisfying the join condition. So let me show you what I mean. So I'm going to say guitarists.df.join left anti. Let me do a show. Let's wait a couple of seconds. The data frames are tiny. And we only have a single row in the first data frame for which there is no row in the right data frame satisfying this join condition. In my case, the error Clapton. So anti-joins basically give you back the missing rows from the left data frame. So let me write this down. So everything in the left data frame for which there is a row in the right data frame satisfying the condition. And for anti-joins, everything in the left data frame for which there is no row in the right data frame satisfying the condition. All right, so these are more join types that you will ever need in your Spark life. Most of the time, you're probably going to use inner joins, for which you don't even need to pass in this argument because it has the default value inner. Now, some things to bear in mind when you're doing joins. For example, in the inner join that we did, we joined with column band equals the bands.df column ID. If you noticed, both the bands data frame has a column ID and the guitarist's data frame has a column ID. And in the end, we get a data frame with 2 columns with the name ID. So for example, I can, if I do guitarists bands.df.select and I do ID and band, and then I do a show, Spark will crash because it will not know which column am I referring to by this identifier ID. So if I try to run this, Spark will crash. Let's prove this. And we have an exception here. That is because the column name is ambiguous. So reference ID is ambiguous, could be ID and ID, obviously. Cool. So this crashes. And I will put a column here. Now, how do we solve this? Well, there are a bunch of options. Well, we can rename the column on which we're joining. And we can say, for example, guitarists.df.join bands.df.with column renamed, and I can change the ID column of the bands. So ID, I can change it to band. So now I have a guitarist df with a column band and another data frame with a column band, and I can join it on the band column. So I can simply pass it as argument here, and Spark will know that this column band will match with this column band. Okay? And the band column will appear only once in the resulting data frame. So this is option 1. Option 2 is to drop the dupe column. So I can say guitarists bands.df, which is the joined data frame that I computed earlier. I can say drop, And then I need to pick one of the ID columns that I care about. For example, if I already have the band ID that I care about in the resulting data frame, I can get rid of bandsdf.callID. But this time, you will need to reference the ID column of the data frame that you wanted to drop, because otherwise, if you simply say call ID, then the Spark will simply get confused for the same reason. So you need bandsdf.callID. Now look at this construct. This sounds pretty weird. So I'm saying guitarist's bandsdf.drop, and then I'm calling the call method on another data frame. Isn't this weird? So the reason this works is because Spark maintains unique identifiers for all the columns it operates on. So what I'm essentially saying is, hey Spark, drop me from the guitarist's bandsdf the column with the unique identifier obtained from bandsdf. So Spark is not confused this time with regards to which ID column I'm referring to. If I had just said call ID, then Spark would not have known which column ID I'm referring to. But because I'm saying bandsdf.columnID, I'm also attaching the unique identifier to the column. And so Spark will know which column I'm referring to. So that was option 2. Option 3 is to rename the offending column and keep the data. So I can say, for example, val bands modifier data frame as bandsdf with column renamed, and I can rename their ID to, let's say, band ID or some unique name so that Spark is not confused. So I can then say guitarist'sdf.join, and I can join in with bands mod df with a very similar join condition. So I'm going to copy this guy. I'm going to say guitarist'sdf.columnBand equals bands mod df.callBandID. And this time, all the column names will be unique in the resulting data frame. But the drawback is that we still have duplicate data. So we have the band and the band ID containing the same data, which might not be what you want, which is why I'm keeping this option last. So this is one thing to bear in mind. The second thing to bear in mind is using complex types, which we will see later in the course, but I want to tease you a little bit on it. So if you go to guitar players, notice that one of the values, one of the columns actually is an array. So it's not a plain value, it's an array. So we can do joins using arrays. For example, I can do guitar players or guitarists df.join with guitars df. And because guitars df also has an ID column, I'm going to rename that. I'm going to use option 1 basically. I'm going to say with column renamed, I'm going to say ID with guitar ID. And instead of a join condition as this kind of construct, I'm going to use an expression. So I'm going to say expra. And in the string, I'm going to use a function called a array underscore contains. And as the first argument for this array contains, I'm going to pass in the guitars from the left data frame, and the, what have I done? And the guitar ID from the right data frame. Now, obviously, I need to import expra, so I'm going to say import org apache spark SQL functions dot expra. Okay, so this is how we can process data frames with complex types, and we can pass in any kind of expression here as a join condition. And in this case, I'm processing a complex type. We're going to discuss complex types in detail later in the course, but this is something else to bear in mind. You can use any kind of expression that you want as a join condition. So you're just learning a critical topic in Spark, and it's just as critical that you practice it with some exercises coming up in the next video. All right, welcome back. I hope you're ready for some exercises. So I hope this all makes sense. And if that makes sense, then of course, let me give you some exercises. And for this exercise, I would like to ask you to start your Docker container with the Postgres database so that you can read some data frames out of it and then do some joins and groups on them. So I will ask you to start your Docker container by doing docker compose up, but I already started my Docker container. So if you do docker ps, you will see your Docker container up and running. And if you do have your Docker container up and running, then do psql.shell so that you can connect to your database. And if you hit \dt, you will see all the tables in the database, including the movies that we wrote earlier in the course. And we have quite a bunch of tables describing employees, departments, salaries, and so on and so forth. Now, the first exercise that I would like you to write using joins is to show all employees and their max salary. Because if I do \d salaries, that is, I want to describe the table, the salaries table has the employee number, which is the employee unique identifier, the salary, which is the actual value, but this salary has a from date and a to date, meaning that the employee may have had a salary evolution in time. So I would like you to take the max salary for every employee. Obviously, every employee has an employee number, which is the primary key of this table. All right. Now, as for the second exercise, I would like you to show all employees who were never managers. What do I mean by that? In the database, we have a table called department manager. And if I try to describe department manager, we see we have a department number, an employee number, a from date, and a to date. I want you to find all the employees that do not figure in this table. Okay. Now, for third, I want you to find the job titles of the best paid 10 employees in the company. The job titles are fetched from another table, which is called titles. So the titles has an employee number, a title, a from date, and a to date. So this table basically records the entire career progression of every employee. And I will ask you to show the latest job title of every single employee that you find that are best paid. Okay? And you can find the most recent title by doing a max on the to date column. So these exercises that we have in this lecture might prove to be a little more difficult than the ones that we've done so far. And if you know databases, or if you know SQL, I would recommend you write the SQL statements first that would return you these results, and then try to translate that SQL into the data frame constructs that we've done in this lecture and in the rest of the course. And regardless if you know SQL or not, try to build each intermediate result step by step. So for example, show all employees at their max salary. Well, try to group the max salaries by employee number and then try to do a join between the employees and that intermediate data frame, just to give you an example. So as always, I will give you a break, and I hope you do as many of these exercises as you can. In any event, I will come back with a solution. All right, so these exercises are a little bit more difficult, but first let's try to read our data frames. So I'm going to go to data sources, and I'm going to shamelessly copy the code that we wrote for the employees data frame. I'm actually going to copy the settings for the database as well. And then I'm going to read the employees data frame, their salaries, I think we have department manager, and then the job titles. So let's do employees df. I'm actually going to create a small method. Let's call this read table, and this receives a table name as a string, and this returns a data frame. So I'm going to return Spark read format JDBC driver URL user password and then DB table, and I'm going to say public and then $table or table name. So I'm going to inject the argument right here in the table name for the database. So right now all I have to do is say read table with employees or salaries, and I should return a data frame. So let's say employees df as read table, and the name of the table is employees. Then we have salaries df as read table with salaries. Then we have department managers df as read table, and the table name is department managers, if I remember correctly, manager singular. Okay, and then we have the titles, so job titles df as read table with titles. Okay, so we have the titles table. Good, so we have the data frames. Now let's do something with them. Let's do exercise number 1. I'm actually going to give them numbers. Cool. So exercise number 1, show all employees and their max salary. As I gave you the hint earlier in the exercise statement, let's compute the max salary per employee number and then join that with the employees data frame. So I'm going to create another data frame. Let's say max salaries per employee number df as salaries df dot group by, and the column name is going to be employee number, and then I'm going to do a max with the column name, I think it's called salary. Yeah, this is the column name. So max for salary. So this is the data frame that I then want to join with my employees data frame. Okay, so I'm gonna say val employees salaries df as employees df dot join max salaries per employee number df, and the join condition is going to be employee number. So I'm joining by this column. If you remember, that's option 1 in our things to bear in mind, because both our data frames already have the employee number column, and this is the column that we want to join on. So I'm just going to simply pass it here. So let's do a show. So I'm going to say employees salaries df dot show. And hopefully I didn't do anything stupid. So I'm going to run this. Few seconds to compile, few seconds to run. It'll actually take a little bit more time to read all these tables from the Postgres containers, so it'll take a little while. But we have the data frame here. So we have the data for the employee, and we have the max salary for each. So this was exercise number 1. This is all the exercise number 1 asked. Just join the employees data frame with the max salary in the other table. All right, so that was exercise 1. Exercise 2 was asking to show all employees who were never managers. That's interesting. So we have the table called dept manager, the department manager. So if we describe the dept manager, this guy, we have the columns department number, employee number, and from date and to date. So the employees that were never managers should never occur in this table. So we will need to join the employees table, the employees data frame, with the dept manager data frame such that the employee number does not occur in the dept manager data frame. Well, what kind of join do we need to do so that the employee number does not occur in the right data frame? Well, there is a special kind of join, which is the anti-join. So we need to fetch everything in the employees data frame for which there is no entry in the department manager data frame, satisfying the condition. So we will need to do an anti-join. So let's call this employee never managers df as employees df dot join with the department managers df, and the condition is employees df dot column employee number triple equals dept managers df dot call employee number. All right, now the join type needs to be left anti, and that should be it. So let me put the arguments here so that we see them more clearly. So let me do an emp never managers df dot show. So we compile quicker. Let's give it a couple of seconds to run and to read the data frames from the container. And we have a bunch of employees. So emp no, birth name, first name, and so on and so forth. So let's just pick one for the sake of testing. So let's pick this guy, 11033. So let's try to search for it in the other table. So I'm gonna go to my Postgres database. So I'm gonna select star from dept manager, where employee number equals this guy. All right, 0 rows. So this guy, the 11033, does not occur in dept manager. So our join worked correctly. So the solution for exercise number 2 was a left anti-join. Now, exercise number 3. We want to find the most recent job title of the best paid 10 employees in the company. Okay, as with the first exercise, I'm going to take this by steps. So first of all, I'm going to create a data frame for the most recent job titles. So I'm going to say most recent job titles df as titles df dot group by the same employee number column and then max to date. Okay, so this is the most recent job titles data frame. Then I will need to get the best paid 10 employees in the company. Cool. So let's get the best paid employees df as employees salaries df, because I computed that in the prior exercise. I'm going to say order by, and I'm going to order by salary, and then I'm going to do a limit 10. When you do a limit 10, you take the first 10 rows of the data frame. And because this data frame is ordered, is sorted, I take the best paid 10 employees. Now, there is something that I need to fix here, because the column name in the employee salaries data frame is not called salary, it's called max salary or something like that. We'll fix that in a second. And finally, at the end, we will need to join best paid employees df with the most recent job titles df. So I'm going to say best paid jobs df as best paid employees df dot join most recent job titles df on employee number. So I'm going to say employee number. Now let's fix the salary thing, because the salary is not the column name in the max salaries per employees number df. So instead of dot max, I'm going to do an aggregation, and I'm going to use max salary as, let's call this max salary as the column name, so I can identify it with a name and then reuse it here, order by max salary. Now, the max function is not available yet because I need to import it. So with export, I'm going to use max as well. And my code should compile at this point. But I've written quite a bit of code, and it would be worth testing something. So I'm going to say best paid jobs df dot show. So let's try to run this and see if we get some decent results. Okay, I have a stack trace. So to date is not a numeric column. That's actually because the max method is actually implemented differently than the max function. So I'm going to use the aggregation as well. So I'm going to say ag max toDate, and this guy should work. Okay, so the previous expression didn't work because .max only works with numeric columns, whereas .ag and max works with date columns. This is a quirk in Spark. And also, I forgot to mention something. The order by orders ascending by max salary, so I get actually the lowest paid employees. So I'm going to order by column max salary dot desk. I'm going to import the call function as well. Cool, so I now get the best paid employees. Hopefully this works this time around. It'll take a bit of time because we have quite a bunch of data. We have, I think, 300,000 employees. So joining on such big data sets takes at least a couple of seconds. So notice here we have employee number, birth date, first date, last name, gender, hire date, max salary, and max toDate. Fine. Well, we need the max toDate, and we also need the job title. So we need the job title here by employee number. We need to pass in the title in the group by expression, because otherwise the title is lost and we only have the best paid employees but no job title. So let's do this again. A few more seconds and we should have, look at that, we have senior staff, we have staff, we have senior staff, and so on and so forth. So these are the best paid employees in the company. So congratulations on finishing the exercises. These were quite difficult and this was a pretty long lesson, but I promise it will be worth it. I'm Daniel and I will be waiting for you in the next video. Yo, welcome back. In this video, we will be exploring common Spark data types. Now, the goal of this video is to give you a comprehensive arsenal in working with various Spark data types. So some of the stuff in this lecture is probably not going to be new because you've already seen it before and used it, but I also have quite a few new tricks to show you. So let's see what this is about. Good, so we're back to our project, and because we've just started a new chapter, I'm going to create a new package under source main Scala. So right click new package, I'm gonna name this part 3 types and datasets. Now, under this part 3 package, I'm going to create a new Scala application. I'm gonna name this common types. Make it an object as usual and extends app. Awesome. Let's do our boilerplate. So val spark session dot builder app name common Spark types, and then let's configure Spark master to be local, and then get or create. Now, for this lecture, I'm going to read the movies data frame. So I'm going to say val movies df as Spark read option infer schema true, and then .json at source main resources data, and then movies JSON. So this is our data frame that we are going to operate on. Now, the first thing that I want to show you related to Spark data types is a common question. How do we insert normal values in a data frame? So this is a common question. Like, Daniel, I've just learned about data frames. I've just operated on my already made data frames, but how do I modify a data frame in that I want to add a certain value to a column? So adding a common value to a df. Well, actually not a common value, but rather a plain value. How do we do that? Well, we need a select. So we are going to see moviesdf.select, and let's select the column name or title for the movies. And we're going to use quite a few of the Spark functions, so let's just import the package entirely. So I'm going to say import org apache spark SQL functions, and then I'm going to import everything. All right, so I have the call function, and I'm going to add the plain value, let's say 47. In order to add the plain value 47, we will use the function called lit. And lit will add the plain value 47 as yet another column to the data frame. So here I have a data frame with two columns, the column title and the column with literal 47. Let's give this guy a name as plain value. So if I do a show, I will see the titles of the movies and the number 47 attached to every single row. Now, if I give this guy a few seconds to compile and another few seconds to run, this should run pretty quick. Look at that. So I have a data frame with two columns, the column title and the plain value, this is the name that I've given it, and the number 47 attached to every single row. This lit function will work regardless of what kind of value or what type of value you use. So this will work with numbers, it will work with strings, it will work with booleans, it will work with whatever you want. Okay, speaking of types, let's talk about booleans for a second. You know about booleans so far, they've been used for filtering. So we can say moviesdf.select, and we can select, for example, titles. And then we can pass in a filter, so where, and we can pass in a column major genre, triple equals drama. So you've seen this before. Instead of the triple equals, you can also use equal to, which does the same thing. Now, we saw earlier that these filters can be extracted and used as values. So if I cut this out and I create a drama filter as this expression, I can use the value here, where drama filter. Now, let's assume you also want a good rating filter as column IMDb rating should be bigger than 7.0. Now, you saw earlier in the course how we can combine multiple filters. So let's say you prefer good dramas. Let's call this preferred filter as drama filter and good rating filter. You can chain multiple filters here with and or. And when we discussed about filtering earlier in the course, you saw that you can use where or filters, you can use multiple filter calls, you can use this combined filter in the where clauses, and so on and so forth. So I'm going to put this here. But I also want to show you something else. This preferred filter over here is obviously an expression, so it can be attached to an additional column in the data frame. So you can say moviesdf.select, and you can select the column title, and you can put this preferred filter here as an additional column. This preferred filter will be an additional column to the data frame. You can give this guy a name as, let's call this good movie, which will obviously be evaluated to either true or false. So this will be a Boolean column in this resulting data frame. So if I show this for a second, let me cut this from here and put it in the last data frame and run this again, we will see lots of trues and falses in this resulting data frame. All right, so we have nulls and falses and maybe true sometimes, but what I wanted to tell you is that these filters can also be evaluated as values in a data frame. Now, having this new column be evaluated to either true or false in a resulting data frame, you can also do the following. Let me save this as a value. Let's say movies with goodness flags. Let me put a df suffix at the end. Now, once you have a data frame that looks like this, you can filter on the column itself. So let me show you. I can do movies with goodness flags df.filter or where, and I can put in the name of this column, good movie, and that's it. I'm essentially doing a where column good movie triple equals true. So this is essentially what I've done here. So if I do a show this time around, you will see only the good movies or the preferred movies by the filter that we wrote. All right, so we have our preferred movies over here. So you can essentially filter on the column name. Obviously, you can also use negations. So you can say movies with goodness flags where not column good movie. And this basically does the reverse. So that's with booleans. Let's talk about numbers. And fortunately or unfortunately, depending on how you want to see it, I don't have that many new things to show you about numbers because they're super easy to work with in Spark. So you know about the number types. For example, the float type as float type, the double type, integer type, and so on and so forth. So we have quite a number of numerical types in Spark. Now, numerical types can be used for mathematical calculations in between the columns in a data frame. So if I go to movies JSON, you see that every movie has, you probably remember this, every movie has an IMDb rating and a Rotten Tomatoes rating. But the Rotten Tomatoes rating is value in between 0 and 100, and IMDb is between 0 and 10. So if I wanted to do, for example, an average in between these two ratings, but normalized to values between, for example, 0 and 10, we would do some math calculations. For example, I would do Rotten Tomatoes divided by 10 plus IMDb and do an average in between these two. So I would go back to my application and I would say something like movies average ratings df as movies, select movies df, select, and I would do a column title. And in order to calculate the average rating, I would say something like column Rotten Tomatoes rating plus column IMDb rating, but I would divide the Rotten Tomatoes rating by 10 and I would add IMDb rating and then I would divide by 2. So notice that the math operators plus and division work with columns without any problems at all. But if the columns are not numerical, which is not our case here, then Spark will crash. So if you're doing math operators on non-numerical columns, Spark will throw an exception in your face. So let's put in some math operators here. Now, again, just for numerical columns, there are some interesting functionalities in Spark. For example, the correlation between columns. This is very useful for data science. So let's compute, for example, the correlation between the Rotten Tomatoes rating and the IMDb rating. The Pearson correlation coefficient, which is what I'm about to compute, is a number between -1 and 1. The closer you get to -1 or 1, the stronger correlation you have. If you get close to -1, then you have a negative correlation. That is, the more one variable increases, the more the other value decreases. If you get a correlation closer to 1, then these two values are closely correlated. If you get a value between -0.3 and 0.3, then the values are almost not correlated at all. So in order to compute the correlation, the Pearson correlation in between these two values, we would do something like println. So the correlation is a number that Spark will compute for us. moviesdf.stat.core. And we will put two column names here. And the column names are Rotten Tomatoes rating and IMDb rating. So core here is a single number that Spark will compute on the entire data frame. So core is an action. You remember the differences between an action and a transformation. A transformation is lazy, that is, Spark will not compute it unless it needs to, but an action will trigger the computation regardless of what else you do in the code. So let's go ahead and show this. Let me kill the other show in the data frame, and let's just print this number. So let's rerun the application again. A couple of seconds. And we have a correlation of 0.4259 whatever. So 0.4259 is actually a pretty low correlation between Rotten Tomatoes and IMDb. 0.425 is actually a meh correlation. So that's with numbers. Let's talk about strings. Also, so strings, right? Now, with strings, I'm actually going to operate on a different data frame. I'm actually going to load the cars data frame. So I'm going to say val carsdf as spark read option infer schema true, and then JSON source main resources data cars.json. Now, I don't know for the life of me why I opened the menu over here, because I already know where the data is, but forgive me. And I'm going to show you a few data processing techniques on strings. For example, some of the more common functions for processing strings are capitalization related. So let me do carsdf, for example, select, and I will use initCap. InitCap will capitalize the first letter of every word contained in the respective column. So I'm going to say column name. If I go to cars.json, you'll see that the names of every car are in lowercase. So for Torino, everything is lowercase, but I want to capitalize the first letter of every word. And I would use initCap for that. So if I did a show, you would see all the names of the cars capitalized on the first letter. So look at that. So this is one of the more common functions. We have capitalization. And we have initCap, we have lower, and we have upper for to lowercase and uppercase for strings. Another very commonly used function for strings is contains. So for example, I can say carsdf select, and I can say select star. I can select all cars where column name dot contains, let's say Volkswagen. So you can use the contains method on the column object. So if you wanted to select all Volkswagens in our cars.json, you would use something like contains. However, there are some cars over here that would not be matched by the Volkswagen contains call. For example, we have VW. VW is obviously shorthand for Volkswagen. So you would use something like either contains Volkswagen or contains VW. But if you wanted to select multiple cars, then you would need to chain all these filters, which is why the more powerful version of contains is to do regex. Wait, did I say regex? Should I say regex? Whatever, regex, depending on which religion you're in, I'm referring to the same thing, right? Regular expressions. So I can do the following. I can define a regex or regex string as Volkswagen or VW. You probably saw regexes before, and this bar here means an OR operator in the regex grammar. And then I can say carsdf.select, and I can select the column name and regex p extract. So I'm going to use this function over here, and I'm going to pass in the column name, and then the regex string. And then I also need to pass in the ID of the matched sequence in case I have any. And I'm only interested in the first sequence, so I'm going to pass in the index 0. Let's show this just to see what we get. Come on, Spark. All right, so we have a bunch of things here. We have regex p extract here. We don't have any values for it, so this is basically empty. But if we do a where clause, and let's name this column as regex extract, and let's put in the condition where regex extract, actually column regex extract, is not equal to the empty string. And let's do a show again. All right, so let me rerun this. Come on, Spark. All right, so we have the actual string that was extracted by the function. So if in practice you wanted to simply extract all the Volkswagens in your car's data frame, you would simply do something like regex p extract and then filter on the regex extract column not equal to the empty string, and then maybe drop the regex extract column because it's not really useful for the data. So let's name this guy VWDF. So this is one of the regex functions that I wanted to show you. This is one of the two most common use cases for regexes. The other common use case is replacing. So I'm going to show you carsDF select, and I'm going to pass in the column name. And instead of regex p extract, I'm going to use regex p replace. And I'm going to pass in the same input column, the column name, the same regex string, and the third argument, which is the string that I want to replace the regex with. So I'm going to say, for example, people's car. And obviously this function is also an expression, so I'm going to give this column, this additional column, the alias regex replace. And let's do a show, just to give you an idea of how the data frame would look like. All right. So what happened here, I didn't really filter for the Volkswagens, so I'm actually using the wrong data frame. So let's use the VWDF, because we've already done the job of filtering Volkswagens. I want to show you how the Volkswagens will actually get changed to people's cars. So look at that. We have Volkswagens and we have people's car 1131, people's car Dasher, people's car Rabbit, and so on and so forth. So I hope everything makes sense, because in this case, I want to give you an exercise. Cool. So I want you to filter the car's DF, the car's data frame, by a list of car names, much like we did with Volkswagen, but this time on a list of car names, like Volkswagen, Mercedes-Benz, and so on and so forth. The problem is that you don't have the list of car names in advance, but rather you would have to call a method, which will be given to you as an API. So somebody gives you an API call, like def get car names, which returns a list of strings, and you don't have the implementation of this method. But once you get the car names, I would like you to construct a filter on the car's data frame that will obtain the cars with the name contained in this list, no matter what this list contains. So filter the car's data frame by a list of car names obtained by an API call. All right, so once you get the car names, I would like you to construct a complex filter. So this is the moment where I'm going to give you a break. pause the video, try to construct a complex filter that will select all the cars with the names contained in this list, and then I will come back with a solution. Alright, so hopefully this exercise wasn't too hard, especially with regexes, which is what I'm going to start with. So first, let's get the get car names out of the way. Let's get a list of some car names. Let's say Volkswagen, then Mercedes, Benz, and let's do also Ford. There are lots of Fords in the data frame. Now, let's construct a regex out of all these car names. So I'm going to say val complex regex. Given that our cars are all lowercase, I'm also going to lowercase all these car names. I'm going to say get car names dot map. I'm going to put into lowercase here. And then I'm going to combine them in a single string separated by this bar. And I'm going to use the makeString function. Okay, so complex regex will basically say Volkswagen bar Mercedes Benz bar Ford. Okay, now all I have to do is filter on my original data frame where this complex regex matches something. So I'm going to shamelessly copy what I did with the Volkswagen. So I'm going to say carsdf select column name, regex extract column name and this complex regex this time around, and with the same conditions. And then I'm going to do a show. All right. So let me go ahead and run this. Let me kill the other shows in the other data frames, and let's run the application. This shouldn't be too hard. Okay, so we have the names of the cars that match our complex regex. So we have Fords, we have Volkswagens. I didn't see any Mercedes over there, but I don't doubt they actually are there. So this is what variant number 1. So version 1 with regex. Version 2 is probably more complicated with contains, because for every single car name, we will have to do a contains filter and then combine them all. So let's create a car name filters list as get car names dot map to lowercase. And for every car name, I'm going to create a filter. I'm going to say the column name in the data frame should contain the name. All right, so I get the car names, I map them to lowercase, and for every car name, I create a new filter such that the column name in the data frame contains the car name in question. So right now I have a list of filters. All right, so a list of columns. Now, I need to combine them into one, which is the more complicated part of this version. So I'm going to say val big filter as car name filters, and I will use a fold. Now, when you start a fold, you will need an initial value, and I'm going to start with the filter false. The filter false is the literal false. You probably remember lit from the beginning of the lecture. So I start with the literal false, and then I combine the filters as I go. And once I have a combined filter and a new car name filter, then I will need to do an OR between these two. So I'm going to say combined filter or new car name filter. So this is how I obtained a huge filter based on these car names. And all I have to do is to say carsdf.filter big filter, and then I can do a show. Let me kill the other show, and let's print whatever we have. All right, so we have the data frame here. Now, I'm not selecting any particular columns, so I'm printing all the columns, but I'm only filtering on the car names. And notice that this data frame only contains Fords, Volkswagens, and so on and so forth. I'm sure it also contains Mercedes-Benz, but this preview only has 20 rows. Now, this version of the exercise was probably a little bit more complicated, particularly in this fold over here, especially if you haven't done too much functional programming. But whatever version of the exercise you did solve by yourself, I am proud of you if you did it. Alright, so your Spark arsenal in processing Spark data types is a little bit fuller now. I'll be waiting for you in the next video. Alright, welcome back. In this video, we will continue what we started in the earlier lecture, and we will systematically deconstruct and explore advanced Spark data types, including dates, structs, and arrays. Let's do this. Good, we're back in the project. Let's do our boilerplate. So under the part 3 package, let's create a new application. Let's call this complex types. Make it an object, extends app. Let's initialize our Spark session. So val Spark equals Spark session builder, and then app name. Let's give this the name complex data types. Let's configure Spark master to be local, and then get or create. Now, let me start by reading the movies data frame. So let's call this movies df as Spark read option infer schema true, and then JSON at source main resources data and movies JSON. Now, I'm going to start talking about dates first. Now, if I go to movies JSON, notice that many of the movies, actually all of the movies, but some have null, all of the movies have a column called release date, which has a date in a very unusual format. So we have the day, the month, and the year in 2 digits. So we saw earlier in the course how we can parse the dates into the data frame directly by enforcing a schema. Now, a more interesting problem is, what do you do when you want to operate on dates, but your data frame already reads the dates as strings? For example, if somebody in your team reads the data frame with option infer schema true, and you still want to operate on dates. So this is the subject of what I'm about to show you. So we can say, for example, movies df dot select, and let's select the column title. And in order to use the column function, we need to import the package. So import org Apache Spark SQL functions. Okay, and let's use the function called toDate. The toDate receives a column, which in our case is called release date, and the format in which you want to parse the dates. So we have day dash month. So we have 3 letters for month. We have, where is it? It's right over here. So we have 2 letters for day, 3 letters for month, and 2 digits for year. So we have dash YY. Now let's give this guy a name as actual release. And let's do a show. Let's run this application. Give it a couple of seconds to compile, another couple of seconds to run, because we've only just starting to process the data frame. So notice we have the actual release in a different format. We have the actual year, the actual month, and the actual day. So this is how you can convert a string column to a date column. And you probably remember the date type and the timestamp type in Spark. We discussed about them earlier in the course. Now, let's add another column. Let's call this with column. And I will add the column called today as current date. So current date returns today, the day that this function is being called. You can also add with column called right now as current timestamp. So current timestamp will return a timestamp that is up to second precision. When you have two dates in your data frame, you can do various operations on them. For example, let's compute the movie age in years. So that is the number of years between the current date and the release date. So we can say with column, let's call this movie age, as date diff, which takes two arguments, the bigger date and the smaller date. The bigger date is the column that we called today, and the column that we called actual release, but not as strings, but rather as columns. So column today and column actual release. The date diff function returns the number of days in between these two dates. So we'll naturally need to divide this by 365 to return the number of years for the movie age. So we've computed quite a lot. So toDate, just to recap, toDate does conversion, current date returns today, current timestamp returns the second, and date diff returns obviously date differences. So let's do a show. So let's run this again. Okay, so we have the actual release, we have today, we have right now, and the movie age in years. Now, very interestingly, we have a negative movie age, which is negative 0.92. That is because we have 2020 as the release date. Now, this looks like a quirk in the data, but if we go to movies.json, let's search for the over the hill to the poorhouse. So this is the movie that has the release date in the future, and it's actually in 17th of September 20. Now, when Spark tries to parse this date, the year 20 is either 1920 or 2020. Now, because the Spark version that I'm using 2.4.3 also has support for next year, so I'm recording in 2019, and it will have support for 2020, the parser prefers the year 2020 as the result for this date. So just bear in mind when you're parsing dates that look like this. Okay, now I want to show you something that's pretty important, and it might bite you in the neck, in the back, when dealing with dates in practice. So let's save the movies df with the parsed dates as movies with release dates. And then let us do movies with release dates dot with column and so on and so forth. Now, I want to show you something. If Spark fails to parse a date like this, so when the toDate function fails to parse a date on this format, Spark will not actually crash, but it will rather return null for that cell. So let me show you something. If I do movies with release dates dot select, and I'm going to use select star, where the column actual release dot is null, and I'm using the is null function self-explanatory, where the value for this column is null. We're going to deal with nulls in a future lecture. You will see that this data frame that I'm showing right over here is not empty. So we have quite a bunch of movies where the actual release is null. Let's say 55 days at Peking. Let's go back to the movies.json. And let's look for 55 days at Peking. 55 days at Peking has a release date in 1963-01-01. So this is basically a different format for the dates. Now, if you see this in real life, this is infuriating. So we have some dates in one format and some dates in another format. Now, sadly, this occurs in real life because when people fill in some dates, they fill in whatever strikes their fancy. So when you see something like this in practice and you see nulls for your parsed dates, don't get discouraged and try to figure out if you have mixed formats for your dates. All right. Now, for processing dates, we used date diffs, but you also have a range of other functions. For example, you have date add and date sub, which can add a number of days or subtract a number of days from a date. Now, this is what I wanted to show you on dates, so I'm going to give you a small exercise. The first exercise is more like a question. How do we deal with changing formats in our days? So how do we deal with multiple formats? This is more like a question for you to think about. And secondly, I want you to read the stocks data frame and parse the dates correctly. So this is pretty simple. The stocks data frame is obviously under source main resources data, and we have the stocks CSV. And notice that the dates here are also in a weird non-standard format. So we have month, day, and year. So I want you to parse these dates correctly. I will give you a short break, so pause the video now, try to think of the first exercise and solve the second, and I will come back with a solution. All right, so how did you do? Let's talk about the first exercise. So how do we deal with multiple date formats? Well, a solution that always got me out of trouble was to parse the data frame multiple times and parse it with all the formats that I could identify in the data frame. So right now we have two formats with day-month-year and then the format year-month-day. So I would parse the data frame multiple times, then union the small dfs. This is the painstaking task of data integration and data cleaning. And like it or not, when you're doing big data, you will have to do some of this stuff in real life. Now, obviously, this solution has some trade-offs because if your data set is really, really big, then parsing the data frame multiple times is not really feasible. So an alternative would be to simply ignore the format that is not really relevant. So for example, if you have 1% of the dates that are in an incorrect format, you can just simply discard them. Now, the second exercise should be a little bit easier. So I'm going to read the stocks data frame as Spark read format CSV, and then with the option to infer schema true, and then another option for header. So header true, and then load at source main resources data stocks.json. Now, from the stocks df, we need to parse the dates. So I'm going to say val stocks df with dates as stocks df. I'm going to use with column. And I'm going to name this actual date. And as the expression, I'm going to use the toDate function. So I'm going to say toDate, and I think the column is called date. Cool. So toDate with the column date, and the format is, let's get back. So we have 3 letters for month, at most 2 letters for day. We only have the day number 1, but we might as well have 2 letters for the day, and then 4 digits for the year. So we have the format month, 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 space, day, day, and space, y, 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 y. let's go ahead and show this. So I'm going to say stocks with df with dates show. Let me collapse my menu and let's run this. Come on, Spark, say yes. Oh no, we have a stack trace. So we have path does not exist, stocks.json, stocks.csv, Daniel, god damn it. You've parsed JSON too much in this course. Okay, so we have the data frame here. So notice the date is a string and the actual date is parsed in the standard format. All right, so we have this working. Let's move on to structures. So structures, or structs in Spark, are basically groups of columns aggregated into one. Let's say, for example, that I want to combine the US gross and worldwide gross values into a single column, which will have these two values as fields. So we can do that by saying moviesdf dot select, and I will put in column title, and then I'll call a function called struct, and I will put in the column US gross and column worldwide gross. And I will give this guy a name as profit. So if I show this, notice how it will look like. These two values, US gross and worldwide gross, will be grouped into a single column. So notice that they are stored in this array-like fashion. Then I can identify each field by selecting the column title and then the column profit, and then I can call the method getField, and I can identify the US gross, for example. So I'm going to say US gross, and obviously I can give this guy a name as well as US profit. Now if I do a show again, you will see the US profit actually extracted from that tuple over there. So structures are nothing else but tuples from a column that is composed of multiple values. All right, so I hope this is pretty self-explanatory, nothing too complicated. Let me kill all the shows so that Spark takes a little less time to process. So this is the version number 1 with column operators. The version number 2 is with expressions. So we can do with select expr, for example. So I can say moviesdf dot select expr and the column title, and the equivalent of this struct call, I can put US gross and worldwide gross inside a tuple-like structure as profit. All right, so in this SQL-like statement, we can group multiple columns in a tuple. And then I can say select expr, title, and then given a tuple, given a structure, I can say profit dot US gross. So you can identify the field by this dot notation. Now you're probably going to encounter structs a little less often, but you're probably going to encounter arrays a little more often. So let's do moviesdf dot select, and I'm going to select the column title, and I'm going to use the function called split, and I will pass in the column title and some separators in a regular expression. So I'm going to use space or a comma. These are the most common word separators. The split function will take the values inside this column title and will split them by either spaces or commas, and it will return an array of strings. Let's give this column a name. Let's call this as title words. Okay, and let's process this array with a variety of functions. So for example, I can do movies with words, select, and I'm going to add the column title, the expression title words indexed with 0. So notice this. So index 0 is the first element in this array. Now, obviously, my code doesn't compile because I haven't put a comma there. So title words 0 means the first word. Then we have size of column title words, which measures the number of elements in this array. And also, we can check if an array contains an element. So we can say array contains the column title words, and let's search, for example, for the word love. So these are some of the functions that you might encounter when working with arrays. So let's do a show. If you remember, array contains was used when we talked about joins earlier, when we did array contains with the guitarists and their favorite guitars. So look at this. So we have title words 0, which is the first word in the title. Size of title words, that is the number of elements in the array. And the array contains title words love. And notice we have our first movie, first love, last whatever. I think it's last love or something. And the function returns true here. Now, I'm not going to stress on structures and arrays too much because you are going to encounter them a little more rarely in real life. But it's really, really good to know. All right, so you're mastering advanced data types in Spark now. I'm Daniel, and I will be waiting for you in the next lecture. All right, good. Welcome back. In this video, I will teach you how to work with nulls. What do I mean by that? I will teach you how to avoid and overcome the absence of data and the presence of nulls in our data frames and various operations in working with nulls. Now, before I dive into the project, I want to make a note right off the bat. Remember when we enforced schemas when reading data frames? So we had code that looked something like this, where we defined a schema as one of those big struct types where we described every single column, and we read a data frame with that schema. Now, when we described non-nullable columns, so when we specified nullable equals false, the intuitive thinking would be that a nullable false means that the column may not ever have null values, but this is not actually the case. So when you say nullable false, non-nullable columns are not actually a constraint. They're just a marker for Spark to optimize for nulls. So what you're essentially saying is, hey Spark, I'm pretty confident that this column does not have null values, but if you do, this can lead to exceptions or data errors. That's why when we use infer schema true, Spark almost always has nullable true in the description of the columns. So be very careful when you use nullable false. Only use nullable false if you're pretty sure that the data may never have nulls. All right, so with this warning aside, let's go back to our project. So I'm here in my project, and as usual, I'm going to create a new application for this lecture. So under the part 3 package, go ahead and create a new Scala application, and I'm going to name this Managing Nulls. Obviously, make it an object and extends app. Now, let's do our boilerplate. So val spark equals spark session, builder, app name, managing nulls, with a config, spark master, local, and then get or create. Good. Now let's go ahead and read the movies data frame. So I'm going to say movies df as spark read option infer schema true. And then I'm going to say JSON at source main resources data movies JSON. Good, now let me collapse the Explorer and let's go to the movies JSON data frame. So movies JSON, and in this movies JSON data frame, notice that we have quite a lot of null values, but I'm particularly interested in the ratings of the movies. So we have Rotten Tomatoes rating and IMDb rating. And if you look at this data frame pretty closely, you'll find that most movies have at least one of these two ratings filled in. So they either have Rotten Tomatoes rating or the IMDb rating set. So there are quite few movies that have both ratings null. So I would like to create the following data frame. I'd like to create the data frame which contains the movie titles, and for each movie title I will select either the Rotten Tomatoes rating or the IMDb rating, whichever is not null. So I will do the following. I will do moviesdf.select, and I will select column title, which I need to make available by the import of the functions package. So I'm going to import org Apache Spark SQL functions everything. Okay, so I'm just selecting the title, and if I want to select the first non-null rating, either the Rotten Tomatoes rating or the IMDb rating, I will do the following. I will call a function called coalesce, and the coalesce function takes an arbitrary number of columns. So I will put in the column Rotten Tomatoes rating and the column IMDb rating. So what does this do? For every row in the data frame, the coalesce function will look at the Rotten Tomatoes rating first, and if it's not null, it will fill in that. If it is null, then it will take a look at IMDb rating. If it's not null, it will put that as the result. Now, obviously, these two are on different scales, so I will multiply the IMDb rating by 10 so that the ratings are between 0 and 100. And just to prove a point, I will actually copy these and I will select them too. So I will select the Rotten Tomatoes rating, I will select the IMDb rating, and I will also select this construct, which selects the first non-null value from all of these columns. So let me do a show here. And let's see how this looks like. Come on, compiler. Good. And then come on, Spark. Okay, so we have a bunch of values here. So we have Rotten Tomatoes rating null and IMDb rating 6.1. Because we have a coalesce between Rotten Tomatoes rating and 10 times IMDb rating, the final value is 61. Conversely, if we have Rotten Tomatoes rating 13 and IMDb rating null, the Rotten Tomatoes rating took priority because it was the first column that I put in here as argument to coalesce. So the final rating is 13. Also, if we have two non-null values, so 25 and 5.8, the Rotten Tomatoes rating still has priority because it's the first value that I put here as an argument. And obviously, if we have two nulls, then I don't have anything to compute, so we have null as a result. So this is a very quick, practical way to select the first non-null value out of a series of columns. Another very practical set of functions is checking for nulls. So I can do moviesdf.select, and I can select star where, and I can put in a condition, and I can say column Rotten Tomatoes rating, and I can add the is null or is not null method. So this one is pretty self-explanatory. I don't think this needs any proof. The next thing that I want to show you, I think you've probably seen this before, is nulls when ordering. So when you want to sort a data frame, you don't know right off the bat where nulls are supposed to sit. So for example, if you want to sort the movies by IMDb rating descending, where do you put the nulls? Do you put the nulls first, or do you want to put the nulls last? You don't know. So there are functions to do this sorting. You saw this before earlier in the course. So we do something like movies df, order by, column IMDb rating, and then you call the method desc nulls first or desc nulls last, depending on where you want your nulls to be. For example, I want desc nulls last. So this is also pretty self-explanatory, plus you've seen this before. Now I want to show you something null, how to remove or replace nulls. Let's talk about removing nulls. That is, removing rows where the values are null. So I'm going to say movies df dot select, and I will select the title and then the IMDb rating, and then I'm going to write the following. I'm going to say .na, which is an object containing methods. So I'm going to say .na.drop. So drop will remove all the rows in the data frame in which any value is null. This is not to be confused with moviesdf.drop. So the drop method on the data frame will drop columns from the data frame and it will return a new data frame. Now, because we're on the subject of this NA special object, we can use various methods on this NA object to replace nulls. For example, if I want to avoid nulls altogether and put in some defined values like 0, I can do that with the NA package. So I can say moviesdf.na.fill. So in particular, I'm going to use the following overloaded version of fill. So I'm going to say 0 for the columns IMDb rating and Rotten Tomatoes rating. So this overloaded version of fill takes the value that I want to fill the nulls with and the columns where I want to search for nulls. So just to prove the point, I can do a show. And if I run this application again, we'll see quite a bunch of zeros in our data frames. Yeah, so we have MPA rating, IMDb. So look at that. Look at IMDb and we see a few nulls. So IMDb rating 0, 0, 0, and so on and so forth. So all the nulls were replaced with this dedicated value. This is very useful when you want to do some data aggregation or processing and null values just won't cut it. All right, now let me remove the show and I'm going to show you another version of fill, which takes a more powerful set of arguments in which you can replace different columns with different values for nulls. So you can say, for example, moviesdf.na.fill, and you can take a map. And this map will take the column name as a string, of course, and you can associate the default value that you want to put for that column when Spark finds null in its place. So for example, let's say the IMDb rating starts from 0 and the Rotten Tomatoes rating starts from 10. So we can say Rotten Tomatoes rating arrow 10. And you can even add other types as well. For example, if you encounter nulls for director, you can associate unknown to that column. Alright, so I hope this makes sense. The fill method is heavily overloaded. Now, the final thing that I wanted to show you are some more complex operations. And I will describe each of those. So I'm going to say moviesdf.select expr. So I'm using select expr because the functions that I'm about to show you are not available in the data frame API. They're only available in the SQL. So I'm going to add the following. I'm going to add the title. I'm going to add the IMDb rating. I'm going to add the Rotten Tomatoes rating, and then I'm going to write the following expression. The first function is if null, written like this. If null is similar to coalesce. So I'm going to say Rotten Tomatoes rating and IMDb rating times 10. So this will return the same thing as coalesce. It will return Rotten Tomatoes if it's not null, otherwise it will return this expression. Another version that you might see in practice is NVL, just like that. And this takes the same arguments, and probably not surprising, does the same thing. Now I'm going to show you two more wacky functions that you'll see a little bit more rarely in real life, if at all. One of them is null if, and I'm going to pass the same arguments. And null if doesn't do the same thing as the two above, but rather it returns null if the two values are equal, which is pretty non-intuitive. And if the two values are not equal, then it will return the first value. In this case, the Rotten Tomatoes rating. So that was the first wacky function. The second wacky function is NVL2, which takes not 2 but 3 arguments. So I'm going to paste the first 2, and I'm going to add a third argument here. Now, this is probably easier to understand. If the first argument is not null, it will return the second argument, otherwise the third argument. Now, at this explanation, you may be wondering, Daniel, how the hell is this easy to understand? Well, it is easier to understand if you wrote some Scala equivalent code. So if I wrote something like, if the first is not null, then it returns second, else third. Now, this, I think, is easier to understand. So just for the final stretch of this lesson, let's name these columns as if null, as NVL, as null if, and as NVL2. And let's run this application and see how the data looks like. Well, I haven't put a show here, so let me do a show, and let's rerun this again. Sorry for wasting your 5 seconds. Okay, so look at that. We have a bunch of nulls and not nulls combinations, and you will see that the definitions here make sense. So let's check this first. We have non-null IMDb, null Rotten Tomatoes. If null returns IMDb times 10 because it's the same as coalesce. So if null and NVL should be identical no matter what. And you'll see here that they are. Now, with null if, we will check that the two values are equal. Now, because IMDb and Rotten Tomatoes are never equal, so even IMDb times 10 and Rotten Tomatoes are almost never equal, this null if should be the same as Rotten Tomatoes, because null if returns the first value if these two are not equal. So null if and Rotten Tomatoes should be identical. And if you scroll through the table, you'll see the values are identical. Now, for NVL2, this is basically a null check, a ternary operator. So we're checking for Rotten Tomatoes to be not null. Wherever it's not null, we return second, which is the IMDb rating. So let's look at this guy, for example, at Slam. So Rotten Tomatoes is not null, so it returns the second argument, IMDb rating times 10, which is 3.4 times 10, which is 34. Conversely, if Rotten Tomatoes is null, then we should see 0.0. So whenever we see Rotten Tomatoes null, we're seeing 0.0 on NVL2. Now, I know this is quite a lot to digest. If you've done a lot of SQL, you've probably seen these functions before. And if you're doing Spark SQL later in your day job or in whatever data processing you do, you'll probably need these functions as well. So who said nulls are easy? No, they're not. Nulls are frickin' hard, and now you're able to deal with them. I'm Daniel, and I will be waiting for you in the next lecture. Ho ho ho, welcome back. I'm Daniel, and in this video we will explore one of the most powerful and important concepts in this course, which is data sets. So datasets are essentially typed data frames. So in this course, we've been working with data frames which are distributed collections of rows. In this case, datasets are distributed collections of JVM objects, and we will see how to work with them shortly. So back to our favorite project. In part 3, types datasets, I'm going to create a new Scala application. I'm going to name this datasets. Make it an object as usual, extends, proper spelling Daniel, extends app, and then let's do our boilerplate. Val spark equals spark session, builder, app name, let's call this datasets, and then configure spark master to be local, and then get or create. Now, for the first example, I'm going to read a different data frame. I'm going to read this plain numbers.csv data frame. So notice that this numbers.csv is just a single column called numbers, and we have a bunch of randomly generated numbers that I created for this lecture. So we are going to read this numbers data frame. So I'm going to say val numbers df as spark read dot format CSV, and then let's specify the option to say header true, and then infer schema true. So option infer schema true, and then load from source main resources data numbers CSV. Awesome. Let's print the schema in this numbers df just to make sure we read the data frame correctly. So I'm going to say numbers df print schema, and let's run this application just to warm up the compiler. And we should see that the numbers data frame contains a single column called numbers. Okay, so we have numbers to be integer. Brilliant. So this data frame is nice and cute, but you noticed that this numbers df is essentially a distributed collection of numbers. So in order to process these numbers, we would have to only resort to the data frame methods and functions, which is kind of clunky. We would like, for example, to filter these numbers by a predicate of our choice. So being Scala programmers, we would probably like something like numbers df.filter underscore bigger than 100 or something like that. Right? But we cannot really do that. We have to resort to the data frame function. So we can say call numbers bigger than 100. We need to import the column method and so on and so forth. So how do we do that? Well, Spark allows us to add more type information to this data frame and transform it into a so-called data set, and allow us to process this data set with predicates of our choice, as if it were a distributed collection of JVM objects, which it is. So here's how we would go about it. I'm going to define a numbers ds for data set as numbers df dot as, and add the type information that I know this data frame is, which is int. Now, in order for this to work, we would need to create an implicit val int encoder. And I'm going to define it as encoders from org Apache Spark SQL dot Scala int. This encoders.scalaint is an expression that will return an encoder of int. An encoder of int has the capability of turning a row in a data frame into an int, which will be used in the distributed collection that I called a data set. And the result of this call is a data set of int. The data set is a type in org Apache Spark SQL. Now, this data set that we've obtained is essentially a distributed collection of ints, and you can operate on this data set as you would on any other collection. So you could say, for example, numbers ds.filter, and you can pass in any Scala predicate that you like, for example, underscore less than 100, and this works. So this is how we can convert a data frame to a data set. Now, this works fine for data frames with a single column, which had just plain values like numbers. But what do we do with things like cars, which have multiple columns and the objects are complex? Well, we would need to create a dataset of a different type. Each row will be a JVM object, and in this case, we will define a case class for cars. So let's create a dataset of a complex type. So in the first case, each row was an integer. Now each row is the description of a car. So we will need to define a case class for cars that will describe all the fields in this data frame. So I'm going to define a case class called car, and let's define the fields in this case class. Now, very importantly, the fields in this case class need to have the same names as the cars JSON. So I'm going to have name with a capital N, which is a string. Then we have miles per gallon, which I'm going to copy just like that because I fear misspelling it. So miles per gallon is going to be a double. Then we have cylinders, which I'm going to use as long. Then displacement, which is a long. Then we have horsepower, which is a long. Then we have weight in pounds, which is also a long. Then acceleration, which is a double. Then we have year, which is a date. And I'm going to use JavaSQL date. Then we have origin, which is a string. Let's go to the playground application and look at the schema over here. So we have miles per gallon, which is a double. Then we have displacement and acceleration is also a double. Okay, so displacement is also a double so that I don't mess up the schema. All right. Awesome. So we've defined our case class. Now let's read our very amazing cars.json data frame, which we've never, ever read before. So let's do val cars df as Spark, read option infer schema true, and that's JSON source main resources. And then we have cars JSON. Now, in this lecture, we're probably going to read a lot more datasets because I'm going to show you how to do joins on datasets, and we're probably going to need the guitars, guitar players, and the other datasets that we used in when we learned about joins on data frames. So I'm going to save your time and your code by extracting this expression into a method. So I'm going to define a method called read data frame from a file name as a string, and I'm going to return this badass boy. And when I do option and then JSON, I'm just going to inject the file name. Okay, so this will be an s-interpolated string. And then finally, when I do cars df, I'm going to read data frame for cars. Okay, or for cars JSON. Let me inject that. Okay, so cars JSON. All right, so we've read our data frame. Now, how do we convert that to a data set of cars? Well, we'll probably need an encoder for a car. So we will do something like implicit val, let's call this car encoder, as encoders dot product with type car. Now, this deserves some explanation. Encoders dot product will take as a type argument any type that extends the product type. Now, fortunately, all case classes extend the product type. This helps Spark identify which fields map to each column in a data frame. So encoders.product, in our case with car, will solve this problem. However, in real life big data applications, defining encoders for every single case class that we write might prove a little tedious and a little frustrating, which is why the very wise team at the Spark development wrapped all these implicits into Spark implicits. So when you do Spark implicits, so when you import Spark implicits, you'll automatically import all the encoders that you might ever want to use. So that when I later say val cars ds, I can then say cars df.as car. And the encoder will automatically be fetched from Spark implicits. Notice this import statement automatically colored up. So you probably identified some steps in order to read a dataset from a file. Step 1 is to define your type. Most of the time, you'll define a case class. Very, 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 very rarely will you need anything else than a case class. Then in step 2, then you need to read the data frame from the file. Step 3, you need to define an encoder, which most of the time will be solved by importing the implicits. All right, and then in step 4, you need to convert the data frame to dataset. All right, so once we have a dataset, we can operate on a dataset as we would on any other collection. For example, let me bring back the filter that I wrote earlier when I saw numbers ds filter underscore less than 100. So when you do something like this, the code will not only compile, but it will return a new data set of numbers. So you can then say show. So notice the data set also has the show method as we had on data frames as well. So if I ran this application, I would see all the numbers in my data set which are less than 100. But I have an exception here because path does not exist. Yes, because cars.json does not exist, I need to also add the data folder. God damn it, Daniel. I thought you already remembered the paths by heart. Okay. So we have numbers 76 and 37. This is totally expected because the numbers data frame contains 10,000 numbers between 0 and 1 million. And because I put in the filter to be less than 100, I'm expecting 0.1% of the numbers. So I'm expecting 1, maybe 2 numbers. So this is pretty normal. All right, you can also do filters or maps or flat maps or whatever you want on the data sets of your objects. So for example, you remember that the cars in our cars data frame have the names in all lowercase. If I wanted to uppercase all the names and return the data set containing just those car names, I would do something like carsds.map. And for every car, I would return car.name to uppercase. And this will be the car names ds. This will be a new data set of strings. So notice that the type information is kept at all times. So because you have a distributed collection, you have access to map, flat map, folds, reduce, filter, for comprehensions, anything you want. And besides the collection methods, datasets can also be shown. So we have car names ds.show. Now, we are in for a small surprise. Few seconds, and then we have a big, badass stack trace. What happened? Look at that. We have a null pointer exception because null value appeared in non-nullable field. So we have a miles per gallon field, which is null. This is because our car here specifies that the miles per gallon is necessarily a double. Now, when you say something like this, then Spark will enforce the constraint that the miles per gallon field in the data frame that you're parsing must not contain a null. So in order to allow for nulls in a dataset, you would use an option. So we have option double. Now I'm going to spare you the trouble of rerunning the application and see which other fields need to be an option. I'm going to add an option to horsepower. Good. So far we've familiarized ourselves with datasets, and by now we found that datasets are essentially typed data frames. They're distributed collections of JVM objects instead of distributed collections of untyped rows. Datasets are very powerful because we can very effectively use them when we want to maintain type information, because we can then process our JVM objects as if we had the collection of those objects locally on our computer, although the jobs actually run on the cluster, much like data frames. Datasets are also very useful when we want to maintain clear and concise code, especially in production-like applications. Datasets are also very effective when our filters and transformations that we want to apply become very complex, and they are hard to express in the df methods and functions or in SQL. So datasets are essentially a more powerful version of data frames because we also have types, and because we're Scala programmers, we love types. However, there's nothing for free in this world, and datasets come at a cost, especially in terms of performance. That is because all those transformations or filters are actually plain Scala objects that will be evaluated at runtime. That is after Spark has the chance to plan for the operations in advance. And so Spark will have to evaluate all the filters and transformations on a row-by-row basis, which is very, very slow. So if you want type safety, use datasets. If you want really fast performance, still use data frames. Good. So now that we understand the trade-offs between data frames and datasets, let me give you the first set of exercises. Because you can now operate on these datasets as if it were any other collection, I want you to go ahead and count how many cars we have. Then I would like you to count how many powerful cars we have. Powerful means horsepower bigger than 140. Okay? So I would like you to count how many cars with horsepower bigger than 140 we have in our data set. And finally, I would like you to compute the average horsepower for the entire data set. Okay, so this should be pretty easy if you've worked with other collections before. I will give you a small break, so pause the video now and try to work through these 3 exercises yourself, and I will come back with a solution. Awesome, so I hope you did these exercises because they are probably not that hard. So let me kill all these shows so that we don't pollute our precious standard output. Good, let's do the first exercise. So count how many cars we have. Well, we simply need to print line carsds.count. So count returns the number of rows in the cars data set. I'm not even going to run the application because this is pretty self-explanatory. We'll see them. We'll see this count when we run the application for the second or third exercise. So for the second exercise, how many powerful cars we have with horsepower bigger than 140? Well, if you've done any processing on any kind of collection before, you know that this implies a filter. So we would say something like cars ds.filter, and then for every car, we obtain its horsepower, and we want that to be bigger than 140. So cars ds filter, and then we have underscore horsepower bigger than 140. But we have a problem here because horsepower is an option. So we need to return, for example, 0 if we have a none inside. So we need to say underscore horsepower dot get or else 0, and then we should be good. You remember get or else returns this value if the option contains none. Okay, so we have cars ds filter horsepower get or else bigger than 140, and I asked you to count how many. So we will do a count again. And I want to print line this expression. Awesome. Now for the third exercise, I will expect you to do something like the following. cars ds dot map. So you need to sum up all the horsepowers in this data set. So for every car, you need to say underscore horsepower get or else 0. So right until this point, you have a data set of longs containing all the horsepowers in this data set. Now you need to sum them up, and you can do a reduce, and underscore plus underscore will sum them up. And then you need to divide by the total amount of cars that we have in our data set. So I'm going to extract that to a value. While cars count as carsds.count, let's print this guy out, and let's divide by this guy at the end. So in the end, we would need to print this big boy, and those will be our answers to the exercise. Let's go ahead and run the application. And I have a compiler error because value bigger than is not member of any val. This is because horsepower is a long, get or else 0. So horsepower is of type long, but in get or else I'm returning an int. We could solve that very easily by putting an L here. So 0L, that means the long with the value 0. So if we do with 0L, this should compile. All right, the compiler is happy now. So let's rerun the application again. Okay, so we have a bunch of numbers. The average horsepower is 103, then the count of the powerful cars is 81, and the count of the total cars is 406. This is pretty expected. Now, I want to show you something else, particularly in the context of the third exercise. If you want to compute the average horsepower for the entire dataset, you could also do something like carsds.select. So notice we have access to all the select methods in the data frame type. So we have select, and I can put in avg, which is the function from Spark SQL functions. So import org apache Spark SQL functions. And then I could say avg for column horsepower. So this is perfectly legal. If I did a show here, and if I ran this, we would see a data frame with a single row and a single column containing the same value 105.08. So if you wanted to obtain the average horsepower of this entire data set, you can also use the df functions. So all datasets have access to all the data frame functions. And now I'm going to break the news why. Let me go up top where I read a data frame, for example, here in numbers.df. I'm going to add the type here. So numbers.df is a data frame. And notice here that data frame is actually dataset of row. Data frame here, if I control or command click on it, you'll see that actually it's a type alias for dataset of row. So all data frames are actually data sets, and their type is the very general type row. And with that, my friends, I will conclude this video. You've learned an important topic. So join me in the next lecture where I'm going to show you more operations on datasets. All right, welcome back to Datasets. I'm Daniel, and in this video, I'm going to continue what I started earlier, and I'm going to teach you how to join and group datasets so that you can combine them in any way you like. Now for this video, I am back in my project, and I'm going to continue working on the datasets application. So I'm going to add a section here, joins, so that we don't need to add the boilerplate once again for the same purpose. Okay, so let's talk about joins for a second. And for this video, I'm going to load 3 datasets here. I'm going to load the guitar players, guitars, and bands, the things that we loaded earlier in the course when we discussed joins on data frames. So let me go ahead and say val guitars as, and if you remember from the earlier video, we had a method called readdf. So I'm going to say read df from guitars.json. And I'm going to add as guitar. Well, we need to also define the case class for guitar. So I'm going to have a case class guitar. And if we go to guitars.json, we'll see here all the fields that we need to add. So we have an ID, which is an int, a model, which is a string, make a string, and the type a string. So we have ID to be an int, make, which is a string, the model, which is a string, and then type, which is a string. Now, type is a reserved keyword in Scala. So I'm going to do a find and replace here to be guitar type, for example. Okay, so I have guitar type instead of type for all the fields. So I'm going to use guitar type instead. Awesome. So I have the guitars data set here as read df from guitars.json as guitar. Let's add the other two case classes. So we have case class guitar player, and this guy has an int as well, and I think we have a name, which is a string, and then I think we have some favorite guitars. I don't remember, so let me go to guitar players.json. So I have ID, which is an int, the name, which is a string, the guitars, which is an array. So I'm going to have guitars as a sequence of int, and the band ID in which they're playing. So I'm going to add the band here, which is an int. And then I have another case class for band, which again has an ID, which is an int, the name as a string. What else does it have? Let's go to bands.json. So we have an ID, the name, the hometown, and the year. So we have hometown, which is a string, and the year, which is an int. Awesome. So we have the case classes. Let's load the other data set. So we have guitars ds. Let's say guitar players ds as read df from guitar players.json as guitar player. And then we have bands ds as reading data frame from bands.json as band. And in very few lines of code, we have 3 data sets. Now, my goal for the part of this lecture is to show you how to join various data sets. So just for the sake of this example, I'm going to join the guitar players, so this data set, with the bands ds under the condition that the guitar player's band ID must match the band's ID field. So in order for me to do that, I'm going to define a guitar player bands ds as guitar players ds dot join with. So notice we had the join method here for datasets as well, just as we did for data frames earlier in the course. But what you get is a SQL data frame at the end. So if you call the join method, you will get a data frame, but if you call join with, you will get a data set. So if you call the join method on a data set, you will lose the type information. So our preference here, because we're working with data sets, is to use join with. So we'll call join with, and we'll join with the bands ds under the condition that the column band, that is guitar players ds dot column band, must equal bands ds dot column ID. So notice that the join condition here looks identical to what we used back when we talked about joins on data frames. So we used the same kind of predicates with columns must equal the other guy's columns. And the join type is by default inner. So the join with method also takes the join type, which is inner by default, but you can use other join types as well. And we discussed about all the join types earlier with data frames. Now, the result of this expression will be a data set, but the type of the data set is going to be the tuple of a guitar player and a band. So while in data frames earlier in the course, we obtained concatenated rows containing all the columns from both data frames, in this case, we get a data set of the tuple, which is the guitar player in one data set and the band in the other data set. So let's print this out and let's see what we get. So we have guitar players ds.show. So let me run the application, give it a few seconds to compile, and another few seconds to run. And we get a stack trace. Why do we get a stack trace? So the exception says cannot upcast ID from big int to int as it might truncate. Well, yes, I know why. Because we're reading the data frame from guitars JSON, for example, and when we read df, we tell Spark to infer schema true. When we infer schema true, then Spark will read all the numbers as longs, that is big int. And we are specifying that guitars have the ID as int rather than big int in Spark's language. Big int means long. So let's change all of these to long, because Spark will infer the schema to be long when it reads the data frame, and when we convert the data set, it will think we're restricting the type. So let's run this again now. It shouldn't crash any longer. Come on, Spark. But we're printing the guitar players ds. Oh yes, because I'm being a little bit silly because I'm printing the wrong data set. Okay, let's run this again. All right, good. This is the data set that I was looking for. So notice that the columns of this dataset are _1 and _2 because the resulting dataset is a dataset of tuples. So I can actually add a type annotation here. So this is a dataset of a tuple between a guitar player and a band. So because this is a tuple, so every row is a tuple, the columns are going to be _1 and _2. And the fields for each of the rows are going to be stored in an array-like fashion. So notice that, for example, Jimmy Page is an array-like structure for ID 0, the guitar IDs that Jimmy Page likes, the band ID, and then his name. So this is the only major difference between joining datasets and joining data frames, that you will in the end obtain datasets of tuples. Otherwise, the mechanism for joining datasets or data frames is identical from Spark's point of view. All right, and we discussed the various join types earlier in the course, so there's little else to discuss joins. Let me give you a small practical exercise. I would like you to join the guitar player's dataset with the guitar's dataset on the condition that the guitar ID is contained in the guitar player's guitars sequence. So join the guitars ds and guitar players ds. Now as a hint, use array_contains. You've seen array contains before in data frames. Additionally, I would like to ask you to use an outer join type. Okay, so this exercise shouldn't be really too difficult. So just pause the video and I will come back with a solution. I won't give you more than 25 seconds to write this down. So I think, or I hope, it didn't take you more than 30 seconds to write that join. So I'm going to do the show directly. I'm going to say guitar players ds, join with guitars ds, under the condition that array contains, and array contains guitar players ds dot column guitars, so guitar players ds dot column guitars, and the element that should be contained in the column needs to be guitars ds column ID. And the join type is outer. We discussed about outer joins when we joined data frames. So I'm going to do a show directly. So I'm going to add the join here, and I'm going to add the show. And let's rerun the application. Come on, Spark, we're starting to love you. Don't get slow. Okay, so we have our data frame over here. Good, so we have _1 and _2. But notice here that when we have a guitar player that doesn't have any guitars, then we get a null here. This is expected, and this is what happens when you do outer joins and one of the fields has no correspondent in the other data set. All right, so you'll see nulls here. So that's all with joins on datasets. I'm assuming you already practiced joins on data frames earlier in the course, so I'm relying on that skill. Now, let's talk about grouping datasets. Now, for this example on grouping, I'm going to go back to the cars data set, and I'm going to group the cars by the country of origin. If you remember, cars JSON had a origin field for every car, so I'm going to group the cars by their origin. So I'm going to go back to the application, and I'm going to write the following: val cars grouped by origin as cars ds.group by, and then you can have the group by methods from the data frame. So we saw group bys when we discussed data frames, but we also have group by key. So I'm going to use group by key, and I'm going to put a function from car to some value. So I'm going to say _.origin. So this will be the key by which we are going to group the dataset. In other words, the cars with the same origin will be in the same group. And the result of this call is going to be a key value grouped dataset, string and car. So string will be the key by which we're grouping, in our case, the origin, and the car will be the type of the objects that are contained in those groups. Now, from this key value grouped datasets, we are going to call an aggregation function. For example, I'm going to call count. So if I do count, then I will return a dataset containing tuples, string and long. The string being every possible key, that is all the possible origins, and long being the number of all the cars contained in that group. So let's do a show here, just to see how that dataset would look like. Okay, it's doing some work. And we have value and count1. The value is the column name of the key, and count1 is the name of the column obtained by calling the count method. There are a bunch of aggregation functions that you can call. For example, you can have reduce groups, map values, map groups, ag, which we saw in data frames, and some more advanced functions like cogroup, flat map groups, and so on and so forth. Because you've done joins and groups in data frames, I'm not going to stress on these concepts too much. I will remind you, however, that joins and groups are wide transformations. What do I mean by wide transformations? Groups and joins can change the number of partitions that will back those datasets. And so this will involve shuffle operations. That means that whenever a job like this gets executed on a Spark cluster, some data will probably be moved in between Spark nodes, which is an expensive operation. So be careful when using joins and groups for performance. All right, folks, you're now able to do complex operations on datasets now. I'm Daniel, and I will be waiting for you in the next lecture. All right, welcome back. In the following lectures, we are going to discuss another core functionality of Spark, which is Spark SQL. So our goal is going to be to get the skills to work with Spark as kind of like a big data database. Now let's talk about SQL for a second. You know about SQL already, I assume. This is a universal standard for accessing structured data, and it's mostly used in databases, either Microsoft SQL Server or Postgres or Cassandra. They all implement a variant of the SQL language. In Spark, SQL will be an abstraction over data frames. This is targeted for engineers that are already familiar with databases and have them ready to work with big data. So for this reason, SQL is supported in Spark in two main areas. First of all, it's supported programmatically in expressions, and you've seen this before in Select Expra, and we're going to explore support in the Spark shell with actual SQL statements. Now, this support for SQL in Spark is done in two ways. First of all, by importing the concepts of database, table, and view, which are already familiar to most engineers. This is one aspect. The second aspect is allowing engineers to access data frames as tables in the Spark shell particularly. Now, if you're wondering what the difference between a table and a data frame is going to be, well, data frame and table are identical to Spark. That is, they're stored in the same way, they're partitioned in the same way, and so on and so forth. On the other hand, data frames can be processed programmatically. So data frames are accessible to us in Scala with all the expressions that we saw throughout the rest of this course, whereas tables are accessible in SQL, which is what we're going to see in this lecture and the next. Good. Now, for this particular lecture, we will make an exception and we will not create an additional application in our project, but rather we would work in the terminal. So exclusively in the console. So I will ask you to open a terminal on your computer and navigate to the Spark Essentials folder. If you list this folder, you will see the subfolder Spark Cluster. I would like you to go there. And if you haven't done so already, just execute the script buildimages.shell. This will construct a Docker container containing a Spark distribution for you. It will take a while, so if you haven't done so already, just pause the video, execute the script, and wait until it finishes. If you have executed the script, then execute the following command. Docker compose, so docker-compose up, --scale, spark-worker equals 3. This is a configuration for the Docker compose YML, and this will spin up a master node and 3 child nodes, 3 worker nodes for a Spark cluster in Docker. So if you execute this, Docker will create 4 Docker containers for us. And once the output here has paused, so just like this, when it says successfully registered with master Spark at whatever address, open another terminal window or tab on your computer, navigate to Spark Essentials again, and execute the following command. Docker exec -it, then copy and paste the master's ID, so spark-cluster _ spark-master _1, so copy this guy, and paste it here, and execute bash. So this will automatically connect to the Docker container containing the master node, and you execute a bash shell. So right now you're inside the Docker container operating as root. If you hit ls, you will see all the folders under the root folder. And you will see we have a folder here for Spark. So go ahead and navigate to Spark, so cd Spark, and we will see a bin folder. If we execute /bin/spark-SQL, we will run a SQL shell on this Docker container. So this will take a couple of seconds to run and start up the Spark session, and it will start a SQL shell for us to operate on. So we see here a prompt with Spark SQL. Once you get this prompt Spark SQL, you can execute regular database-like commands. The first command that I'm going to show you is show databases with a semicolon at the end. So when you hit this, Spark will give you the list of all the quote-unquote databases that it has available. Right now we have the default database. A database from Spark's point of view is nothing else but just a form of organizing tables. A table, like I mentioned earlier, is identical to a data frame from Spark's point of view, but from our point of view is different in the way that we access it. A data frame is accessible in Scala. Right now, a table is accessible in this SQL shell, which we are going to use. Right now, because we only have the default database, we are connected to it. Let's create another database. So create database. Let's call this Rock the JVM with a semicolon at the end. So right now we have a database created for us, and let's use Rock the JVM. Cool. Right now, because we have a database, let's create a table. So we can create table. Let's call this persons. And this persons table, let's say it has two fields, an ID, which is an integer, and a name as a string. Semicolon at the end, enter. Awesome. So we have a table created for us. Control L or Command L to clear your output and get back to the SQL prompt. And let's select star from persons. Right now, you're able to do any SQL statements that you like because you're operating on a database-like shell. Right now, we don't have any input or we don't have any data in the persons table, so let's insert some values in it. So we have insert into persons values, and then we can put values here in tuples. Let's say we have ID 1, and let's put Martin Odersky as our first citizen, and then with a comma, let's put another tuple 2, and then Matei Zaharia, the one who started the Spark project, and then a semicolon at the end. Right, so we now have two rows in our table. So if I do select star from persons, and then a semicolon, then I have here my output. So right now we've created a database, we're able to use it, we created a table, and we've inserted some data into it. Now, the true power of the SQL shell is that no matter how big your data frames or your tables are, Spark is able to access them and Spark is able to transform them. So if you run any SQL statement, Spark will do the same transformations that we've been learning throughout the rest of the course. Now, I want to show you a key difference between what is called a managed table and an external table. So let's describe extended persons. Describe will give you information about this table, and extended will give you more data than a non-extended command. So notice here we have a type managed. A managed table means that Spark is in charge of the metadata of this table, that is the description of where the table is, what the columns are, what the schema is, and Spark is in charge of the data. So if you drop a table, it will drop both the metadata, that is the description of the table, and the actual data. So if you drop table persons, you'll actually lose the data. If you really want to understand why, you can open another terminal window or tab on your computer and hit another docker exec -it, and then you can paste the ID of the Docker container, so spark-cluster _ spark-master1, and then hit bash again. And then go to the folder /spark/spark warehouse, and then hit ls. You'll see here rockthejvm.db. This is the folder where all the tables related to the rockthejvm database are going to be stored by Spark. So if you go to rockthejvm.db, you'll see folders here for every single table that we have. So we have persons here because that's the only table we have in our database. If you go to persons, you will see a number of files. Each part over here is a partition in the table. So this is how a managed table looks like. If we wanted to create an external table, we would do something like this. create table, and let's say we wanted to create a table called flights that had an origin as a string and a destination as a string. Now, if you wanted to make this table external, you would need to pass additional options. So first of all, you would need to specify in which format you would want to store it. So you'd say using CSV. So assume I wanted to store this table in CSV format, I would say using CSV, and then I would pass in some options. So options, and then open a parenthesis. And I would say header true, and path, let's say /home/rock.jvm/data/ let's say flights. And then semicolon. So these options here are very similar to what we did when we wrote data frames. So we specified the format with CSV and we passed a bunch of options. So we would say option and then header true and then option path, this path. Now let's insert a bunch of rows into this table just to actually write some data to the table. And we would say something like insert into flights values. And then we put in some tuples. And let's say we had Los Angeles, and then New York. And then another tuple, let's say London to Prague. Good. So we have two values, two rows here into the table. So we select star from flights. We have two rows here, Los Angeles to New York and London to Prague. Now, if you insert some actual data into the table, you would find that if you navigate to /home/rock.jvm/data/flights, you would see that this folder is already created. We would have two parts here. So we have two partitions for the flights table. And if we describe the table, so we describe extended flights, we would see the information related to this table. And we would see here that the type of the table is external. The provider is CSV, and then the location is a file. So just to recap, we have the concept of a managed Spark table, in which Spark is in charge of the metadata, that is the description of the table, plus the actual data that the table contains. And if you drop the table, you will lose the data. Versus, if you have an external or unmanaged table, Spark is in charge of the metadata only. That is, Spark will keep the description of the table inside its own files, but the actual data is in some other place. This is very useful when you have some Hive or some S3 files that you want to keep for yourself so that they aren't managed by Spark. So if you drop the table, you get to keep the data, but the data is your responsibility. So this was a very, very short introduction to Spark SQL and the Spark SQL shell. We learned how to create and use databases and tables. And the fun part is that once you can create and use them, you can write any SQL statement you want, which is the subject of the next video. All right, we are back to Spark SQL, and in this video I'm going to teach you how to use Spark SQL programmatically, that is in Scala. So we are back to our project. Now I've done something in between these two lectures so that you can refer back to it whenever you have the time. So I've created, under the Scala folder, I've created a part 4 SQL package in which I created a dummy application called Spark Shell. And I've put down everything that we did in the previous lecture. That is how to build the Docker containers, how to connect to them, and all the commands that we wrote in the previous video. Now, for this video, I would like you to create a new application under the part 4 SQL package. First of all, create it, and then create a new Scala application. Let's name this Spark SQL, make it an object, and extends app. If you're curious where you can find all that I wrote here in the Spark Shell dummy application, you can find it in the repository for this course. So that will be at github.com/rock.jvm. Awesome. Now, in Spark SQL, let's go ahead and create our boilerplate. So I'm going to say val spark equals spark session dot builder dot app name, and let's name this Spark SQL practice, and then config spark master local, and then get or create. Good. So we have our Spark session over here. Now, let me go ahead and read one of our data frames. Let me go ahead and read, for example, the cars JSON data frame. So I'm going to say val cars df as spark read option infer schema true, and then JSON at source main resources data cars.json. Awesome. Now, with this data frame, we used to do something like carsdf.select, and we used to have a column called name. Let me import org Apache Spark SQL functions. So we used to have these kind of functions, and we used to do selects on data frames, and we selected expressions on columns where some expression would be true. So where column origin would triple equals USA. So this is how we would select all the American cars from our data frame. So this is the regular data frame API. Now, I want to show you how we can use Spark SQL to do the same thing. For example, how to select all the American cars. And first of all, we would need to say carsdf.create or replace temp view. This is important. So I will call this method create or replace temp view, and I will give this the name cars. So what this will do is it will create an alias in Spark so that it can refer to it as a table, so that it can later say spark.sql, so SQL, and you can pass in any SQL string that you like. We usually do multi-line strings, so I use triple quotes here. So I can say select star or select name from cars. So this is the name under which Spark will identify my data frame, where origin equals, so a single equals, single quotes USA. So this call over here is a data frame. So let's call this val American cars df. Whenever you call the SQL method, you'll return a data frame. So I can simply say American cars df.show, much like we did with any other data set or data frame. So give this a few seconds to compile. Let me collapse my menu over here. Let me clean up my screen estate while Spark is starting up. All right, so I have all the American cars here because my SQL statement just worked. So at this point, you have access to the entire power of SQL in this Spark SQL call. You can do selects, you can do multi-line selects, nested selects, you can do groups, joins, sorts, whatever you like, and whatever you know from regular SQL, you can also do in Spark. Now, the more interesting SQL statements that you can run are to create databases and create tables. So for example, if you run Spark SQL and you say create database, rock the JVM, then this also returns a data frame. This returns an empty data frame. So when we run this application, Spark will run all the SQL statements one by one as if it were a Spark shell. So it will run this statement first, then this statement after that. So when I do create database rock the JVM, watch what happens. I'm going to run the application again, and I'm also going to uncollapse my file explorer over here, because Spark automatically created a new folder in our project called Spark Warehouse. Spark Warehouse is a folder where Spark will store all of its databases. So if I uncollapse this, we will see rockthejvm.db, which is very similar to what we saw earlier in the earlier lecture with the Spark shell. So rockthejvm.db will be a folder where Spark will store all the tables belonging to rockthejvm. Now, in practice, we tend to change the default directory of the Spark warehouse because we might want to store it elsewhere, like in S3 or somewhere else. So what we usually do is to add a configuration here. So right up top at the Spark session where we do Spark Session Builder, we would add another configuration. So config, and the configuration is Spark SQL warehouse dir, dir. And we will put in the folder source, main, resources. Let's call this warehouse. So let me go ahead and remove the Spark warehouse directory, the default one, and let me rerun the application just to show you how this is going to look like. So under source main resources, I will expect to have another directory over here. So look at that. We have warehouse rock the JVM DB. This is how IntelliJ shows our folders. So this is actually two folders, warehouse and rock the JVM DB under it. But IntelliJ shows them like it shows packages. So we can write any SQL statement that we like under Spark SQL. So for example, we can say Spark SQL use rock the JVM. And every subsequent select will be related to the rock the JVM database. We can also say Spark SQL, say show databases. And show databases actually returns a table, which means that our programmatic call to Spark SQL will return a data frame. Let's call this databases df. And we can simply do databases df.show. So let's rerun this and see what we get. We should get the default database and the rock the JVM database. All right, so we get a data frame with a single column and two rows. So we can run any SQL statement. Awesome. Now I'm going to leave the SQL practice for the exercises because I already assume you know some SQL. So I will leave that for the exercises, but I'm now going to show you some techniques related to Spark SQL in particular. One such technique is how to transfer tables from a database to Spark tables. So here's how I'm going to do it. First of all, I'm going to go to part 2 data frames, to joins, and I'm going to shamelessly copy the code that we used to read the tables from the employees database from Postgres. So I'm going to copy this, and I'm going to get back to our application over here, and I'm going to paste it. So we have a method called readTable, which can read a table from the Postgres container as a data frame. Now, I would like to ask you to start up your Postgres container. So go to your terminal and open up the Docker container for Postgres. In other words, just navigate to Spark Essentials, where you have your project installed, and just do docker compose up to start the Postgres container. So my Postgres container is already started, so I can now connect to it if I ran this application. Now, I'm not finished yet. I'm not going to run the application yet because I want to transfer these data frames that I obtained by calling the readTable method to Spark tables. And I'm going to start with just one table. So I'm going to say val employees df as readTable with a table name employees from the Postgres database. Now here's what I'm going to write about this employees df. So I'm going to say employees df.write. So this is a data frame writer. I'm prepared to write this data frame. So I'm going to say employees df.write, and I'm going to add a mode, save mode.overwrite. And then I'm going to call the method save as table with the table name employees. So what the save as table method will do is it will save this data frame under the table name employees in the rock the JVM database that I'm currently using. So if I run the application now, I should see a new folder under the warehouse rock the JVM DB folder. Takes a little while to write 300,000 employees, but we have a folder under warehouse rock the JVM DB.employees. So this is actually 3 folders. So we have warehouse, rock the JVM DB, and employees, but IntelliJ again shows this composite folder as a package. And here we have a number of files. So we have this snappy parquet. This is the single partition of the employee's data frame as snappy parquet. And we have the CRC files for checking integrity. All right, so this works for employees. Let's do the same for all the other tables in the Postgres database. So let me create another method, def transfer tables, which is going to receive a list of table names as a list of string. All right, so I'm going to do the following. I'm going to say table names for each. And for each table name, I will do the following. I'm going to say val table df as read table with that table name. All right, then I'm going to load it in memory. So I'm going to say table df dot create or replace temp view with the table name. So I can refer to this table under the same table name in Spark SQL. And then I'm going to do what I did with employees df. So I'm going to paste this. I'm going to say table df dot write dot mode override save as table, and I'm going to pass in the same table name. And I'm going to do this for all the tables in the Postgres database. So I'm going to say transfer tables, and I will have a list of employees, departments, managers, titles, and then we have the department employee relationship, and then we have salaries, I think. And we also have a dept managers, if I remember correctly. Now, let me check the table names. So I'm going to go to Spark Essentials and I'm going to connect to my Postgres database. So I'm going to say psql shell, and then I'm going to \dt to describe all the tables in my database. So I have departments, which is good, department underscore employee, so dept emp, which is fine, dept manager, singular, so not dept managers, but dept manager, employees, movies we wrote in the previous lecture, salaries, so salaries, plural, and then titles. That one is correct. Let me write these one by line because it looks better and it's easier to read so that we don't scroll our code over and over again. All right, so we have transfer tables. Now, if I run this application, I should be seeing multiple directories under warehouse rock the JVM DB. Now, the problem is because I've already written the employees table, if I try to transfer tables with employees again, it will try to overwrite the employees table and it will fail, even though I've specified the save mode override. That is because in Spark 2.4, the default override mechanism has changed. This is something that's behind the scenes. So if you're using Spark 2.4 or higher, which is what this project has configured, you need to config and you need to write the following. So repeat after me. Spark SQL legacy allow creating managed table using non-empty location. So look at this. Spark SQL legacy allow capital creating capital managed, capital table, capital using, capital non-empty, capital location. And this whole mouthful needs to be configured to true. Let's run this application again. This should work. So we shouldn't get any exceptions thrown. And it will take a bit of time because the tables, oh, we got an stack trace. Relation public.managers does not exist. Yes. The table managers does not exist. Only dept manager exists. So let me rerun this. Notice that warehouse rock the JVM DB already has two tables. So we have employees and departments. But let's rerun the thing and let's store all the tables. It'll take a bit of time because the entire database is 160 megabytes. All right. We have employees, departments, then we have everything else. So this is how you can transfer tables from a regular database into a Spark database, into a data warehouse where you have all the tables that you wanted. Now, I'm also going to show you how to read a data frame from a Spark table, from a data warehouse. So let me create a data frame just to play around. Employees df2 as spark.read. So far we already know this structure, but I'm going to call the table method. So table, and I'm going to call employees. So when you say Spark read table employees, this will be loaded as a data frame. And obviously, once you get a data frame, you can do whatever you want with it. And we've spent quite a few hours in this course operating on data frames, so I'll leave you to that. All right, you've learned quite a few techniques that are very specific to Spark SQL. Now join me in the next video where I'm going to give you some SQL exercises on Spark tables. All right, we are back to Spark SQL, and it's time I gave you some exercises. All right, so we are back to the same application that we wrote in the previous lecture, that is in the Spark SQL application, and let me give you some exercises. First, I would like you to read the movies data frame and store it as a Spark table in the rock.jvm database. So all you have to do is read the movies data frame and then store it as a table. Now, the second exercise and beyond are going to be related to the employees database that we've already transferred. So I'm going to ask you to do the following. Count how many employees we have in between January 1st, 2000 and January 1st, 2001. By how many employees we have, I mean how many employees were hired. So the employees table has a column called hire date. So you can compare the hire date to be between January 1st, 2000 and January 1st, 2001. And just count how many employees were hired in between those dates. The third exercise is going to be to show the average salaries for the employees hired in between those dates, grouped by department number. So you will have to join employees, dept emp, and salaries. And the final exercise is going to be show the name of the best paying department for employees hired in between those dates. So considering just the employees hired in between 2000 and 2001, show the name of the best paying department during that time. So I think the exercises should be pretty clear. Now, obviously for exercises 2, 3, and 4, you will have to do quite a bunch of joins. Now, in Spark SQL, you will have to write SQL statements for joins. So for example, if you want to join the employees and the dept emp tables, you would do something like Spark SQL, and then you would select star from employees E and dept emp D. So you would need to give some aliases, some names for the tables, because the where condition will need to reference those tables. So you'd say e.emp underscore no equals d.emp no. So if you've seen SQL, you probably saw something like this, where you would select something from multiple tables, and each table had a name, and the join condition is in the where clause over here, and you would reference those tables by the aliases that you set. So you would need to write something like this for all the three exercises 2, 3, and 4. Exercise number 1 is unrelated. All right, so I will give you a break right now. So pause the video now and try to run the exercises yourself, and I will come back with a solution as usual. All right, so I hope you did these exercises. It's very likely that you encountered some road bumps around comparing dates, but we're going to sort that out in just a second. So let's get rid of exercise number 1 first. So let's read the movies data frame, which is probably in the back of your hand already. So let's say movies df as Spark read option infer schema true, and then JSON at source main resources data movies JSON. Brilliant. We've read the movies data frame. Let's write it as a Spark table. So I'm going to say movies df dot write dot mode save mode overwrite, and then save as table. You saw save as table earlier when we transferred the tables from Postgres. So we had save as table, and we will save it under the table name movies. Now, speaking of that, I'm actually going to comment out the transfer tables method because I don't want the job to take that long. So right now I'm going to run the application again. A few seconds to compile, another few seconds to run, and hopefully Spark, okay, we have a stack trace over here. Why do we have that? Table review not found employees. Well, yes, because we don't have a table name employees because we're not reading it from anywhere. So I'm going to comment this out as well. So let me rerun the application, and I'm looking for the movies folder here under the warehouse rock the JVM DB. Okay, we have the movies folder over here. So we have the movies written as a table under rock the JVM DB. This is fine. Brilliant. Now I'm going to comment this out because I don't want the job to take too long. I'm going to uncomment before I commit this code to the repository, so don't worry about that. And let's move to exercises 2, 3, and 4. Exercise number 2. Count how many employees were hired in between January 1st, 2000 and January 1st, 2001. Well, I'm going to say Spark SQL. And inside the SQL statement, I'm going to write the select. So I'm going to select. And what do I need? I need how many employees. So I will need count. So I'm going to say count star from employees where the hire date is in between January 1st, 2000 and January 1st, 2001. So where hire underscore date is bigger than, so this is how we compare dates. It's that simple. So where hire date bigger than, and the string is important, 2000-01-01. So this is the format for dates. Spark will automatically know that hire date is a date. So it will know to compare the date object parsed from this string. And hire date less than 2000 2001-01-01. Awesome. Now let me go ahead and show this. Now, before I actually run this application, I need to load these tables from Postgres or from the warehouse. Now, here I made a small mistake when I said read df from warehouse. This is read df from loaded tables. So this will convert a table loaded in memory by Spark into a data frame. All right, now we need to change the transfer tables method. This is the easiest way that I can think of when we are going to add a small flag here. Let's say should write to warehouse as a Boolean. And by default, let's make it false. And if we have should write to warehouse, then we are going to actually do the writing. Does that make sense? So I've modified the transfer tables method to add this small flag to tell us whether the tables should be written to these folders, to warehouse rock the JVM DB. And by default, this flag is false, meaning that we only load the tables from Postgres and we don't do any writing. So we can safely uncomment this method, and I will leave this employees df2 commented out. Actually, it doesn't really matter. And we should be able to show this resulting data frame. So let me go ahead and rerun this application, see what happens. All right, so we have count 1 equals 12. So these are 12 employees, which is kind of small. That is because the database only has employees up to 2001, 2002, something like that. So if we change the year to, say, 1999 and 2000, sorry if we're changing the dates in the middle of the game. If I changed the year to 1999 and 2000, we should see more employees. So we should see like 1,000 employees or something. So if I run this application again, I should be seeing way more employees. So we have 1,500 employees. This is a much more reasonable result. Good, so that was exercise number 2. Then we'll start doing joins in exercise number 3. So in exercise number 3, we want the average salaries for the employees hired in between 1991 and 2000 grouped by department. So we will need to do a 3-way join between employees, salaries, and department employee. This is a by-way relationship between the department number and the employee number. So we will do something like this. Spark SQL, and I will add a triple quote here, and I'm gonna select, what do I need? I need the average salaries for the employees hired in between those dates grouped by department. So I will need the department number and the average salaries for the employees hired in between those dates. So I will need the dept no. So dept no is the column for department employee, so dept no, and average salary. Now I will need to prefix these columns with the table aliases that I'm going to use. So from employees E, dept no DE, and salaries S. So I will need de.deptno. So deptno is a column from the department employee table. Then I'm going to access the salary column from the salaries table. So s.salary. Brilliant. From 3 tables, where, and I will copy and paste the hire date for the employee. So e.hire date is bigger than 1991, 1999, and e.hire date is less than 2000. So this is the condition on the employee. And what else? Well, we need the join condition, so e.empno must equal de.empno, which I showed you earlier before I gave you the break for the exercises. And e.empno equals s.empno, because the salaries table also has the empno foreign key. Now, I've done the join conditions. Now I need to group the average S salary. I need to group by de.deptno. So hopefully this makes sense. I am selecting a bunch of columns. I am selecting the department number and the average salary from 3 tables, such that these 2 join conditions hold true, and the join conditions are on the employee number and the restriction by hire date for the employee. So this will be a data frame that I later want to show, and I will kill the other show and just rerun the application, and hopefully I don't do anything wrong. If you want to test these SQL statements, you can copy and paste them directly in the Postgres database. Now, I hit a stack trace. Now, why is that? Table or view not found. Dept no. Well, dept no is actually called dept emp. So this is the association between departments and employees. I haven't yet learned this database by heart, so I hope you'll forgive me. Good, let's rerun the application, and a few seconds to do the actual join, which means Spark is actually doing some work. Good, so we have the department numbers and the average salaries for each. These are the department numbers. So this was a little bit complicated because this was a three-way join. So if you find this as exercise a little bit hard, I totally empathize. Before I learned SQL, these kind of multi-way joins were really hard for me too. So let's go to exercise number 4 now, which is the most complicated of all. We need to show the name of the best paying departments for employees hired in between these dates. So this is actually good news because we have most of the exercise 4 done in exercise number 3 because we are doing the average salary by department. So all we have to do is sort them descending by the average salary and then figure out the department name as well. So we need to do another join with the departments table. So let's do this. So let's go ahead and hit our Spark SQL, and then let's just shamelessly copy exercise number 3 and let's add to that. So in the Spark SQL to exercise number 3, we're selecting the department number and the average salary. Now we also need the department name. The department name is fetched from the departments table, which I'm going to alias by the name D. So in the from clause, I'm going to add departments D. Now the column that I want to add is d.dept_name. And the conditions here are going to be the same condition for hire date for employees, the 2 join conditions between employees, departments, and salaries. This is fine. And we also need to join with the newly added departments D. So we need to add another AND clause by de.deptNo. So the department number must be equal between DE and D. So d.deptNo. So we're now selecting the department names as well. We need to sort them by salaries descending. So we need to order by, and we need a column name. And the column name is this average S salary. We need to give it an alias. Let's call this payments. So we need to order by payments. And then we need the best paying one. So I'm going to say limit 1. All right. Good. Now, looking at this table, we can very easily identify which department we are looking for. So the best average salary is actually this one with 73,000, and the department number is D007. James Bond, are you listening? All right. So we are looking for the department number 007 and the average salary 73,234. Hopefully, we will get it. So let us do a show. Let's rerun the app. And fingers crossed we will get the department. It'll take a bit of time because Spark will need to join tables with 300,000 rows, which takes a little bit of time. We get a stack trace. Well, why is that? d.deptName is neither present in the group by nor is it an aggregate function. Well, that's actually very true because we have an aggregate function and 2 non-aggregate columns. So we need to group by the rest of the columns. So I'm actually going to remove the d.deptNo, and I'm actually going to group by d.deptName. So we have an aggregate column. Come on, IntelliJ, let me live my life. So we need an aggregate column that I called payments, and we have a non-aggregate column. So because we have a non-aggregate column, we need it here. So just to recap, we're selecting the average salary and the department name from all these 4 tables under these 3 join conditions, and the condition that the employee must be hired in between 1991 and 2000, grouped by the department name, ordered by payments, and limit 1. Godspeed. Come on, Spark. Do this for us, please. A few more seconds to do the join. All right, so we have the data frame that we computed in exercise 3. I forgot to remove the show so that the job takes a little bit of time. So we have payments and 48,000. This is quality management. This is actually the lowest paying department. God damn it. We need to order by payments, disk, descending. So let's remove the show and let's rerun the application to get our final result. This is actually a good sign because the SQL actually works correctly. It just returns the least paying department instead of the best paying department because I forgot to add a desk here. Okay, so we have payments. This is 73,234. This is the actual number that we saw in the previous table, and the department name is called sales. So there you have it, folks. Quit being engineers and data scientists and big data and stuff. Go do sales because that's how you'll earn the most money. Joke aside, these exercises were quite difficult. They're not really Spark SQL related, they're more like plain SQL related. But if you've done these yourself, I'm really proud of you. This is actually quite hard. So, congratulate yourself on mastering yet another core Spark topic. I'm Daniel, and I will be waiting for you in the next lecture. All right, welcome back. If you've come this far, I am really proud of you. The high-level APIs that we've learned in this course should get you through most Spark tasks that you might encounter in real life. Now, this chapter, which is probably going to be pretty short, will introduce the low-level Spark APIs, and in particular, I'm going to introduce the concept of RDDs, which you might encounter as you read more on Spark and as you write more Spark code. So in this chapter, I want to make sure that you know what RDDs are and how to work with them. So in this lecture, I want to introduce RDDs, which stand for Resilient Distributed Datasets. And after this lecture, you should get some essential skills in working with RDDs. That is, you should be able to read and write RDDs to and from some external sources and how to convert to and from data frames and data sets. You will then understand the difference between RDDs and data frames and datasets because at first glance, RDDs will look very similar to datasets. And here's why. RDDs are essentially distributed typed collections of JVM objects. Now, if you pause that for a second, you will probably notice that this definition is essentially identical to the one that I gave you for data sets. The difference is that RDDs are actually the underlying first citizens of Spark. That is, all the higher level APIs that we've learned so far in this course actually reduce or boil down to RDDs. So whenever you write a data frame transformation or a dataset transformation, before Spark runs any code, it will compute a plan to process these RDDs behind the scenes. So you can think of RDDs as the essential building blocks of big data. RDDs are the ones that are actually partitioned, as we will see in this lecture. So why would we want to use RDDs? Well, the thing about RDDs is that they can be highly optimized. So because RDDs are the ones that actually have partitions, we can actually control how they are partitioned. With data frames or datasets, we could not do that. We can also determine the order of elements in RDDs and the order of operations on RDDs because they can impact our performance. Advanced users of Spark can actually double the performance of their big data processing with some really advanced knowledge of the Spark internals and RDDs. So this can actually have some really big impact on perf. However, RDDs are actually hard to work with. So for complex operations, we need to actually know the internals of Spark if we want to get even decent performance. Also, if you want to do quick data processing or aggregations, the RDD API is actually a pain in the neck because you have to do a lot of manual work to do what the data frame API would have done in a single line of code. So for most big data and Spark tasks, you should still use the data frame or the dataset API because Spark is usually smart enough to optimize your operations without you needing to do anything at all. If you really want to care about performance and you need to fine-tune the operations on your distributed data, you should probably use RDDs then. All right, enough talk, let's go to the code. So in our project over here, because we've started a new chapter, let's go to the source main Scala and create a new package. So I'm going to say new package. Let's call this part 5 low level. And under the part 5 package, I'm going to create a new Scala class. I'm going to name this RDDs. Make it an object as usual and extends app. Awesome. Let's do our boilerplate. So I'm going to say val spark equals spark session builder app name. Let's call this introduction to RDDs. Give it whatever name you like. Let's config spark master to be local and then get or create. Now I'm going to show you how to create RDDs, but first we need an additional what is called a Spark context. So the Spark context is usually named SC and it's spark.sparkContext. The Spark context is your entry point for creating RDDs. Normally you don't have access to the low-level APIs because we operate on the data frame and dataset level, but if you want to operate on RDDs, you would use this Spark context. And I will show you how to create an RDD in various ways. The first way is to parallelize an existing collection. So if I had a collection of, say, numbers, so if I had numbers to be 1 to 1 million, so a local range collection, I would say something like numbers RDD as SC, that is the Spark context, dot parallelize numbers. And what we would get would be an RDD of int. So this is a distributed collection of ints. The second way is reading from files. First of all, let's read some stock values here under the stock CSV. This is easiest to parse because it's a CSV. We can simply split by comma. So if I defined a case class called stock value, which had the symbol, date, and price, let's call this company as a string, the date as a string, just to ease our parsing, and the price to be a double, we would read a local collection of stock values via, let's say, a method called readStocks, which takes a file name as a string, and we would write something like this. So this is basically just a plain file read. So we would say source from Scala.io. So make sure you import the right source. So source.fromFile, and I would pass in the file name. Then I would say getLines, which is an iterator of string, and then I would map each line to the tokens. So I would split the line by comma. So line split comma, and then I would map each token array, so tokens, to one of these stock values. So I would create a stock value out of token 0, and then tokens 1, and then the tokens 2 converted to double. So we would say tokens 2.to double. And then finally, I would say toList to make this a list of stocks. So right now, if I called this method, I would get a list of stock values. Obviously, if we wanted to convert that to an RDD, we would call sc.parallelize. So I would say stocks RDD as sc.parallelize, and then I would call readStocks from the file name. So source main resources data stocks.csv. So notice how much harder it is to read an RDD from a file rather than a data frame or a dataset. Now, because this is a CSV, would also have to drop the first row. So this is the header. So if we wanted to get rid of the header, we would say drop 1. So if you read data from a CSV, then you'd also need to make sure if you have a header, if you need to drop the header, what the separator is, and so on and so forth. There is another option to read a RDD from files, but with not much less labor. So let's say 2b, reading from files, because we're on the same topic. So I can do the following. I can say val stocks RDD2, to be sc.textFile, and you can pass in this path. So when you do sc.textFile, you will return an RDD of string, because every single row in the file will be treated as an entry in the RDD. Now, because you have basically a distributed collection of strings, you can do map and flat map and so on and so forth, which I'm going to get to in a second. So I'm going to shamelessly copy the splits and the stock value creation over here. So you have an RDD of string, then you map it to obtain an RDD of arrays of strings, and you map that to obtain an RDD of stock values. That is in theory. Now, how do you get rid of the header? Because we mentioned that RDDs are distributed collections, so you can't simply drop one because you don't really know which entry you are dropping from the RDD. So I'm going to do a plain filter. So I'm going to say .filter. And for the tokens array, I'm going to simply specify that the first token, this is the company name, should be an uppercase string. This is how these entries are different from the header. So I'm going to say tokens 0.toUppercase must be equal to tokens 0. So this is how I filter out the header. So as you can see, this is still a pain in the neck because you don't really know if you have a header, how the header would look like, if this filter still applies for your CSV, and so on and so forth. So yeah, quite a bit of labor. The easiest way is to read from a data frame. So we would say something like stocks df as spark read option, and then we would pass in our CSV options, that is header true and option in first schema true, and then CSV at source main resources data stocks.csv. Then you would convert that to a data set. So let's say val stocksdf stocksds as stocksdf.as stock value, but you need to import the Spark implicits as well. So import Spark implicits, and then from that data set you can say, let's call this stocks rdd3 as stocksds dot rdd. So you will obtain the RDD that backs this data set. And at the end, what you'll obtain will be an RDD of the right type, stock value. You can also do stocksdf.rdd. So if you do val stocks RDD, let's say RDD4 as stocksdf.rdd, that's also valid, but you will obtain a RDD of row because the stocksdf is a data frame, not a data set. So you will lose the type information. In order to keep the type information, you will need to convert from a data set. All right, now, once you have a RDD, let's say you want to convert the other way around from an RDD to a data frame or a data set, you can also do that. So we can do an RDD to a df. So for example, I can say val numbers df as numbers rdd.toDF, and then you can pass in the column names. In this case, I have a single column name, which I'm going to call numbers. If you have an RDD with multiple fields, with multiple columns, you need to pass in the column names as well. So this is how we can create a data frame from an RDD. We can also create a data set from an RDD. So I can say, for example, numbers ds as spark.create dataset, and then you can pass in an RDD of your type. For example, I can pass in numbers RDD, and this will be a dataset of int. Now, bear in mind, when you transform an RDD to a data frame, you lose the type information, because the data frames do not have any types. They only have rows, whereas with datasets, you get to keep the type information. All right, so you learned various ways of reading RDDs and how to construct RDDs, and also how to convert between RDDs and data frames or datasets. Let's compare RDDs in data frames and datasets. Now, the reason why I crossed data frames on the screen is because data frame is actually a type alias for dataset row. You learned that earlier in the course. So in reality, we're comparing RDDs with datasets. So first, let's see what RDDs and datasets have in common. First of all, RDDs and datasets are distributed collections of JVM objects. So we naturally have the collection API that we've gotten used to from regular Scala collections. So we have map, flat map, filter, take, reduce, fold, and so on and so forth. Secondly, we have the capability of combining RDDs and datasets respectively by union, and also the ability to count and distinct, and also how to group by and sort by for both RDDs and datasets. Now, what RDDs have over datasets are partition control with various methods to repartition, zip partitions, map partitions, check the partitioner, coalesce, which reduces the number of partitions, and everything related to managing partitions. Now, RDDs can also optimize operation control with checkpointing related methods and caching. Also, RDDs can control their storage with get storage level and persist and unpersist as well. So RDDs have a lot of control over how they're stored, how they're partitioned, and how operations on them are being executed. By contrast, what datasets have over RDDs are select and join. So these two methods have the power to do any kind of data processing that you like. And we've seen in the rest of the course how powerful they are and what kind of processing we can do. And we can do a lot. Now, this powerful high-level API comes with Spark's capability to plan and optimize the operations before we run any code. So Spark can automatically optimize our selects and joins without us needing to do anything at all. This is a really powerful combination of the high-level APIs in datasets. So for this reason, in most Spark operations, you would use the data frame or the dataset APIs. So let's do a small recap of what we learned in this video. So first of all, we turned in a regular collection into an RDD. This is the first way that we can create an RDD. First of all, we need the entry point to the low-level API by creating the Spark context from the Spark session. And then we can turn a regular collection into an RDD by calling the parallelize function. We also learned how to read an RDD from a file, so we can use the text file method on the Spark context as well, and you can pass the path to your file, but then you need to process each line in turn, and we saw how painful that was. We learned how to turn a dataset or a data frame to an RDD by calling the RDD field. All datasets can access their underlying RDDs. We also learned to convert RDDs the other way around to data frames or datasets. So we learned to call the toDF method and how to create the dataset based on an RDD. And just a minute ago, we discussed the differences and the commonalities between RDDs and datasets. Alright, so you're touching the water on some very advanced concepts. Join me in the next video where I'm going to teach you how to work with RDDs. Alright, welcome back to RDDs. In this video, I'm going to teach you how to effectively work with RDDs. By that I mean transformations, how to control partitioning, and at the end I'm going to give you some exercises. Alright, so we are back to our project, and for this lecture I'm actually going to continue the code that we wrote in the previous lecture, in the application that I called RDDs, so that we don't have to write our boilerplate all over again. We have some RDDs that I actually want to show you how to transform. So this is what I will show you first. I will show you transformations. So once we have an RDD, then we can process it like we would on any other collection. RDD, the stocks RDD has three parameters here for the stock values. We have symbol, date, and price. Now, let's assume that we want to filter the stocks which are only for Microsoft. So let's define a val called MSFT RDD as stocks RDD.filter. So notice we can do filtering, and we can pass in any function from stock value to Boolean. So I'm going to say underscore dot company or dot symbol equals MSFT. So this is for Microsoft. Now, once we have a filtered RDD, we can do count, for example, as Microsoft RDD dot count. Now, it's worth pointing out that this filter transformation is lazy. And the count method is an action, and it's eager. So in the RDD API, we also have the notion of the lazy transformations and the eager actions. We discussed about them earlier in the course. Lazy transformations do not apply until Spark actually needs to, whereas actions actually trigger computations in Spark. We also have maps. So for example, if I want to select all the companies in my stocks RDD, so I'm going to say company names RDD equals stocks RDD.map, and you can pass in any function from stock value to anything else. So I'm going to say _.symbol. Then I will get an RDD of strings. Now, the trouble is, because we have so many entries for so few companies, the company names will be duplicated. And so the RDDs have a method called distinct. Distinct is also a lazy transformation. So we learned how to do distinct and then how to do counting. Good. Let me show you how to do min and max based on the ordering of stock values. So we can say val min Microsoft as Microsoft RDD dot min. Now the trouble is that if I try to compile this application, the compiler will yell at me because there is no implicit ordering defined for stock values. So I need to define an implicit ordering. So I'm going to say implicit val stock ordering as ordering from less than, and we need a comparison function between two stock values. So we need stock A and stock B. And the return type of this function needs to be a Boolean, which specifies whether the first argument is less than the second argument. So I'm going to say sa.price is less than sb.price. Now, the problem is I haven't specified any types for this stock ordering, so the compiler has no way of inferring the fact that I'm referring to stocks. So there are a couple of ways that I can solve that. Either I can specify the type explicitly here, so I'm going to say ordering of stock values, and that's how the compiler is able to figure out the types. Or I can specify the type here in the from less than, so I can say stock value. Or I can specify the types here in the function arguments. So SA is a stock value and SB is a stock value. So any one of these three things will do to help the compiler infer the types. Now, if I try to recompile the application again, the compiler will not yell at me because it found the implicit stock ordering. This is also an action because it reduces the entire RDD to a single value. Now, speaking of reducing, we have the reduce method on RDDs. So for example, I can take the numbers RDD and I can sum them up. So I can do numbers RDD dot reduce, and we have two options for reduce. We have reduce and tree reduce, which is more advanced. I'm going to say reduce, which is the same function that we used to have for collections, and we can pass in any function that takes two ints and returns another int. So I'm going to say underscore plus underscore just to get the sum of all the numbers. And finally, I want to show you grouping. And let's assume, for example, that I want to group these stocks by the symbol, that is by the company name. Well, I can do something like val, let's call this grouped stocks RDD as stocks RDD dot group by. And notice we had a couple of group by options. Let me bring them all in scope. So we have group by that takes a function from stock value to any kind of value, which is going to be the key by which we are going to do the grouping. And then we have two overloaded functions for group by, one that takes a number of partitions and another one that takes a partitioner. These are more advanced, and these allow us to control how the resulting RDD is going to be partitioned. Not our cup of tea right now. So we are going to group by, for example, by the company name, so an underscore symbol. So what we get here at the end is another RDD that takes as type argument, so an RDD of tuples between a string, which is the key by which I'm grouping, and as the value I have an iterable of stock values. Now, I want to mention that grouping, much like with data frames and datasets, is very expensive. Because given the fact that you may deal with big data, which means that your RDDs are going to be partitioned in between Spark nodes, grouping will involve operations known as shuffling. You've heard about them before in the course. So because we have data partitioned in between many Spark nodes, grouping will involve moving data in between the various Spark nodes as the job is being executed, which is very expensive. So use grouping sparingly. So let's just run this application to make sure that everything that we wrote so far actually runs correctly. Okay, so our application ran correctly. We didn't get any exceptions. So let's just move on. We spoke about partitioning for a second. Let's spend a few more seconds talk about partitioning. So I mentioned earlier that RDDs have the capability of choosing how they are going to be partitioned. So here's what I'm going to do. I'm going to take the stocks RDD, one of the stocks RDDs that I have. I'm just going to take this one, and I'm going to repartition it to 30 partitions, just to show you how that would look like. So let me name this repartitioned stocks RDD as stocks RDD dot repartition, and I can pass in the number of partitions, say 30. Now, what I will get will be a new RDD of stock value. Now, let me show you how that would look like if I wrote it to a data frame. So I could say repartitioned stocks RDD dot to df, and let me go ahead and write it to a file. So I'm going to say write, and then mode, save mode dot overwrite, and then let me write it as parquet to the path source main resources data, and let's name this data frame stocks 30. Let me rerun the application, and this time I'm going to open up my file explorer. So under the resources data, I should be seeing a new data frame over here. Okay, so we have stocks 30, which has a bunch of files. So look at that. We have part 0000 up to part 00029. So we have exactly 30 files for the stocks RDD. So this is how we can repartition an RDD. Now, it's worth mentioning, so I'm actually going to write this here. Repartitioning is expensive, because repartitioning by definition involves moving data in between Spark nodes. So involves shuffling. So the best practice for repartitioning is to do repartition early in your Spark workflow and then process the repartition RDD. Now, probably the question that pops up earliest after learning about partitioning and repartitioning in particular is, hey Daniel, how many partitions should I have? Well, the answer will involve the size of one partition rather than the number of partitions in total. So in my experience, for best practice, the size of a partition should be between 10 and 100 megabytes. So this is the optimal size of a partition. You don't want one giant partition 1 terabyte in size, nor do you want a lot, millions of small partitions like 100 kilobytes in size. So that's 1 year of Spark experience right there in these 2 lines of comment. Now, we talked about repartitioning. Let's talk all about coalescing. So coalesce will repartition an RDD to fewer partitions than it currently has. So you can say val coalesced RDD as repartitioned stocks RDD dot coalesce, and then you can specify the number of partitions. Let's say 15. And by default, the shuffling is false. What do I mean by that? Well, coalesce will not necessarily involve shuffling. That's because the data doesn't need to be moved in between the entire cluster. That's because we have, in this case, at least 15 partitions that are going to stay in the same place, and the other partitions are going to move the data to them. So this is not a true shuffling in between the cluster. However, this is a new RDD, so if I wanted to save it, I could say coalesced RDD, and then let me copy the other code. And I said parquet to source main resources data, let's say stocks 15. If I run this application, you would see that this stocks 15 RDD would have 15 partitions. Let me open my file explorer. Let's collapse the stocks 30 because we're already convinced about them. So we now have a stocks 15 RDD, which has part 00000 up to part 00014. So this is 15 files. Awesome. So we learned about partitioning as well. Now, let me give you some exercises. So let me collapse my output over here so that I have room to write the exercises. First, I would like you to read the movie's JSON as an RDD. And in particular, I would like you to read the movie's JSON as an RDD of the following case class. I'll name this movie. And the movie will have a title or a name as a string, the genre as a string, and the rating, which is the IMDb rating, which I'm gonna make a double. All right, so I want you to read the movie's JSON as an RDD of this case class. Remember, the movie's JSON has a lot of fields. So when you read this data frame, I want you to select the right columns so that you can map them to the movie case class. Now, second exercise. Show the distinct genres as an RDD. This is pretty self-explanatory. Then, I want you to select all the movies in the drama genre with IMDb rating above 6. Obviously with RDD transformations. And fourth, which is probably going to be a little challenging, show the average rating of movies by genre. Obviously with RDD transformations, the ones that we learned in this lecture and in the previous lecture. Now, a word of warning, these exercises might prove a little challenging. You might encounter some roadblocks along the way, starting from the very first exercises, actually. So don't fret, just pause the video and try to solve the exercises yourself. And obviously, as usual, I will come with a solution in just a few seconds. All right, so how did you do? Let's take the exercises in turn. Let's read the movie's JSON as an RDD. First, let's read the data frame for movies JSON. So let's call movies df as spark read option infer schema true, and then JSON at source main resources data movies JSON. Probably know this the back of your hand by now. So we right now have a data frame. The data frame contains rows, and the rows contain a lot of columns. So you will need to map those rows onto this movie case class. Now, converting the movie's df directly as a data set of movie will not do the trick because one, you have fewer columns here, fewer members in the case class than you have columns in your data frame, so that will crash. And secondly, the column names, the member names here, do not match with the column names in the data frame. So title, for example, is uppercase, the genre is called major genre in the JSON, and rating is called IMDb_rating. Not to mention that they can also be null. So we have a bunch of challenges from reading this data frame as a RDD of movie. So let's do that. So I'm going to say movies RDD as movies df. And now I have to do a select. And I will add the column called title. Now, obviously, I don't have the column function, so I need to import it. I need to go up top and say import org Apache Spark SQL functions. And then everything. Okay, let me go back. So I now have the column function, and I need to select the column capital case title, and then I need to alias it to the lowercase title. So column title as lowercase title, and then column called major genre as genre, and then the column IMDb rating as rating. So this solves two challenges. First of all, we have the same number of columns as our case class has members. And secondly, we have the column names matched correctly. That's fine. But we also need to select those rows that do not have the major genre or the IMDb rating null. The title is not null, but the other two are. So we need to put a where clause. So in the condition, we'll put the column genre to be not null, so is not null, and column rating is not null. Now, it's fine to convert this data frame to a dataset, so I can say as movie. Now, from the dataset to an RDD, all we have to do is say .rdd. Now this movie's RDD is an RDD of movie. Awesome. So this was exercise number 1. Exercise number 2 asks us to show the distinct genres as an RDD. Well, this is basically the same thing as we did with the company name earlier. So the distinct genres is going to be val genres RDD as movies RDD dot map, and we can put in the function underscore genre, and then we can do distinct. And that is the genres RDD. That was exercise number 2. Then, exercise number 3, we need to select all the movies in the drama genre with IMDb rating greater than 6. Well, all we need to do is to apply some RDD transformations, not more than some plain collection transformations. So let's say good dramas RDD as movies RDD dot filter, and for every movie, we will expect that movie.genre must equal drama, and movie.rating must be bigger than 6. Let's put a break at this point and let's show the RDDs here. So let's do movies RDD.toDF.show, because you might have noticed that the RDD type doesn't have a show method, it only has for each. And movies RDD.forEach println will pollute our output pretty bad. So this is one way to show the RDD, convert it to data frame and then show. Let's print the genres RDD, so to df and then show. And let's also print the good dramas RDD, so good dramas RDD to df dot show. And hopefully I haven't done anything stupid, and this thing will work on the first try. Fingers crossed. All right. So we have our data frames over here. Let's scroll up. So we have the movies data frame with title, genre, and rating. This is fine. Then we have all the genres. This is a data frame with a single row. That's because we have an RDD of strings, right? And so when we convert the RDD of strings to a data frame, we have a single column called value. And then at the bottom, we have an RDD of movies. So we still have title, genre, and rating. And notice that all the movies have the genre drama and all the ratings are above 6, which is fine. Good. Let's delete the shows and let's go to exercise number, magically, 4. Now, for exercise number 4, I'm going to create a small case class that I'm going to call genre average rating. And this will take the genre as a string and then the rating as a double. I'm just using this case class for convenience to store this data. Now, the average rating of movies by genre. Now, in data frame speak, you would do a group by. In RDD speak, you would call the group by method on the movie's RDD. So we would do something like this. Let's call this average rating by genre RDD as movies RDD dot group by, and we need to group by the genre, so underscore dot genre. And right now we have an RDD of tuples between the string and an iterable of movies. That is, for every genre we have an iterable of movies that we need to aggregate on. So I will do a map. And I'm opening and closing some curly braces because I'm running a partial function here for a case to deconstruct a tuple. So genre and the movies. So right now I have an RDD of tuples, and if I call map, then I'm expecting to take as argument a tuple between the genre and the movies, which I'm deconstructing in a partial function. Probably done this before in regular collections. At the right side of this arrow, I'm going to return an instance of this genre average rating case class. So genre average rating, and the first argument is going to be my genre, and then the average rating is going to be the movie's ratings sum over the movie's count, right? So I will need to do the following. I'm going to say movies.map, and I only care about their rating, so I'm going to say underscore rating. Now, this thing is an iterable of integers or of doubles this time around. So movies was an iterable of movies, and I'm turning that into an iterable of doubles, and I need to do a sum. So if I do a sum, I will obtain a double. Now, this is the sum of all the ratings, so I need to divide that by the size of the movie's set. So I'm going to say divide by movies.size. All right, so this is how we obtained an RDD of genre average rating. Let's print it out. So average ratings by genre RDD.2df.show. And just for comparison, let's do the same with the regular data frames. So I can say movies RDD.2df. That's because I'm selecting just the movies where the genre is not null and the rating is not null, so this is important. And then I can call a group by, and I'm going to group by the column called genre in this data frame. And then I will average the rating, and then I'm going to call show, just to compare the results. Let's run this application again, and let's compare the tables. It'll take a while because I'm also writing all those RDDs to various partitions. So we have two tables here. One for the movies RDD. So this is the second table. This is the reference. Let me paste it here. Let's scroll up top where we also print the group by for the RDD. So what we obtained. Wow, this is some scrolled. Okay, I found the table. And this is the same table, so let's pick one. For example, adventure 634501, adventure 634501, and etc. So we have the same values here in these two tables. So by all means, we did right. All right, let's wrap this up. So what have we learned? We learned transformations on RDDs. First of all, we learned collection transformations, which is pretty intuitive given the fact that RDD is a collection like any other. So we have map, flat map, and filter, and we saw how they work. Then we learned about actions on RDDs and the fact that RDDs also have the notion of lazy transformations and eager actions. And we saw a bunch of actions like count, min, and reduce. In particular, min requires an implicit ordering for the types of the RDDs that you want to aggregate. We also learned about grouping, and we saw those in the exercises as well. When you do a group by, you will get an RDD of a tuple between the key and an iterable of the type that you have in an RDD. Now, we also mentioned that grouping is an expensive operation and involves shuffling. We also learned about partitioning, and we saw the effects of repartitioning a data frame. We also mentioned that this operation is also a shuffle and is also expensive, and we discussed some best practices around partitioning. We also learned about coalesce, which is not a full shuffle, but only reduces the number of partitions in an RDD. So congratulate yourselves, because RDDs are a very hard topic and you already know more than most Spark programmers. I'm Daniel, and I will be waiting for you in the next video. Alright, welcome to the truly practical chapter of this course. In this video, I'm going to show you how Spark runs on a cluster. And in this lecture, we're going to start easy. We are going to show you how Spark will run on our Docker-based cluster, and I'm going to show you the anatomy of a Spark job, and we're going to discuss about stages, tasks, and the directed acyclical graph as some new concepts, and of course shuffles, which you've heard of before. Also, we're going to learn how to interact with a running or a finished job with the Spark UI. Now, for this lecture, we're not going to create a new application in the code, but rather we're going to work in the terminal most of the time. So I'm going to ask you to create a couple of windows or a couple of tabs for a terminal in your computer and navigate to the Spark Essentials folder where you downloaded the materials for this course. Now, once you created your windows in your terminal, navigate to the Spark Essentials folder and to the Spark Cluster folder in the project, and then execute the Docker command to start up the Spark cluster. So docker-compose up --scale spark-worker equals 3. And give it a few seconds to start up the Docker containers. And at this point, the cluster should already be up. And in another window in your terminal, go again to the Spark Essentials folder and then do docker exec -it, so it, and then the name of the Spark master Docker container. And the Spark master Docker container is Spark cluster Spark master 1. So copy this one. So spark-cluster_spark-master1, and then bash. So now you're logged in as root in your Docker container for the Spark master node. And then if you hit ls, you'll see the Spark folder. So navigate to it and do /bin/spark shell. So not Spark SQL, but Spark shell. And give it a few seconds to start, because Spark Shell starts a fully fledged Spark session. So it should look something like this with the Spark ASCII art over here. And you will see that the Spark Shell already sets up a web server for us to inspect Spark jobs. So if you open a new browser window in your computer, and if you navigate to localhost :4040, and once this loads, you will see here a small UI. This is called the Spark UI, and this is a web application, and this is hosted on the master node in our cluster. And notice here at the top of the page, we have a bunch of tabs. We have jobs, stages, storage, environment, and executors. The jobs tab, the one we're at, describes all the jobs that we have run on this cluster, or that we are running on this cluster. Right now we don't have any, but this page will be populated soon enough. The stages will describe all the stages for individual jobs. The storage is not of too much interest to us in this chapter, and this will describe the storage for the driver and executors. We'll describe drivers and executors in this lecture and in the next one. Environment will describe all the system properties and all the configurations that Spark was started with. So you see here a bunch of configurations and their values here on the right hand side, as well as some system properties and the class paths, which is all the jars that Spark uses. And here on the very right, we have executors, which describe the data related to the nodes in our Spark cluster. This is useful for debugging purposes and for performance optimizations, which we will see later in the Spark series. Now, having discussed the UI, which we will see shortly here when we run our first job, let's go back to our terminal and let's run our first job. We have here the Spark REPL, the console over here, the shell, and let me do the following. Let me write val rdd1 as sc.parallelize 1 to 1 million. Now, notice what I'm writing here. I'm writing a plain Scala expression. You probably saw the Scala REPL before, so you saw how we can define values in a Scala shell. Now, when we start a Spark shell, we already have access to the Spark session under the name Spark and the Spark context under the name SC. As I mentioned earlier in the course, Spark and SC are very common names for the Spark session and the Spark context, respectively. So let me go ahead and run this. And we see here an RDD as a parallel collection RDD. Of course, this is not really initialized. This is only lazily initialized. But I will trigger some computation on Spark if I run an action. For example, if I do rdd1.count. And I have a result here to 1 million. Now, if I go back to my Spark UI and I refresh the page, notice here we have a completed job over here. So in this table, we have our very first job. The job ID is 0 and the description is count at console line 26. We have the submitted date, the duration, which is very fast, half a second, and we have stages, which is a new term that I'm going to explain shortly. So we have one stage completed out of one stage total, and a number of tasks completed. So we have 6 tasks out of 6 completed. So we already noticed that for a given job that I executed in the console, we have subdivisions for the job. We have stages and we have tasks. I'm going to explain what these are shortly. Now, once I click on this link here at count at console 26, we have here the details for job 0. And we have here the completed stages, and here we have a table of all the stages that compose this job. So notice that a job has stages, and each stage has tasks. So this will be the first terminology that we are going to use. We're going to use the terms job, stage, and tasks. So a job has multiple stages, and a stage can have multiple tasks. Now, what is a stage? A stage is a series of computations in between shuffles. You remember what shuffles are. They are the exchange of data in between Spark nodes. So the shuffles will delimit our stages. I'm going to exemplify that with more complex examples shortly. Now, a task is a unit of computation per partition. Now, in our case, the RDD that we had, the RDD parallelize, had 6 partitions, which is why we had 6 tasks in our stage. And we can prove that by saying rdd1.get num partitions. And we have 6. Now let's do a more complicated example. Let's call this rdd2 as rdd1.map, and let's multiply each element by 2, so underscore times 2. So right now this RDD is lazily evaluated, obviously. Now if I do rdd2.count, this will trigger a Spark job, and obviously this RDD2 also has a million elements, but if I go back to my Spark UI and click on the Jobs tab again, we see how now that we have 2 jobs, and the job ID 1 was for our last computed job. So let me click on this guy over here, and we see that we still have 1 stage and 6 tasks, but this graph over here, the stage 1 with parallelize and map, now has 2 elements. If you paid close attention, the first job only had 1 node, only 1 blue square over here. This is 1 step in what is called the directed acyclical graph. This graph maps the dependencies between RDDs. So in the first node, we have an RDD parallelize, and then we obtained a new RDD by running the map operator. So in our series of terms, we will introduce what is lovingly known as the DAG, which is the directed acyclical graph. This is the graph of RDD dependencies. In our first two examples, the DAG was very simple, but as you run more complicated jobs, the DAG can be astronomically big, but it can give you a quick bird's eye view of how your RDDs are linked together. So I mentioned earlier that a stage is delimited by shuffles. Let's force a shuffle on an RDD and let's see how Spark will determine the splitting into stages. So let me do RDD1.repartition. Let's repartition into, for example, 23 partitions, just a random number, and then let's do a count. So directly starting up a Spark job. So look at that, it already said stage 2, which is why in this jobs table, we now have stages succeeded total 2 out of 2, so we now have 2 stages, and in total we have 29 tasks. Let's see how that was computed. So let me click on this third job, and notice the DAG now has 2 stages, stage number 2 and stage number 3. Now, why stage 2 and 3? Well, it's because Spark incrementally counts the number of stages since the start of the application. That is, since the start of the Spark shell. So stage 0 was for job 0, stage 1 was for job 1, and stages 2 and 3 are for job 2, which is why you see the numbers here 2 and 3. Now, you see here that for the completed stages, we now have 2 entries in this table, and the first stage, stage number 2, had 6 completed tasks, and the stage number 3 has 23 completed tasks. That is because the count will go through all the 23 partitions, and it will run a task for each partition. So once we do a repartition, that is, once we force a shuffle, we get an additional stage. Now, I'm going to give you some additional examples, and I'm going to explain both the DAG and the splitting in stages and tasks. So let me start with the following. Let me go back to my terminal, and I'm going to say rdd1.toDF. So I'm converting this RDD to a data frame, and then I'm going to call show, which is, again, an action. So I'm going to start an additional Spark job. It'll take a bit of time, but we now have this table preview that we saw throughout the entire course. We have the column called value, and we have all the numbers here, only showing top 20 rows. Now, when I go back to my jobs tab, we have an additional job, and we have a single task with a single stage, even though the RDD was 6 partitions. So notice that once you convert an RDD to a data frame, although we have a single stage, we have many steps happening here behind the scenes. So first we have the parallelized, and then we have scan, a hold stage code gen, a map partitions internal, and finally a map where we do the show. All right, now let me show you something else. Let me go ahead and create a data set by doing a Spark range. So I'm going to say the following. I'm going to say val ds1 as spark.range, and the spark.range method takes 3 arguments. The first argument is the start of the range, the second argument is the end of the range, and then the third argument is the step in which Spark will iterate. So this is a lazily evaluated data set of long. Now, if I do ds1.show, I will start another Spark job, and I already have this little table preview, but let me get back to my jobs, and we notice here our 5th job, which has a single task. But now the DAG looks different. So the lesson to take away here is that whenever you're working with the high-level APIs, with data frames or with data sets, you don't have too much control over what steps Spark actually creates behind the scenes when computing whatever you want to compute, in this case, the show table. If you want to make this DAG or this DAG creation a little less obscure, you can type in ds1.explain and then hit enter. And here we have what is called a physical plan, which is very simple in this case. The physical plan describes all the operations that Spark will do to actually compute this data set. But as you do more complex operations on data frames or data sets, these physical plans will become increasingly large, and it's a useful skill to be able to analyze physical plans and logical plans pretty quickly. And I will give you a couple of examples here. So let's work through a more complex example. Let me create another data set. Let me call this DS2 as Spark range 1 to 1 million, or 10 million, or whatever you want to put in there. And then let's increase the step. Let's increase the step to 4 or 5. So we have another data set. Now, I will do a repartition on the first data set. So I'm going to say val ds3 as ds1.repartition. And let me insert, for example, 7 partitions. In the physical plan, if you read it carefully, the physical plan for ds1 says splits equals 6, which means that Spark will do 6 partitions for this data set. But if I repartition to 7, then I will force Spark to execute a shuffle for me. So if I hit enter, I will create a new data set long, which will contain the same data, but 7 partitions this time around. And I will verify that by calling ds3.explain. So when I hit ds3.explain, notice that the physical plan is a little bit more complicated than the previous one. The first step that Spark will do to compute ds3 will be to evaluate this range 1 to 1 million, step 2, and splits 6. And then it will execute this step, exchange round-robin partitioning with 7. So this is the new number of partitions. Now, let me do the same with the other dataset that I created. So I'm going to say val ds4 as ds2.repartition, and let me put in a different number of partitions, say 9. Obviously, if I hit ds4.explain, then I will have a very similar explain plan for ds4 as well. I start with a range dataset, and then I do a round-robin partition, this time with 9 partitions. Now, let me do the following. I'm going to say val ds5 as ds3, that is the repartitioned dataset, not select expr, and I'm going to put in a string like id times 5 as id. So we have here an expression that I'm going to use to do a select on this dataset. And if I hit ds5.explain, Spark will know in advance all the operations that it will do to actually compute this dataset. So first, it will execute the range, it will do the repartitioning, and then as step 3, which is 2 here under the parentheses, it will do a project. And the project will do id times 5 as id. And the hash over here is the identifier of the column. So this is the name of the column, id, and then hash 9l, this is the identifier of the column. And the hash 22l is the identifier of the new resulting column. Now here's what I'm going to do. I'm going to say ds5.join with ds4 under the column id. So all these data sets have the column ID in their single call. Now, when I do a join, let me attribute that to a value. Let's call this joined. This is a data frame. Now, when I do joined.explain, notice that the physical plan has ballooned. So let's figure out what Spark wants to do when we are doing the join. So first of all, before we're doing the join, we need to compute the 2 data sets, which is what happens in these 2 separate branches over here. So the lower branch computes ds3 with the repartitioning into 9 partitions. Then into the upper branch, we're doing a bunch more operations. First of all, we're computing the range, and then we're repartitioning it into 7 partitions. And then we're doing that project, which we saw earlier, and then before we're doing the join, this data set is repartitioned again with the broadcast exchange. So this broadcast exchange operation will actually do the shuffle before the join is actually being executed. And finally, we're doing the broadcast hash join with the ID hash 22L, which is what I mentioned earlier with the identifier, and ID hash 16L, this is the other data set. The inner join is the type that we're running, and then build left. This is another attribute of the join. And finally, we're projecting the ID 22L because that is the single column that this data frame will have. So notice that this graph of operations is what Spark will actually execute when it will compute this dataset. Notice that it hasn't computed the dataset yet, but it already has a plan for what operations Spark will do in what order before the dataset will be computed. Now, I really want to make a pause here and mention that this stuff that we're working here with physical plans is actually pretty hard and advanced already. Maybe less than 10% of Spark engineers actually know this stuff, and I really want to make sure that I give you guys the skills to succeed with Spark truly by knowing some Spark internals, even though this is just an essentials course. So if you're still following along, I'm really proud of you, and I also thank you for listening. I know the Rock the JVM students are always the best, so let's just carry on. All right, so we did a join here, and we have a pretty big explain plan. Now, what do we do if we wanted to also aggregate this data set? So if I wanted to say joined dot select expra, and I would say sum of ID. All right, so we get a data frame. Now, let me attribute that to a value. Let's call this sum. And let me do sum.explain. Notice we have an even bigger explain plan. So after the actual join, which happened here at project, we have an hash aggregate, an exchange single partition. So this is the repartition, the shuffle that I was talking about earlier in the course when I mentioned the aggregation functions actually do a shuffle. And then we do a hash aggregate with step 5 over here with the functions sum with the column ID hash 22L, which we computed earlier. Now, if I run this job, so I do sum.show, this will take a bit of time because for every single exchange, for every single shuffle, Spark will do another stage. So we have sum ID equals null, which is pretty weird that we don't get a number here, but it might also be expected due to how I chose the numbers. So the first data frame, the first data set actually was numbers 1 to a million, 1 to 10 million in steps of 5. So we have multiples of 5 plus 1, and then we're doing select expra with ID times 5 as ID. So we're doing a join with multiples of 5 and multiples of 5 plus 1. So that's probably never going to happen. It's not really relevant anyway. If you picked some different numbers and you got a different value for sum ID, that's totally fine as well. I'm interested in how Spark actually figured out how to execute that job. And we'll notice here that we actually have 2 jobs, not 1. So let's take a look here. That's job ID equals 5. We have run at thread pool executor Java. Let's click on that. So we have a DAG with 2 stages. The first stage has 6 tasks, and then the second stage has 7 tasks. If we look at the explain plan, that will correspond to these 2 steps over here, the range and the exchange round robin partition with 7. Everything else was computed in the other job. So let's go ahead and figure that out. So let's click on this guy, and we see the DAG has 3 stages this time around. We have the initial Spark range with 6 partitions, and then we repartition it to 9 partitions, and then we have a single task over here. So why does that happen? Well, we can go back to the physical plan and we can explain that. So we have the first stage with 6 partitions over here, and then the repartitioning to 9, and then all the way up top we have an exchange single partition all the way to the top. So this is the single task in stage number 10 that I have over here, which is the 3rd stage of the job. So not only did Spark decide to split this whole plan into 2 separate jobs, but Spark also did some clever optimizations behind the scenes to eliminate one stage altogether, because you might notice from the join we have another exchange, which should have triggered another stage. But because I'm doing a sum, Spark decided to eliminate that stage altogether before running the job. Now, if you want to see everything that Spark has planned before running the job, you can call the explain method, so sum.explain, with the argument true. And what you get here is the following. You get a parsed logical plan, which is an initial version of what Spark will execute, then an analyzed logical plan in which it figures out which functions you want to actually evaluate on the data frames or data sets that you want to compute on, and then it will optimize these operations. So notice we have a range, a repartition, a range, repartition, and project, which is the select expra. Then we have a join, and then we have another project. And then finally we have an aggregate. So this is the optimized logical plan. And the physical plan is the actual set of operations that will be executed on the cluster. Now, if this pile of information with physical plans and logical plans and all these operations is too much for you and overwhelming, that's totally normal. All right, I'm talking advanced stuff already. This will become second nature to you as you run more Spark jobs and as you dive deeper into Spark jobs. Now let me do a very similar but different example. Let me create a data frame from an RDD this time around. So I'm going to say val df1 as sc.parallelize 1 to 1 million. So this is an RDD, and then I'm going to call 2df. And then I'm going to say repartition 7. So I'm creating a data set of row, which is a data frame, which has a single column called value. So if I'm doing df1.explain, I have a scan, which is the sc parallelize, and then serialize from object and the exchange round robin partitions, which is basically the repartitioning. All right. Now let me do another data frame. So df2 as sc parallelize, say 1 to 100,000 or something like that. 2df repartition, let's say 9. So we have another data frame. Now let me do df3 to be df1 dot select expra. And then I'm going to do the same thing that I did earlier. I'm going to multiply each value by 5. So I'm going to say value times 5 as value. Notice that the column name is value this time around. All right, so I have a data frame here. Now I'm going to do a join. So I'm going to say joined 2 as df3.join df2 on the column value. All right. I have another data frame. And let me do the sum of this joined data frame. So sum2 equals joined dot select expra sum value. Now I don't have the value column. This is because, I have joined instead of joined 2, which I created here earlier. So let me clear the screen. Let me create val, let's call this sum3 as joined2 dot select expra sum value. All right, so I have a data frame, sum value of big int. Now let me do a sum3 dot explain, and notice we have a bigger physical plan this time around. Let's go ahead and actually run sum3, and then let's explain the execution of the job based on this physical plan. So let me do the following. I'm going to say sum3.show. So this will start an actual Spark job, and notice we now have an actual number because the join contains some numbers which Spark can sum up. Now, if I go to jobs, we notice here that we have a single job with a huge DAG and with a big number of stages and some various numbers of tasks. Let's go about explaining this stuff. Now, the first two stages, stage 16 and 17, are the creation of the RDD and the transformations of those RDDs to data frames. So when we did sc.parallelize and then 2df, this is what we obtained in stage 16 and 17. The next two stages, stages 18 and 19 in my screen, we have the actual repartitioning of the data frames. So the smaller stage, which I have stage 18 here, we have the repartitioning to, well, we had 9 partitions in this explain plan, and the other stage, stage 19 on my screen, we have both the repartitioning to 7 and the select expra, which is done in the same stage, which is why this stage has actually 3 operations instead of 2. So I hope at least the first 4 stages of this job at least makes some sense, and the directed acyclical graph, the DAG here, shows the dependencies between the first and third stages and the second and fourth stages in this job. Now, the 5th stage is probably the most confusing, and I hope you're at least somewhat confused by this stage. So let's go about explaining this. So the first step in this huge stage is an exchange step. So this is a shuffle, and the number of partitions that Spark will choose is 200. This is the default value, and both data frames incur the same operation, exchange hash partitioning and exchange hash partitioning over here. So this is why we have these two branches over here in the same stage, because both data frames are being repartitioned in the same stage. Now, Spark figured out that the join is in between some numerical columns, so it will do a sort operations on both data frames. So we have sort here on both before doing the join. You probably know, if not from computer science, at least by intuition, that joining two sorted sets of values is much faster than joining non-sorted values, which is why Spark does these optimizations for us in this second layer here in our stage. And then it will do the main join, and then it will do a repartition. So this is why in the stage 20 that I have here on my screen, we have 200 tasks, because the data frames are split into 200 partitions and they're being sorted inside 200 partitions. So this is why we have 200 tasks, and they're being sorted and joined in parallel. Now, in the final stage, we have a repartition, which is explained by this exchange single partition over here. And then all the values are summed up into a single value in this final stage that I have here with the ID 21 in a single task. So if at least some of the stuff that I've talked about in the last few minutes is still confusing, that's normal, all right? This is hard stuff, and very few engineers don't even come close to analyzing this kind of job. But at least you have some intuitive sense of how Spark decided to split these jobs into stages and tasks. With time and practice, this kind of analysis will become second nature to you, and you will be able to debug and analyze any Spark job of any magnitude. All right, so let's do some recap of what we learned in this video. This was pretty hard. So we learned how to use Spark Shell as an interactive Spark REPL. So this is how you can do ad hoc analyses on any data frames that you like. We also saw how to use the Spark UI to investigate and track jobs. And we discussed the anatomy of Spark jobs with various examples of increasing complexity. So we saw that Spark jobs are split into stages, which is whatever happens in between two shuffles. This is a series of computations in between two shuffles. Then we saw that every stage has tasks. A task is a unit of computation per partition, and we saw how the number of tasks was computed for every stage in our various jobs. Then we saw the directed acyclical graph, which is the graph of RDD dependencies, and we saw that this DAG can get pretty big pretty quickly. Then we saw firsthand how Spark does various optimizations and generates various steps. It can even decide to split a job in between multiple jobs, or even eliminate stages altogether if an operation can be optimized. And finally, we saw physical plans, which describe all the steps that Spark will execute before running any code on the cluster. You saw that physical plans are pretty hard to read, at least at first glance, but as you become more experienced with Spark, physical plans will become second nature to you. So you probably got into this lecture thinking, man, this is the Spark shell, this is pretty easy. Man, Spark is a beast, and hopefully you got a taste of what it takes to actually dive into the Spark internals. I'm Daniel, and I will be waiting for you in the next video. All right, welcome back. I hope you're ready, because in this video I'm going to teach you how to deploy and run a Spark application on a cluster. So my objective for this lecture is going to teach you the anatomy of a Spark cluster and how an application actually runs on a cluster, and how to deploy a Spark application directly on our local Docker-based cluster. Now, when we're talking about a cluster, we're talking about the infrastructure where Spark actually runs its job. And a cluster is kept in place by the Spark Cluster Manager, which is a series of processes. Each process is started on a separate machine in the cluster. One of the processes is called the driver and will manage the state of the entire cluster. The other processes will perform the actual work related to the job. So if you want a very geeky visual description of how a cluster looks like, it probably looks something like this, where the blue square in the picture is the Spark Cluster Manager node, and the green boxes are the workers that actually perform the work. As of this recording, Spark supports 3 cluster managers: Standalone, Hadoop Yarn, and Apache Mesos. Each of these cluster managers is probably big enough to warrant its own course, but we will launch most of our jobs in standalone mode here on the Docker Spark cluster, and later I will show you how to launch a real-life Spark application on Amazon. Now, on top of this cluster infrastructure, we have Spark-related notions. First of all, let's talk about the Spark driver, which is a process that manages the state of the stages and tasks of a running application, and this interfaces with the cluster manager. Then we have the notion of Spark executors, which are processes that are running on the cluster, and their sole job is to perform the tasks assigned by the Spark driver and report back their state, if success or failure, and the results, if they have any. So you can imagine the Spark driver and executors running a configuration that looks something like this, where the red dot in the picture is the driver and the yellow ones are the executors. So we have the notion of Spark driver and Spark executors. Now, confusingly, we also have the notion of cluster driver and cluster worker, so make sure you do not confuse the concepts. Now, the way that the dots in the picture are going to be deployed on the boxes in the picture is the subject of the next few minutes. So, let's talk about execution modes. So we have 3 possible execution modes in which we can launch a Spark application. We can launch an application in cluster mode, in client mode, and local mode. I'm going to discuss what each means right now. So, in the cluster mode, the Spark driver, you remember the red dot, is launched on a worker node on one of the green boxes in the previous picture, and the cluster manager is responsible for the Spark processes. So if we bring back our small cluster, then the Spark driver and the Spark executors will all be launched on the green boxes, on the cluster workers. And all communication between the Spark driver and the Spark executors will be done inside the cluster, and the cluster manager will take care to run the processes correctly. Now, the client mode is where the Spark driver resides on the client machine executing the submit job. So the client is responsible for the Spark processes and state management. What do I mean by that? Assume we have a clean cluster, then if we want to deploy a job in client mode, then we need the client machine on which we actually run the command. So the client machine will actually talk to the Spark cluster manager, and after that it will spawn the Spark driver on the client machine, so not on the actual cluster. And then the Spark cluster manager will take care to spin up the executors on the worker nodes. And after that, the Spark driver will start to communicate with the Spark executors residing on the cluster. Now, the local mode is the least interesting of the 3 execution modes because the entire application runs on the same machine. So you have as much parallelism as many cores you have on your computer. Now, as I get back to our favorite project in the course, I created here the Part 6 practical package for this chapter, where I created the Spark Job Anatomy application for the previous lecture, so you can check out the code that we wrote in the previous lecture where we investigated the Spark shell and the deconstruction of a Spark app. Now, under this Part 6 practical package, which I invite you to create on your own project, I will create a new application as a test application to deploy on a local Dockerized Spark cluster. So I'm going to name this test deploy app. And let me create this an object, and I will not do extends app at the end because I will do a def main with args as an array of string. I will need the command line arguments for reasons that will become apparent shortly. Our goal for this lecture is to package this whole application and run the test deploy app on a cluster. So we will need this main method, which will take command line arguments. And the example application that I'm going to run will be the following. Let's assume we have the movies JSON as args0, and I will compute the good comedies from movies JSON, and I will write it into a new data frame, good comedies.json, in the path denoted by args1, so as args1. And by good comedy, I mean the genre needs to be comedy and the rating needs to be above 6.5. All right, so let's do the following. Let's first, in this main method, check for the args length, and let's make sure that the args length is exactly 2. So if args dot length is not equal to 2, then let's print line need input path and output path, and let's do system.exit1. And after we make sure that the arg's length is exactly 2, let's start a Spark session. So val spark equals spark session dot builder dot app name, and let's give this an app name, test deploy app. We will not configure the Spark master to be local. We will pass that as command line arguments to Spark submit shortly, and then get or create. Then let's read our input data frame. So let's say val movies df as Spark read option to infer schema to true, and then JSON to args 0. Now, having this movies df, let's select the good comedies. So I'm going to say movies, let's say val good comedies df as movies df dot select, and let me import the functions. So import org apache spark SQL functions, and I will use the column title, then the column rating, so IMDb rating, and I will give it an alias rating, and the column, let's call this release date as release, just for the extra data, just to keep track of the age of the movie. And let's put in the where filter, so where column major genre must triple equal comedy, and the column IMDb rating must be above 6.5. Now, I would like to sort the data frame by rating descending, so I'm going to say order by column rating desk with nulls last. Now, having written that, let's go ahead and show this. So say good comedies df.show, just to see this in the console as well as in the file. And then we are going to write this to the file denoted by args1. So I'm going to say good comedies df.write.mode save mode.overwrite, and then I'm going to say .format JSON, and then I'm going to call save at the path denoted by args1. All right, so this is our whole application that we are going to deploy on our Dockerized Spark cluster. So we are reading the data frame from the first command line argument, then we're doing a select, then we're showing the select to the console, and then we're writing the output to the path denoted by the second command line argument. So this is pretty simple. Now, in order to deploy this application to a Spark cluster, we will need to package this whole project into a jar. If you've worked with Scala, Java, or IntelliJ, you've probably packaged jars before. So let's go ahead and package this whole project into an executable jar. So we will go to File and then Project Structure in IntelliJ, and this dialog, this huge dialog, will pop up. We will go to the Artifacts menu here on the left, and we will click on this plus to add a jar. And once you get into this menu, click for Modules with Dependencies. The second pop-up will come up, and we will select Spark Essentials from the first selector. We will leave the main class open, and we will check Copy to the output directory and link via manifest. This is important for executing the jar. Now, in the path that IntelliJ has generated for me, I will delete everything after source, and then click OK. If you have more complex build configurations in your IDE, feel free to use those. This is the simplest that I could find. Now, we will click on Apply and then OK. So once you've done that, go to the Build menu at the top at IntelliJ and click on Build Artifacts. Once you click that, a small dialog will pop up with a single option with Spark Essentials : jar. Click on Build. This will take a bit of time for the compiler to actually recompile all our sources into one single jar. And if successful, we will see here an output folder, an orange one in my video, which has an artifact subfolder and a Spark Essentials jar folder with a lot of jars. These are all the jars that we are including in our application, as well as a huge jar which includes them all in one, the spark-essentials.jar. Spark-essentials.jar contains all the code that we wrote in the entire course, plus all the libraries that we can use. So I want you to copy spark-essentials.jar with Control or Command C, and then copy it right at the top inside the Spark cluster folder, inside the apps subfolder. So paste it here and click OK. So copy and paste the spark-essentials.jar inside the apps subfolder in the Spark cluster Docker container. I will explain what this means in a second. We will also need to copy the movies.json input data frame into the data folder here in the Spark cluster. So I'm going to go to source main resources data, and I will copy the movies.json. So I will do Command C, you can do Control C if you're on Windows, and paste it under the data folder here under Spark cluster. So hit OK. All right, so we have here under Spark cluster, we have two subfolders, apps and data. The apps contains spark-essentials.jar and the data folder contains movies.json. Now, what's with these two folders? These two folders are mounted in the Docker containers as spark-apps and spark-data. This is specified in the Docker Compose YML. So if you take a look at here under volumes for both Spark Master and Spark Worker, you will notice that the apps folder is mounted in the Docker container as /opt/spark-apps, and the data subfolder is mounted as /opt/spark-data. So this is an easy way to copy the jar and the input data to the Docker containers without actually going to SSH and SCP and doing some complex maneuvers to ship the data to the Docker containers. Awesome. So now that we're on the subject of the Spark cluster, navigate to a terminal window in your computer. So start up a couple of terminal windows or terminal tabs on your computer and navigate to the project folder, to Spark Essentials. And in one of the terminal windows that you have open, navigate to Spark cluster and start up the Spark cluster in much the same way as we did in the previous video. So docker-compose up --scale Spark worker equals 3. If you have the Spark setup already started up, just leave it open. Otherwise, just start it now, and it will take a couple of seconds for the Spark cluster to start up. All right, so our nodes were registered, which is fine. And in another window, go to docker exec -it, so -it, spark-cluster _spark-master_1 and then bash, in much the same way as we did with the previous video. So we have a shell here under our master Docker container as root, and if we navigate to /opt, we will see the spark-apps and spark-data already mounted here in the Docker container. So if I do ls spark-apps, then I have the spark-essentials.jar that I copied earlier in the project. So notice that the spark-essentials.jar is already present in the Docker container. Now, given that we have the jar and we have the data here under spark-data, so movies.json, all we have to do is actually execute this jar. And we will execute that with a command known as spark submit. So navigate to /spark. And under /spark, if you do ls bin, we will see here all the binaries that we can operate on. So we saw Spark Shell and Spark SQL earlier in the course. Now we will do spark submit. So here's what I'm going to do. I'm going to say spark, so /spark submit. And the spark submit is a big application and it will take a large number of command line arguments. So type after me. I'm going to say --class, and I'm going to put in the fully qualified class name of the class that I want to execute. In my case, I want to execute the test deploy app. So that's under part 6 practical. So I'm going to say part 6 practical dot test deploy app. All right, so this is the class name. All right, now I'm going to say dash dash deploy dash mode client. So I'm going to deploy this in client mode. I'm going to say dash dash master. And normally I would say local if I wanted to deploy this in local mode, but I'm going to put in the Spark URL of the master node here. So I'm going to copy this identifier and I'm going to say spark : / I'm going to paste the Docker identifier and then : 7077. So this is the Spark URL for the master node. Previously in the course, we always did master local directly in the code, but this is how we can configure Spark master here in the command line. So our spark.master in this case is the URL of the node, which will be the master node in the cluster. So the Docker identifier : 7077, and then I will pass some additional command line arguments. I'm going to say dash dash verbose and dash dash supervise. And then I will put in the jar that I want to submit to Spark. So I'm going to put /opt/spark apps /sparkessentials.jar, and then the command line arguments for the jar, for the class. So in my case, I have movies.json, and then the path where I want to write the output data frame. So the input data frame is at /opt/spark-data/movies.json, and the output data is going to be /opt/spark-data, and then I'm going to name this good comedies. And this will be the place where Spark will write the output data frame. Remember, when Spark writes a data frame, it will store this as a folder and it will put each partition as a JSON inside. So I'm going to hit enter now. Oops, I've made a mistake. This command is really big. So Spark submit is not present in the /spark folder. It's actually ./bin/spark submit. So I'm going to hit the up arrow to bring up my previous command, and then I'm going to navigate to the start of my command by Control-A, both on Mac and Windows. This is a little trick to edit the beginning of the command. So I'm going to say ./bin/spark submit. And now I can execute. So these are all the configurations of Spark, and now we're starting a Spark session, which will actually run our Spark job. This shouldn't take really long. So we're actually running this job on the Dockerized cluster. And because the job is short, the Spark job here will terminate pretty quickly. All right, so clean the accumulators, and we should already be good. So finish task in stage 4. All right, good. So we notice here up top that we have the table shown as instructed from our code. So we said goodcomedies.show, and we see here the title, the rating, and the release. And we see here that the movies are rated descendingly, are sorted descendingly by rating. And because I started the job in verbose mode, you can inspect here all the information that Spark can spit out while executing this job. So we see here that all the configurations are being shown before Spark actually starts. The class path and the Spark configuration. So look at this. The Spark master is actually the path, the URL of the Docker container. So it's not local this time around. We're running on an actual cluster. And we see here every single step that Spark actually does to compute this data frame for us. And at the end, we're writing it to a file. So we should navigate to the file. So let's do cd/opt/spark data. And if we hit ls, we have the good comedies directory over here. So if we navigate to it, we see here the JSON partitions of this data frame. So this is pretty cool. Now, because the good comedies folder is stored under /opt/spark data, this will be automatically reflected in our project because it's mounted into an actual folder on our computer. So under the data, we have the good comedies folder already reflected here in our project. So we can inspect here all the JSON files that Spark wrote for our job. This is pretty cool. All right, so congratulations for sending your first Spark application to an actual cluster. Let's recap what we learned because this lesson is pretty important. So we learned about the Spark Cluster Manager as an infrastructure for running applications, and we learned about the driver node and worker nodes as the components of this cluster. We learned that the Spark Cluster Managers can be in 3 forms at the moment of this recording, so we can launch a Spark application in standalone mode on a Yarn Cluster Manager or on Apache Mesos. Then we learned how Spark applications are actually being deployed on a Spark cluster, and we saw how a driver process controls many executors that are actually performing the work. And we saw that there are many ways in which we can deploy the driver and executors onto an actual Spark cluster. So we can deploy Spark application in cluster mode, in which the driver and executors are launched on the cluster. We can launch an application in client mode in which the driver process is launched on the client and executors actually perform the work on the cluster. Or you can deploy this locally, which is what we've been doing in this entire course up to this chapter, where everything runs on the same machine. Also, we deployed our first Spark application to an actual cluster. So we packaged a jar, we shipped it to the cluster, and we submitted the jar to Spark using the Spark submit command. As you saw earlier, the Spark submit command is a big one and takes a lot of command line arguments. And I've highlighted the command line arguments and the various configurations that we can put into Spark submit here on the screen. I'm also going to put it in the code for your reference when you get back to this lecture. So congratulations again for submitting your first Spark application on an actual running cluster. The techniques that you learned in this video will apply whatever cluster you use in production. Now join me in the next video where we are going to start doing the hard stuff. All right, this is it. Welcome back. In this chapter, we'll put everything that we learned in this entire course to the test, and we will do our first truly big data project. So starting in this video, we will run a project that will involve some real big data, and we will do everything from scratch to finish, from data gathering to investigative analysis and answering questions and gathering some data insights, to packaging an application and then running it on Amazon EMR. Now, I'm really excited about this project, so let me tell you a little bit about it. So the scenario is as follows. The New York City taxi company want to improve their business, and they hired you, the newly appointed lead Spark and big data engineer, to advise them. In order to improve their business and in order to help you accomplish your job, they will put the following data at your disposal. They will give you all the taxi rides that they've recorded between 2009 and 2016. Now, with this data, they will ask you to do the following. You're required to gather some insights about this data, and if you spot any patterns that might help them in their business, either by growing profits or reducing environmental impact or anything that might help them. Also, to make some proposals for business improvements, so not just to gather some patterns, but actually give them some advice. So you would make some proposals and suggest one that would maximize their impact and evaluate that impact over the existing data so that you can paint a picture of how the future might look like. Now, you might be wondering, how much data do we have? So we have all the taxi rides between 2009 and 2016, totaling almost 1.4 billion taxi rides, billion with a B. In terms of storage, that comprises almost 35 gigabytes of snappy parquet, which is compressed. If you uncompress it and store it as CSV, that will total almost 400 gigs of uncompressed CSV, so we're talking half a terabyte of data. This is breaking the big data barrier because 400 gigs is more than can fit on most computers. So this fits the big data definition that we said at the beginning of the course. To my knowledge, this is one of the biggest publicly available datasets in existence. So I wasn't kidding when I said that this course is the only truly big data course on the web. Now, if you're curious about how this data looks like in a plotted fashion, a really smart guy called Ravi Shekhar actually took the time to plot this data on a map, and it looks absolutely stunning. Now, how can you get this data? Well, you can search online for NYC taxi data, and you can click the first link that pops up, the TLC trip record data on nyc.gov. So this is all the data that the NYC Taxi and Limousine Commission has made available to the public. So this is real life big data available publicly. And they've recorded data all the way up to 2019. And at the moment of this recording, we have data available up until June 2019. And the data will probably still grow. Now, the reason why we don't analyze the whole data up to 2019 is that the data is not 100% consistent, and it might break our analyses, which is why the smart guy, Ravi Shekhar, with the amazing visualization a minute ago, also took the time to clean the data and make it available in compressed snappy Parquet format as an academic torrent. So you can open another browser tab and you can search academictorrents.com, and here in the upper right hand side where you can search for data, just search for taxi. And you have here the New York taxi data 2009-2016 in Parquet format. And the size of this torrent, the size of this data is 35.08 gigs. So if you want to analyze the entire dataset on your computer, you can download this torrent. It's still active, and I'm also a seeder on this academic torrent. So if you want, you can download this entire dataset. 35 gigabytes is big, but it's not so big for 2019. There are games that are bigger than this. So if you want to analyze this whole thing, just click on download and wait until it's finished. Now, if you still want to go through the course, I have a small partition of this data here under Yellow Taxi January 25, 2018, gathered from the main NYC website, and I've cleaned this in Parquet format. So we have here two partitions for a single day out of all the data, so we can run our analyses on it. Additionally, I will ask you to download a file from the official New York City website. So when you hit this website that I mentioned earlier with NYC.gov, where the main dataset is located, there is a small CSV file called Taxi Zone Lookup Table, CSV. I want you to go ahead and download this file and then copy it in your project. So copy it under source main resources data. If you want, you can rename it because the name is pretty funky. So I'm gonna go ahead and refactor rename. I'm going to name this taxi_zones CSV. All right, now let's go ahead and create a new package specifically for this chapter because I want this project to stay in its own package. So under source main Scala, go ahead and create a new package. I'm going to name this part 7 big data. And under part 7 big data, I'm going to create a new Scala application called taxi application. Make it an object, extends app, and let me go ahead and read these data frames. So I'm going to read the Yellow Taxi January 25, 2018, so the single day data frame, the Taxi Zones data frame, and I'm also going to read the actual big data frame that I have downloaded on my computer just to give you a comparison and prove the number of taxi rides that we are going to analyze in this project. So first of all, I'm going to start with my usual boilerplate. So val spark equals spark session builder config spark master with local, and then app name taxi big data application, and then get or create. Now, let me go ahead and read the single day data frame. So I'm going to say val taxidf as spark read, and then I'm going to simply load the data frame at the path source main resources data and yellow underscore taxi underscore January underscore 25 underscore 2018. I'm going to use the load because the data is already in the default Parquet format. So I'm going to print the schema of this data frame. I'm also going to count the number of entries in this data frame. So let me do taxidf.print schema and then print line taxidf.count. Let me go ahead and run this just to warm up. Give it a few seconds to compile, another few seconds to run. The small data frame is actually small enough that Spark can compute this in roughly 1 second. And we have the schema here, which I'm going to explain in a second. And we have in this single day data set, we have 331,000 taxi rides in a single day. Just to give you a comparison, let me create the big taxi data frame. So taxi, let's call this big taxi df as Spark read load. And I'm going to load that from the location where I downloaded my big data frame. So I'm going to say /users Daniel downloads. And the folder name is NYC taxi 2009-2016 Parquet. If you downloaded the big dataset, if you pause the video in the meantime and you downloaded the dataset, you will probably have a folder that looks something like this. Now, just by comparison, I'm also going to print line bigtaxidf.count. All right, and let's go ahead and see how many taxi rides we actually have. So this will take a bit of time, but not too much because Spark is pretty quick and I have a fast hard drive. So we have, let's read this number. So we have 1,382,375,998 taxi rides. So this is at the point where we cross the big data boundary. When you have a billion data points rather than a million data points over a 20 megabyte data set or something, this is actually big data. So uncompressed, as I mentioned earlier, this is 400 gigs of uncompressed data. So let me go ahead and remove this count and leave the big taxi df as a lazy data frame. And let's load the taxi lookup zones, the taxi zones here, just to print its schema. So I'm gonna say val taxi zones df as Spark read, and the taxi zones being a CSV, I will need some options here. So I'm gonna say option header true, because the CSV here has a header. So let me get back. So option header true, and then option infer schema to true, and then CSV at source main resources data and taxi zones dot CSV. Let me put the dot where it should be. And let's also print the schema of the taxi zones df. So let me remove the count and let's say taxi zones df.print schema. And we will start describing the data frame shortly. All right, so what do we have here? We have a big schema for the taxi df, and I will explain what each of these relevant columns means. And here under the taxi zones df, we have the location ID, the borrower name, the zone name, and the service zone. I will explain what the schema means right now. All right, so before we embark on this huge project, it's worth understanding what the data is and what it means. So as I mentioned earlier, we have a big data frame containing 1.4 billion rows between 2009 and 2016. But what are the columns and what do they mean? So we have a bunch of columns. We have for every taxi ride, we have the pickup and drop-off date times. So we have the timestamps for pickups and drop-offs. We have the passenger count. That means how many people were in the ride. We have the trip distance in miles. Then we have a rate code ID, which describes the conditions under which the taxi ride is going to be paid. And we have most taxi rides being on the standard rate code ID, a couple of rate code IDs for airports as well. Then we have the pickup and drop-off location zone IDs. Then we have the payment type, which is credit card, cash, no charge, dispute, unknown, and voided, which we are going to analyze later. Then we have the total amount, which is how much money the taxi ride was worth. And then we have other columns that are not really relevant for our analysis. Then we have a smaller data frame with the taxi zones, which I described earlier. And then we will join the big data frame with this smaller data frame under the location IDs for pickup and drop-offs. Now, we will get familiar with this data as we go through our analysis. So here are the questions that we will start to ask in this big data project, and we will ask quite a bunch of questions. First of all, which zones have the most pickups and drop-offs overall? This is worth investigating because if you have some more popular zones and some not so popular zones, it'll give you a sense of whether you should incentivize other people to use the cab as well. Second question, what are the peak hours for taxi? If there is any way you can measure demand, then you can start to experiment with some price surges in the style of Uber. How are the trips distributed, and why are people taking the cab? This is a very important question for any company at all. Why are people using your product? If there are many people that are using the cab for different reasons, maybe we can segregate the market segments and then we can tailor the services to them. What are the peak hours for long and short trips? If there is some such segregation, maybe we can tailor the services depending on the demand for long and short trips by the time of day. What are the top 3 pickup and drop-off zones for long and short trips? So not just the most popular drop-offs overall, but rather for long and short trips. How are people paying for the ride on long and short trips? What payment method are they using? Are they using cash? Are they using credit card? And how is that evolving over time? And finally, can we explore a ride-sharing opportunity by grouping close short trips? We will see later that this last question can have some really big impact. So these are the big questions that we are going to analyze on this big data set. So let's go ahead and analyze this data starting in the next video. All right, let's get to it. It's time to write some code that will actually analyze our big data set for taxi. So I am back in our very favorite project, and in the taxi application app that we created in the previous video, I attached the questions that we asked at the end of the last lecture, and we are going to attempt to answer these questions in this video. So let's get refamiliarized with the schemas of the data frames, just to remind ourselves of the data that we're working with. And we have the schemas for the big data frame for taxi and the schema for the taxi zones. Now, for the first question, which zones have the most pickups and drop-offs, we will join the big data frame by the pickup location ID, which is an integer, and the foreign key in the other data frame is going to be the location ID. And we're going to fetch the data related to those locations, to those taxi zones. So here goes. I'm going to do the following. So for question 1, I'm going to create a data frame, let's say pickups by taxi zone df as the following. I'm going to say taxi df dot group by, and I'm going to group by the column called pickup location ID, and then I'm going to call the ag function because I'm going to count star. Let me import the count function. I'm actually going to import all the functions. So import org Apache Spark SQL functions. So I'm going to count everything, and I'm going to give this guy a name as total trips. And I will have an aggregate of total trips by location ID, which is still an integer. I will need to join that with the taxi zones df. So I'm going to say join taxi zones df under the condition that column called pickup location ID must equal column of location ID. Then I'm going to drop the irrelevant fields in the taxi zones df. So if we go to taxi zones CSV, I'm going to drop service zone and location ID because it's a duplicate column. So I will drop location ID and service zone. And because I'm looking for the most pickups, I'm going to sort by this total trips descending. So I'm going to say order by column total trips dot desk nulls last, although we don't have nulls in this data set. So again, what are we doing here? We're grouping by the location ID, which is an integer, and we're counting the total trips by the location ID. And then we're joining with the taxi zones df by this location ID. So we're fetching the location information of each location identifier, and we're dropping the irrelevant columns, and then we're ordering by the total trips. So let's go ahead and show this data frame. So I'm going to say pickups by taxi zones df dot show. So let me go ahead and run this application with the first answer to one of our questions. All right, so we're printing the schemas, and Spark is actually doing some work, and we have the location ID, and we have total trips, and we have the borough. And notice here in the first 20 rows that Manhattan absolutely dominates the popularity contest here. And if we look at the data, we see here at the top, we have Upper East Side, South, and North, Midtown Center, and a few others that are some of the higher end zones of Manhattan. But obviously Manhattan dominates. But it's probably an interesting question to group this data frame by borough as well. So for us to see how much Manhattan is more popular than the rest of the boroughs in New York. So let's do a 1B to group by borough. So I'm going to do the following. I'm going to say val pickups by borough as pickups by taxi zone, and then I'm going to group by the column called borough. So I'm going to group by borough, and then I'm going to sum the column called total trips. So I'm going to say ag sum of the column called total trips, and let's give this guy a name as total trips. And let's do the same order by. So order by column total trips with desc nulls last. Let's also do a show on this pickups by borough. So pickups by borough dot show. And let's rerun the application. Give it a few seconds. Spark will actually run some computation to crunch the numbers. All right. So we have borough and total trips sorted descending. And you see here that Manhattan absolutely dominates the entire ranking by an order of magnitude over everything else combined. So as we see here, the data is extremely skewed towards Manhattan. There are multiple ways we can go with this data analysis, but one proposal that comes right off the bat is to try to differentiate the prices according to the pickup and drop-off area and by demand. So because the data is absolutely dominated by Manhattan, you could try slightly increasing the prices for Manhattan because it's so popular, and slightly decrease the prices for the other boroughs, and thereby incentivizing the other people of New York to use the cab more. All right, back to our data analysis. So we can kill the shows here. And let's try to answer the second question. What are the peak hours for taxi? So we'll probably do a similar group, but we need to extract the hour. So let's do a group by hour of the day. And we will extract the hour from the pickup date time. So just the time of day, the hour of the day. And then, of course, try to sum up all the taxi rides by hour. So let's try to do that. So let's say val pickups by hour df. To be the following, taxi df, and let's add a column. So let's say with column, and I'm going to call this hour of day to be hour of the column called tpep underscore pickup underscore date time. All right, then let me go ahead and group by hour. And let's do a similar aggregation with count star as total trips. Okay, now we don't need to join with the taxi zones df. Instead, we can simply sort by this total trips column. So I'm going to say sort by, or order by column total trips, and then do a descending with nulls last. And that is our data frame. So let's go ahead and show it. So I'm going to say pickups by our df.show, and let's try to rerun our application. The code should compile pretty quickly, and Spark should run just this show because, okay, we have a stack trace. Cannot resolve column name hour. Well, it's true because it's not hour, it's rather hour of day. So I'm going to group by hour of day. So let me go ahead and rerun this thing again. All right. Let's give a few seconds to actually process this data. And we have an answer here that the peak hour of the day is 18, 19, 21, and 20. So it's more like 18 to 22. So between 6 and 10 p.m. in the evening, we have the most trips. Another closely peak hour is 8 p.m., probably for people that are going to work. And then if we take a look at the difference between 5 p.m. and 6 p.m., we notice a sharp almost 4,000 trips difference. So it's 10 to 15% sharp increase in between 5 p.m. and 6 p.m. So we notice that there are some clear peak hours with increased demand for our cabs. So another proposal that we might go for with this data analysis, should we choose so, is to try to differentiate the prices according to demand, especially in early morning around 8 a.m. and in between 6 and 10 p.m. in the evening. So we have a second proposal for our data set. The third question that we might want to ask is, how are the trips distributed? Now, this is a pretty vague question. I'm pretty interested in how the trips are distributed by length. That is, by trip distances. Why are the people taking the cab by long or short trips? Are they taking it for work? Are they taking it to go to a bar? Or are they doing it for some other longer journeys? Specifically for long trips, because the airports in New York City are pretty far apart, so we might expect some longer trips if people are taking the taxi in between airport locations. So let's do the following. So I'm going to do question number 3, and I'm going to do a statistic based on the trip distance. So I'm going to first create a data frame containing just the trip distance, so trip distance df, as taxi df dot select column, let's call this trip underscore distance. This is the name of the column, and let us use a shorter alias as distance. Now let's consider that a long taxi trip is about, let's say, long distance threshold around 30 miles. 30 miles is just enough to cross New York City. So beyond 30 miles and you're talking about a long trip. So let's assume that 30 miles is our threshold. Now, I'm going to do a statistic on this trip distance df. So I'm going to say val trip distance stats df as trip distance df dot select. And I'm going to do the following. First, I'm going to count the instances. So I'm going to count star as count. Then I'm going to insert this reference, this threshold, as a literal. So literal long distance threshold as threshold. And then I'm going to do the very standard statistics, mean, standard deviation, min, and max. So I'm going to say mean of distance as mean, standard deviation of distance as stddev, then min of distance as min, and max of distance as max. So this should be a single row data frame where we will analyze these numbers. So I'm going to say trip distance statsdf dot show. Let me go ahead and rerun the application and see what numbers we get. Not a few hours, hopefully a few seconds for this Spark job to execute. Okay, so we got 331,000 instances of trips, which is what we computed earlier. We have the threshold 30. We have the mean 2.71. So this is the average of all the taxi trips, 2.71 miles. The standard deviation is 3.48 miles. So the distribution of the length of the taxi trips is pretty spread out. The minimum is 0.0 and the maximum is 66 miles. All right, so we have some pretty long trips. Now, because the mean is actually pretty small, I'm expecting most trips to be short. So let's do the following. I'm going to say val trips with length df to be taxi df with column, let's say, is long. So this will be a Boolean column with the expression column of trip distance to be bigger than or equal to long distance threshold. Let me group the taxi with length df by this attribute. So I'm going to say val trips by length df to be trips with length df dot group by this column is long. And the aggregation function should be count. All right, so we're counting how many trips are long and how many trips are not long based on this predicate. So the isLong column will tell us whether the column trip distance is bigger than 30 miles, and then we're grouping by the isLong attribute. So let's do a trips by length df dot show. So let's rerun the app. And let's see how many trips that are long and that are short we have. Okay, so is long true, we have 83, and false, the trips that are short, we have 331,000, so almost the entire data set. Now, because we have so few long trips, it might not be worth exploring the questions 4 and 5 for long trips, but I'm going to do that anyway. So when you encounter in a data set, you encounter too few data points to actually answer some meaningful questions, you might want to trim them all together. But I'm going to do that either way. So let me compute the peak hours for long and short trips. So for this question, I'm going to use the logic that we saw earlier when we computed the peak hours by all the taxi, by the entire taxi data frame. But now I'm going to also use this additional isLong attribute. So I'm going to shamelessly copy the pickups by hour df. I'm going to paste it under question number 4, but instead I'm going to use the trips with length df, because the trips with length df is the taxi df with that additional column with the isLong property. And I'm going to name this pickups by hour df2, or df by hour by length df. Now there's something else that I need to change. I need to group by both the hour of the day and the isLong attribute. So I'm going to say isLong here. And then I can do a show. So pickups by hour by length df dot show. All right. Come on, Spark. Be fast. It's pretty fast already, poor thing. All right, so we have only the top 20 rows for false, that is for short trips. Let's show the entire data frame, and by that I mean all the 48 rows of it. Now, why do we have 48? That is because we have 24 entries for short trips and 24 entries for long trips. So I want to show the entire data frame. All right. Okay. So we have the entire data frame over here. Now, as expected, the long trips data is going to lag behind the data for short trips by 2 or 3 orders of magnitude. So the data is not really relevant. So it's not really worth pursuing the question of what are the peak hours or what are the top 3 pickup and drop-off zones for long and short trips. If the data was more relevant, or if you had more long trips in your data set, then it might have been a sensible question to pursue. But I'm going to be stubborn, and for question number 5, I'm still going to do the pickup and drop-off zones, the most popular pickup and drop-off zone pair for both long and short trips, because it's not that big of a burden. We just have the original taxi df with the attribute is long. So let me answer question number 5 with a pickup and drop-off popularity. So let me do the following. Val pickup drop-off popularity df as trips with length df. So this is the original data frame with the isLong attribute. Then I'm going to filter that, so where not column is long. All right, then I'm going to group by, and I'm going to group by the pickup location ID and the drop-off location ID. So if you go way up top, we see here that we have both a pickup location ID and a drop-off location ID. I'm going to group by both. So I'm going to say group by pickup location ID and the drop-off location ID. And then I'm going to aggregate to count star as, let's name this total trips. All right, so I have an aggregate to count all the trips by the pickup location ID and drop-off location ID pairs. So let me join the pickup location ID with the taxi zones. So I'm going to join the pickup location ID with the location ID of the taxi drop-off, the taxi zones. So I'm going to say join with taxi zones df under the condition that column pickup location ID should equal column location ID. And then we need to drop some irrelevant columns. So we need to drop the borough, the service zone. I'm only interested in the zone column over here. So I'm going to say with column renamed, and I'm going to name zone to pickup zone. All right, and then I'm going to drop the rest of the columns. So I'm going to say drop, and I'm going to drop the location ID, then the borough, then the service zone, then I'm going to join with the taxi zones df again. So I'm going to say dot join with taxi zones df under the condition that the column drop-off location ID this time around should equal column location ID. And I'm going to again rename the column zone, so with column renamed zone to be drop-off zone. And then I'm going to drop the rest of the columns as well. So what have I done here? I took the original data frame with all the taxi trips with the length attribute, and I filtered them so that they are short, so where not column is long. Now, I grouped them by both the location ID of pickup and both by location ID of drop-off. So I'm grouping by 2 columns, and I'm counting the instances of the taxi trips, and I named that column called total trips. All right, so right now I have a data frame with 3 columns, pickup location ID, drop-off location ID, and total trips. To join both of these columns with the taxi zones, which is why I'm having 2 joins here. And I'm doing both joins one at a time. So I'm going to say join with taxi zones df under the column pickup location ID, and then I rename the relevant zone to pickup zone, and I'm dropping everything else. And then I'm joining the taxi zones df again under the drop-off location ID this time around. And I'm renaming the zone to drop-off zone and dropping all the other columns. Now, because I'm done with the joining, I don't need the location IDs anymore, so I'm going to drop them again. So I'm going to say pickup location ID and drop-off location ID, because I have the pickup zone and the drop-off zone. That's all I care about. So I have pickup zone, drop-off zone, and total trips. That's what I care about. And then I will order by the column total trips, descending with nulls last. All right, so this is a mouthful, but I hope it makes sense. Now, let me do a show on this pickup drop-off popularity df. So I'm going to say pickup drop-off popularity df dot show. Do we have other shows? No. So Spark will only process this data frame. So let me rerun the app. And hopefully I have not misspelled any of these columns, because otherwise Spark will complain. It will take a bit of time to do joins again. So we have here a sorted data frame by total trips, grouped by pickup zone and drop-off zone. And notice that the most popular known zones are Upper East Side South and Upper East Side North, which are some of the wealthiest zones in Manhattan. Now, it's very easy to run the same computation for long trips as well. So I'm going to create a small method, def, let's call this pickup drop-off popularity with a predicate as a column object. And I will run this computation based on a predicate. So I will pass that predicate here. All right, and I will create two data frames, one for long trips and one for short trips. So I'm going to say pickup drop-off popularity with column is long. So this is for a data frame for long trips dot show, and pickup drop-off popularity by not column is long, which is what we did earlier for short trips. I'm going to do a show here as well. So does it make sense what I did here? So I extracted this big mouthful data frame into a method in which we have a predicate that I can inject over here. And the predicate was not column is long for short trips, for the data frame that we are just analyzing here in the console. But I can do the same thing for the isLong predicate, so for long trips. So I can rerun the application, and I can show two data frames now. All right. So we have one data frame for long trips over here. Look at that. So we have JFK Airport NA, LaGuardia Airport NA, so not available, JFK Airport to JFK Airport, so mostly airport transfers for long trips, and essentially high-class zones for short trips. So we can draw some conclusions from this data. So first, we notice that there is a clear separation of long and short trips, even though the long trips are significantly fewer by orders of magnitude. Despite that, we could draw some conclusions about how the taxi trips are being used. For example, the short trips are mostly in between wealthy zones, which we might lead to suspect that the taxi trips are between bars and restaurants in the wealthy areas, whereas long trips are mostly used for airport transfers. So in this light, we can forward a conclusion to the New York City Town Hall to construct, or at least think about constructing, an airport rapid transit service so that people don't need to take cars and taxis and Ubers between airports. And to the taxi company, it's always worth trying to separate market segments and trying to tailor services for each, especially if we start to notice an increase in the proportion of long trips in the data. Now we have a single day, but if we choose to go with this proposal, we might want to analyze the entire data set and see the progression of the proportion of long trips in our data. As for short trips, the taxi company could work towards striking a partnership with the various bars and restaurants in the wealthy areas to do a pickup service as part of a package. All right, so these are some of the questions that we have already answered in this big data project. Join me in the next video where we will answer the rest. All right, welcome back to the big data project. Let's continue. All right, so we're back to our project. And in the previous video, we answered the first 5 questions that we wanted for the big data project. In this video, we are going to answer the other 3. So let me go answer question number 6, which is how are people paying for the ride on long and short trips? If you remember, the method that people are used to paying for the ride is described by the rate code ID column. So all we have to do in this question is to group the data by the length attribute, which in the previous video you remembered I denoted by the isLong attribute, and I will also group by the rate code ID. So let me go to the bottom here and let me define a data frame called, let's say, rate code distribution df to be taxi df. So you can use the trips with length df, but I'm using the taxi df because we don't have that many long trips. So I'm going to say taxi df dot group by, and I'm grouping by the column called rate code ID, and I'm using the aggregate function to count star, and I'm going to give this column a name as total trips. All right, then I'm going to order by the column total trips, descending with nulls last. Let me put the dot where it should be. So this is our data frame. We're grouping by the rate code ID, and we're counting the total number of trips by each rate code ID so that we can see in the data which rate codes are the most popular. So this is pretty simple. Let's do a show here. So rate code distribution df.show. And let me go ahead and run the application again. This shouldn't take too long because the data is small. So we have here the rate code ID and total trips. And notice here that rate code ID number 1 is responsible for almost the entire data set. Now, I doubt you remember the meaning of the rate code IDs from the beginning of the project, so I will put them here on the screen. Now, rate code ID number 1 here is for credit cards, and rate code ID number 2 is for cash. So notice that credit cards are used for most trips. They're absolutely destroying cash by 2 orders of magnitude. So even from analyzing a single day of data, we can safely say that cash is dying. So a proposal, which is not really a proposal, but actually a warning, to make sure that the card payment processor works 24/7 for your taxi company, because even if you have an hour of downtime in your card payments, you might get in trouble with taking your payments. All right, so this is a pretty easy conclusion to figure out from the data, from 3 lines of code. Now, let's answer question number 7, which is, how is the payment type evolving with time? Now, given the amount of data that we have for a single day, we won't be able to draw any meaningful conclusions. The question here can safely be answered with many months of data so that you can track the progress of the rate code ID evolution. Regardless, I'm going to show you how to do it, and then you can test that with some more data after you download it from the official website. So I'm going to say val, let's call this rate code evolution to be taxi df dot group by. So I'm going to group by this rate code ID, but I'm also going to group by the day of the pickup. So I'm going to say column tpep underscore pickup underscore date time. So this is the column name for the date time of the pickup. Now this is a timestamp, so we will need just the day of the pickup. So I'm going to say to date of this column. To date is a function that we used earlier in the course from the functions package over here, which we imported earlier. So we're grouping by the to date of the date time day. So let me give this guy a name. So as pickup day. All right. So I'm grouping by the day of the pickup and also by the rate code ID. So column rate code ID. Now with a camel case and also with proper spelling. So rate code ID. Now, what do I do here? I'm going to aggregate to count everything. So count all the trips as total trips, okay, then I will order by this column, pickup day. So I will order by the day to track the progress of the rate code ID. So I will order by, so I'm going to put in here the column called pickup day that I created earlier. And then you can plot this data frame using some kind of plotting library, because you will get, for every pickup day, you will get all the rate code IDs, and then you can track the number of trips that you get for each rate code. All right, now let's get to the final question, number 8. Can we explore a ride-sharing opportunity by grouping close short trips? Now, this is a complicated question, but it's a question with a lot of potential. So here's what I'm going to do. I'm going to group all the taxi rides that are starting in the same pickup location in 5-minute time window buckets. So I'm going to group the taxi DF data frame by the pickup location ID and by their timestamp divided by 5 minutes. So that will be the absolute time window in which the taxi ride is happening. So I'm going to say the following. I'm going to make another data frame called group attempts DF, and I'm going to say taxi DF, and I'm going to select the following things. I'm going to select the Unix timestamp from the column that we called tpep underscore pickup underscore date time. The Unix timestamp is the number of seconds since January 1st, 1970 of the date time of the pickup of the taxi ride. So this is the absolute number of seconds of the taxi ride pickup. And then I'm going to divide this number of seconds by 5 minutes. So I'm going to divide it by 300. And then I'm going to cast that as integer. So first I will call the function called round, because this expression is a double. So I'm rounding the division of the timestamp by 300. And I'm going to cast this column as integer. So cast integer. And then I'm going to give this column a name as, let's call this 5-minute ID. So this is quite a mouthful. I hope this makes sense. So I'm taking the date time column, I'm converting that to the Unix timestamp, that is the absolute number of seconds since January 1st, 1970. Then I'm dividing it by 300 to obtain a 5-minute bucket ID. Now, because this expression is a double, I'm rounding that to the nearest integer, and I'm casting the result to integer. And then I'm giving the column name 5-minute ID. So I hope this makes sense. Now, besides this huge column, I'm also going to select the column pickup location ID and the total amount. So column total underscore amount. So I'm selecting these 3 big things. Now I'm going to put a where filter, and I'm only considering the trips that can theoretically be grouped. That is, the trips that have at most 2 passengers, because if you want to group 2 rides with less than 2 passengers, you can put them in the same car. So I'm going to say column passenger underscore count is less than 3. Then I'm going to group this data frame. So I'm going to say group by, and I'm going to group by the column 5-minute ID and location ID. So column called 5min ID and the column pickup location ID. And then I'm going to aggregate the following. I'm going to first count the number of trips as total trips. And I'm also going to sum the total amount. So just to estimate the value of all the trips that I'm grouping. So I'm going to say sum of column total amount as, let's give this column a name, total amount. So let's keep the same name. Now, if you're wondering whether the total amount column name is actually redundant here, it's not, because if you simply did sum of total amount, that would be the name of the resulting column. So I'm reducing that to simply say total amount. Now, I'm going to order by, and I'm going to order by the simultaneous total trips. So by this column total trips. Descending knows last. So I'm interested in the maximum amount of trips that can be grouped. And that's how we can get all the taxi trips that can theoretically be grouped by location ID and by their 5-minute bucket. So far we've selected this huge expression over here as their 5-minute bucket ID, the location ID, and the total amount. We are filtering only the taxi trips that have at most 2 passengers, and then we're grouping by the 5-minute bucket ID and by location ID, and we're counting the total number of trips, and we're summing up their total value. And we're ordering by the total amount of trips descending. Now, in order to make this data frame more human readable, we will actually multiply this 5-minute ID by 300 back so that we can understand the approximate date time. So I'm going to say with column, and I will add the column called approximate date time, and the expression for that is going to be column of 5-minute ID times 300, and the 5-minute bucket times 300 is actually a Unix time, so you need to convert from a Unix time. So I'm going to call the function from Unix time. All right. So this is the new approximate date time column that I've added to the data frame. Now, I'm also going to drop the 5-minute ID because I don't need it anymore. I only used it for grouping. So I'm going to drop 5-minute ID. And now I would like to also join the location ID with the taxi zones so that I can understand which zones we're referring to. I don't know all the location IDs by heart. So I'm going to say .join with taxi zones df under the condition that column pickup location ID should equal column location ID. And obviously I'm going to drop the residual columns from taxi zones df. So I'm going to drop the location ID and the service zone. And this is my big data frame. So let's recap once again because this is a big data frame. So from the original taxi data frame, we're selecting the date time, which we are converting to a Unix timestamp, the absolute number of seconds, which we're then dividing by 300 to compute their absolute bucket ID, 5-minute bucket ID. And we're rounding that to an integer and casting it as such, and we're naming that 5-minute ID. And from the original data frame, we're also selecting the pickup location ID and the total amount. And we're filtering the data frame only for the trips that have at most 2 passengers. And then we're grouping by the 5-minute ID column, which we computed earlier, and by pickup location ID. So we're grouping by the time bucket and by location ID because we're interested in grouping the taxi trips that are starting from the same location within a 5-minute time window. Obviously, you can run a smarter algorithm to better group the taxi rides by 5-minute windows, but this will be good enough. Now, we're aggregating to count the total amount of trips within a 5-minute window and within the same location ID, and we're also summing up their total value. We're ordering by the column total trips, so by the number of taxi trips. And then in order to make this data frame more human readable, we're calculating the approximate date time of the time window of the 5-minute ID bucket. And we're multiplying that by 300 again, so we're converting from Unix time to determine the start of the time window, of the time bucket. Then we're dropping it because we only used it for grouping earlier, and then we're joining with the taxi zones df to understand the actual location ID description. All right, so I hope that makes sense. Let's go ahead and show this. So I'm going to say group attempts df.show. So let's see what we got. Compilation should be fast. And then the grouping should take a few seconds. All right, come on, Spark. Do the work. All right, so we have a data frame here. And notice that by location ID, the zone is Upper East Side North, Upper East Side South. These are expected. These are the wealthiest zones of Manhattan, so we are expecting the most taxi trips to originate from these areas. But notice that within a 5-minute time window, we have 100 total trips starting in the same location ID. So this is a massive opportunity to try to do some grouping or ride sharing for taxis. So as a data scientist, when you see numbers like this, your spidey sense should go ding, 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 because this is a proposal worth pursuing further. So we see here in the data lots of close taxi rides within a very short time frame. So we can incentivize people to take a group ride at a discount, or disincentivize people to take an individual ride with an extra cost. So this will lower the costs in our taxi company. This could bring us more competitive with lower prices against technologies like Uber or Lyft. And also for the environment, this can lead to fewer emissions because we're using fewer cars for the rides. At the same time, because this is a project with some significant potential environmental improvement, we can investigate the possibility of a subsidy from the government or from the local authorities. So let's try to run a simple model to estimate just the potential economic impact over this dataset. And for that, let's assume we have some reasonable parameters. Let's assume we invented a technology that could attempt to group taxi rides by sending notifications to the user's, let's say, smartphones. So let's assume that this algorithm, this technology, could automatically detect 5% of all the taxi trips to be groupable at any time. We noticed earlier that we have hundreds of taxi trips. So let's get a conservative number of 5% of these taxi trips detected to be groupable. Let's also assume that 30% of people actually accept to be grouped, and the rest of 70% decline grouping and take individual rides. Now, let's assume we get a $5 discount if we take a grouped ride, and we incur a $2 extra to take an individual ride if we have some privacy or time constraints. If two rides are grouped, let's further assume that we're reducing the cost of the taxi maintenance and salaries and so on and so forth by 60% of one average ride. So these are some of the parameters that we are going to use in this model. Now, in order to further tweak the parameters, we can do some surveys on the population and gather some more accurate data. But so far, this is pretty reasonable as an assumption. All right, so let's bake these numbers into our code. So let me define some values. So I'm going to define the percent group attempt to be 0.05. So I said 5% of the total trips are detected to be groupable at any one time. Let's define another value called percent accept grouping to be 0.3. So that's 30% of the actual detections are accepted. Then we have the incentive to take a grouped ride. So let's say discount to be $5 and the extra cost to be $2. And finally, the average cost reduction. So I'm going to say val average cost reduction. And this is the average value of a ride. And I'm going to multiply that by 60%. So I'm going to say 0.6 times the average of the total amount of a ride. So I'm going to say taxi df dot select, and I'm going to run the average of the column called total amount. Then I'm going to convert that to a double. Now, in order to convert that to a double, I need the Spark implicits. So let me do that. So let me import Spark implicits up top. So import Spark implicits. So we're converting that to a double. Then I'm going to do take one. Now, if you do take one, you will get an array of doubles, and I will only be interested in the single value that I have from the array. So I will call that with the index 0. All right, so I'm selecting the average of the total amount from the data frame. I'm converting that to a double, so far I have a data set of doubles. Now, if I'm taking 1, then I will convert this data set into an array of doubles, which will have only a single value, and then I'm extracting the single value out of that array. So this is the average cost reduction as a double. All right. Now, let's put these numbers into a data frame. Let's say grouping estimated economic impact, DF, as the following. I'm going to start with group attempts DF because these are the taxi rides that I've detected earlier to be groupable. There's no point in trying to group the attempts that are more than 5 minutes apart and in different taxi zones. So from this group attempts DF, I'm going to add a column, so with column, and I'm going to add a column called grouped rides as the column simultaneous trips. So we have here the total trips, column total trips multiplied by the % group attempt. So this is the amount of taxi rides that the algorithm that we're thinking of developing, we think will notify to be grouped. Now, let's add another column. Let's say accepted group rides. And I'm actually going to compute the profit here. Let's say economic impact. Because we don't really know if this is actually the profit all for the taxi company, although it might as well be. So let's say accepted grouped rides economic impact to be the column called grouped rides that we just computed. Now we need to multiply that by the % accept grouping. So this is the number of accepted grouped rides, and then we need to multiply that with the profit of each. The profit for each grouped ride is going to be the average cost reduction that we as a taxi company are saving. So average cost reduction minus the discount that we're offering. So minus discount. So this is the economic impact or the profit of the accepted grouped rides. Now, let's add the economic impact of the rejected rides. So with column, I will name this rejected grouped rides economic impact. I think I might have chosen some pretty long column names, but I'll stick to that. Now, I will create this rejected grouped rides economic impact to be the column grouped rides, and then multiplied by the % of the rejections. So I'm going to multiply that by 1 minus % accept grouping. So if 30% of people are accepting the grouping, then it follows that 70% are rejecting the grouping. So this is the number that I'm after. Now I'm going to multiply that by the extra cost that these people are incurring for rejecting a grouped ride. So extra cost. Now let me add these two. So with column, let's call this total. So total impact to be the column of accepted grouped rides economic impact. Now I definitely have picked some really long names, plus the column with the other guy, the rejected grouped rides economic impact. All right, so we have a data frame. Let's go ahead and show this. So group estimate economic impact df dot show, and let's show 100 instances of it. Are we doing show anywhere else? I don't think so. So let's go ahead and run this. It'll take a bit of time to do all the grouping and all the computation. A couple of seconds. All right, so we have our data frame over here. So for pickup location ID, total trips, total amount, approximate date time, borough, zone, grouped rides, look at that. We have 5.75 grouped rides, accepted grouped rides economic impact, that's $7 per 5 minutes, and $8 for the rejected grouped rides economic impact. So we're making $15 every 5 minutes. This is pretty reasonable, given the fact that the total value of the taxi rides is almost $1,500. Making $15 is pretty significant, so 1% of the total value of the rides. This is pretty reasonable. Now let's try to sum up all these numbers, all the numbers from the column total impact, and let's compute the total value, the total economic impact, or the total potential profit of the company per this day of this data set. So I'm going to create the total impact, or total economic impact, or total profit df to be grouping estimate economic impact df dot select, and I'm going to sum up the column total impact, and let's give this guy a number. Let's call this total, and let's show this. So total profit df dot show. Let's rerun this, and let's see what numbers we got. It'll take a bit of time for Spark to actually perform these computations. All right. Okay, so we have $39,987. So we have almost $40,000 in savings, or an economic impact, per day, per this whole day of this data set. So think about it, folks. We have $40,000 a day. At 365 days a year, that's more than $12 million per year. Think about it. You're saving a company $12 million a year. For this entire data set, I wouldn't be surprised if we get upwards of $70, $80 million for the entire data set, because we have 7 years worth of data. So let's go ahead and run this computation over the entire data set. So let me go ahead and create a new application under source main Scala under part 7, where I'm going to only run this last computation. So under part 7, I'm going to create a new application. I'm going to name this taxi economic impact. Let's make it an object, make it extends app. Let's copy most of the stuff from taxi application. So I'm going to copy question number 8. All right. I will import the Spark functions. So I'm going to copy the Spark session over here. I'm also going to copy the big taxi df. All right. And I'm going to run this computation on the big taxi df, so not on the small taxi data. Then I'm going to import the functions. So I'm going to import org apache spark SQL functions. So everything should compile. Now I also need to load the taxi zones df. All right. So let me do that as well. Now, instead of taxi df, I'm doing big taxi df. Now, the reason why I'm doing all this stuff is that I want to separate this application so that we can launch it on the Amazon cluster. So I want to separate that into its own app. Now, we're doing some implicits here. So I'm going to import Spark implicits, and our code should compile. However, there is a warning that I have to give you. The schema of the big taxi data frame is slightly different than the schema of the small taxi data frame that I have here under source main resources. That's because Ravi Shekhar, the guy who cleaned the data, also included a bunch of other columns and renamed some columns like tpep pickup date time to be more human readable, like pickup date time. So it would be worth printing the schema of the big taxi df before we run this application. So I'm going to say big taxi df dot print schema, and I'm going to kill the shows over here so that the data frames are lazy. So let me run the taxi economic impact and just see the schema so that I know which columns to rename. All right, so we have an exception here because we're doing a bunch of selects from columns that are not there. So look at that. We have drop-off date time, drop-off longitude, so this is extra, drop-off taxi zone ID, and so on and so forth. So let's rename tpep pickup date time to be pickup date time. All right. Then we need to rename the location ID. So we have pickup taxi zone ID in this big data set. Passenger count, we have the same passenger count, if I remember correctly. Yes, we have the same passenger count. Pickup location ID, we need to rename that again to pickup taxi zone ID. Okay. The location ID is from the taxi zones data frame, so the location ID should not be renamed. So we have 5-minute ID, this is our column, total trips is our column, total amount, we have total amount over here as well. Total trips, 5-minute ID, service zone, we should be fine. Let me try to rerun the application. Even though the data frames are lazy, Spark will do the column checks. So, because we're doing an action over here, it's also performing some computations. And if it's performing some computations, then the data frame is fine. All right. So we're almost ready to show these data frames, but I will unfortunately have to give you a little piece of bad news. In the big data frame, the passenger count is null for the entire data frame. So I will have to remove the filter here because there is no entry where the column passenger count is less than 3, which will lead to some empty data frames. However, we could compute the percentage of the taxi routes that are groupable, that is, they have the passenger count less than 3, from the smaller data set where we actually have the data and where we have the passenger count. So in the taxi application, instead of me doing the shows here, which I'm going to save for the taxi economical impact application, I'm going to add another data frame right at the top here. And I'm going to name this data frame, let's say, passenger count df as taxi df dot select, and I'm going to count all the taxi trips where the passenger count is less than 3. So I'm going to count star, and then I'm going to filter first. So I'm going to say where column passenger underscore count is less than 3, select count star. And then I'm going to show this. So passenger count df.show. And I'm also, for comparison, I'm going to select count star from taxi df and do a comparison. So I'm going to say taxi df select count star dot show. So let me go ahead and run this application, and just to be extra safe, I'm going to comment out the other code so that Spark doesn't do some more computation. So this should take a couple of seconds, and we should be getting some approximate numbers. So we have 331,000 and 289,000 to have the passenger count less than 3. So almost the entire data set. So we have 289,000 out of 331,000. I'm actually going to take these numbers and paste them right into the other application. So taxi economic impact, I'm going to create another percentage, let's say percent groupable, as 289,000 times 1.0, so that we have a double, and then divided by 331,000. And this percent groupable, I'm actually going to multiply by the total trips that I compute in the early data frame. So when I determined how many taxi trips are groupable, originally I did the filter with a passenger count less than 3, but since I don't have that information in the big data frame, I'm going to approximate that by this percent groupable. So I'm going to multiply that with percent groupable. So I'm going to say count star times percent groupable as total trips. Now I'm going to move these values up top so that they're accessible. And this is how I'm going to estimate the group attempts. All right. So all that it's left for us to do is to do total economic impact df.show, and let's start the application. And Spark will start to crunch the numbers, and it will take a bit of time. Now the results will come, obviously, in the next video. All right, welcome back to the end of the big data project. Let's see what we got. So I started the job a minute ago when I also finished up the last video, and you see that Spark is still crunching the data over here. Depending on how powerful your computer is, the job might take between 10 minutes to an hour. Now, if you navigate to a Google Chrome or a browser and you hit localhost 4040, you will see here that you already have a job running here into your browser. So the Spark session that we started here in IntelliJ also started a web server, much like the Spark shell back in the earlier lectures of the course. So as long as this job is running, the Spark web server is still running here. So notice we have 549 tasks in the job ID 5. So Spark already finished up the first 5 job IDs, so jobs 0 to 4, while deconstructing the data frame and then finally aggregating the values here under the taxi economic impact.scala. So if you click over here, you'll see the DAG, and you'll see here the tasks progress. Now this job will probably take another good 5 minutes of computing time, so by the magic of video editing, here are the results. Okay, drums rolling, the job has finished. Let's scroll up and let's look at the data frame. This has a single row and the total says 1.39469 whatever E8, so times 10 to the 8th. So that means 139,469,875. And this is the number of dollars that the economic impact measures. So you're talking $139 million over the entire data set. So even with this very simple model, with a few numbers that we picked as reasonable amounts, we get the order of magnitude, which is the really important piece of information that we want to take away from this application, to be in the order of magnitude of $100 million worth of economic impact. This is big. So let's wrap up the Big Taxi project before we actually launch it on AWS. So we have 5 proposals worth pursuing for the Big Taxi company. We have the best proposal, which we have just computed, worth $100 million in economic impact as an order of magnitude, which even for a company this size, operating on probably hundreds of millions of dollars a year, it's still significant. And if you wanted to deliver this project as a data scientist with some additional visualizations and some more accurate data processing, this can be worth anywhere between $10,000 and $100,000. So this is the true power of a data scientist operating with the right tools, such as Spark, in the right way. And I hope this project gave you not just knowledge of Spark, which you surely already had from the rest of this course, but rather gave you an example of how to approach this big data project and how to help you deliver one of these projects on your own. All right, so this is the moment we've all been waiting for. Actually launching the Taxi Economic Impact application on a real-life cluster on Amazon. So here's how I'm going to go about it. First of all, I'm going to make some changes to the application, and then I'm going to package it as a jar under the Spark Essentials jar in much the same way as we did earlier when we submitted the application on our Dockerized cluster. So I'm going to modify the Taxi Economic Impact first to not extend app and rather have a main method with args as an array of string, and just wrap this whole code under the main method. Now, the main method will actually take 3 command line arguments. So let me mention them here. The first command line argument is the big data source. So here we will have Spark read load, and this will be the first argument to our application. So I'm going to say args 0. Now, the second argument is going to be the source of the taxi zones data frame. So I'm going to say here, taxi zones data source. And instead of the CSV here, I'm going to pass args1 as a CSV. And finally, I'm going to do a show at the end with a total economic impact data frame. And then I'm also going to write it at a third command line argument. So I'm going to say total economic impact df.write .mode save mode override. Let me import save mode. And then I'm also going to store that as a CSV. So I'm going to say option with header true. And then I'm going to store that as a CSV at args2. So this is the third command line argument. And the rest of the code is going to be the same, except I'm going to check for the command line argument's length. So the third command line argument is the output data destination. And at the beginning, before I execute any code, I'm going to check for the command line argument's length. So if args length is less than 3, or is not equal to 3 exactly, then I'm going to print something, and I'm going to print need one big data source, 2 taxi zones data source, and 3 output data destination. And I will do a system exit 1. Now, once we have this application, we need to rebuild our jar file. So I'm going to go to the build menu under IntelliJ, and I'm going to say build artifacts, and then I'm going to rebuild the Spark Essentials.jar. It'll take a few seconds for the compiler to catch up with all my modified code. And right now I have the Spark Essentials jar file written somewhere in this huge folder. So Spark Essentials.jar. This is very important. We're going to ship this to an Amazon S3 bucket, and then we're going to load it in an Amazon cluster. Now, from this point onward, you don't need to do what I'm doing, because this will start to cost real money, because we're going to involve a real life cluster owned by other people, so we are going to have to pay them. So here goes. I will go in a browser and I will go to aws.amazon.com, which is the home for all the Amazon Web Services. And I will go ahead and sign into the Amazon Web Services console. If you don't have an account, you obviously need to create an account, but I already have one, so I just clicked on that button and the browser already knew to log me in. Now, there are 1,000,001 AWS services, but the two that I want to show you are S3 and EMR. S3 stands for Simple Storage Service, which is a file system, a distributed file system owned by Amazon. On S3 is where I have what is called a bucket that I called Rock the JVM. And under this bucket, which is the equivalent of a hard drive if you want to abstract it that way, under this bucket, I have both the Spark Essentials.jar that I uploaded. You can simply drag and drop a file into this window and it will automatically upload it into a bucket. So I have both the Spark Essentials.jar and the data sources for all the data. So we have both the taxi zone CSV, and I also have the big ass data set in Parquet format, the 35 gigabytes one. If you want to create your S3 bucket, there are just a bunch of buttons that you need to push. For example, you can go to Amazon S3 and simply click on create bucket, and it will automatically create a bucket for you. Click on next, and then you'll have an empty bucket, which is where you can put in any file of any size that you want. So the UI is pretty straightforward, especially for the very simple use case that we have. Now, S3 is where we will store the data, and S3 is also where we will refer the data to when we actually submit the Spark application, which I'm going to show you shortly. Now, this is S3. The second service is EMR, which stands for Elastic Map Reduce. And this is a cluster that's already been set up with Spark and Hadoop and the infrastructure for running Spark. So if you click on EMR, all you need to do is go ahead and create a cluster. Once you create a cluster, you will get a small menu that will allow you to create a small cluster and configure that with some very simple libraries. So you can give this cluster a name, for example, the taxi application economic impact. You can also check this logging checkbox, which will store some log files that will allow you to debug the job as it's running so that you can diagnose if something goes wrong. I tested this application, so I already know it's running, so I'm going to check this off. Now, as for software configuration, you have Core Hadoop, HBase, Presto, and Spark. So this is a small Spark infrastructure with Hadoop 285 with Yarn. So this is one of the clusters that Spark can run on top of. So Yarn is the job scheduler, the generic job scheduler from Hadoop, and Spark will run on top of that. We don't really need to care about Hadoop and Yarn. We only need to care about Spark, which is running 2.4.4, which is the latest Spark version at the moment of this recording. Now, as for hardware configuration, you can select any instance type that you like. You see here that you have lots and lots and lots of options, which can have some various hardware configurations for different combinations of memory, storage, GPU, CPU, and so on and so forth. We're picking the general purpose here, and for example, an M4 X large is more than enough for what we need. Bear in mind that if you select a beefier computer, that is, if you're going downwards in every single sublist, that will cost more money because you're being charged by instance hour. So this cluster of ours will contain one master node and two core nodes, each node being one of these M4 X large machines. Okay. Now, for security and access, we need an EC2 key pair. If you don't have one, click on this Learn how to create an EC2 key pair link, and this will pop up a small dialog instructing you how to do that. The setup should be pretty quick, and as a result, you will get a small file called a PEM file. A PEM file stands from Privacy Enhanced Mail, and this will contain some security certificates for you to be able to log into your Spark containers, all right? So you will need to do that before creating the cluster so that you are actually able to log into your Amazon cluster. So I happen to have one. I have one key pair called Rock the JVM, so I'm going to use that. And once you have those, click on Create Cluster. And once you click on Create Cluster, Amazon will automatically start to provision 3 machines for you. It will say starting, and the machines here have the status here on the right hand side saying provisioning. In a couple of minutes, this should be cleared green. And bam, by magic, a few minutes have already passed. We've traveled in time, and we have a running cluster waiting for our commands. So all we have to do is connect to them via SSH. So click on this small SSH link, which should give you some instructions on how to connect to your cluster via SSH, depending on whether you're on Windows or Mac. I'm on a Mac, so I will copy this command. I have the rockthejvm.pem file on my computer, so I will copy that. I will go to a terminal window, and I will paste it over here. So I will connect to the Hadoop instance. I will type in yes, because I've never seen this machine before. And because I have the rockthejvm PEM file, I'm able to automatically authenticate without a username and a password to the Amazon cluster directly. Now, if you get into trouble connecting to your Amazon cluster, or if your SSH connection times out, go back to your console and click on this link on security groups for master. So this security group should have the SSH port 22 already open. So if you click on the security group for Elastic MapReduce master, which is going to be the security group for which all your master nodes are going to be spawned from, go to the inbound tab over here, and you should have an entry for SSH already open. I did not have one by default, so I needed to add one by clicking on the edit button and add the SSH port 22 from my IP and give it a description of your liking so that the SSH port is open in your Amazon cluster. All right, so this is quite a lot to do, but just make sure you follow these steps. All right. Now, once I am on the cluster, I will have to actually do the Spark submit, which we already have set up by the nature of this cluster. So if I type in which Spark submit, we notice that we already have the command embedded into the machine. So we don't need to go to the Spark submit wherever it's installed. It's already been linked from the setup of the cluster. Now, the first thing that I will have to do before actually running the job is to copy my Spark essentials.jar file from the S3 bucket to here. Fortunately, the Amazon cluster already has some Amazon related commands that will allow you to interact with an S3 bucket very easily. So I will type in AWS S3 CP. So AWS S3 is a set of commands that will allow you to interact with an S3 bucket. So I will do a CP, and the source is S3 // my rock the JVM bucket, which is under my name and with my permissions. So S3 rock the JVM, and I will do /spark-essentials.jar, and I will copy it here into this folder. So notice that the download was blazing fast, although the Spark Essentials jar probably has some 200 megabytes. So where am I? I am in home Hadoop. I'm logged in as the Hadoop user, and I have the Spark Essentials jar waiting for my Spark submit. So let me go ahead and do it. So spark-submit --class. And the class name is going to be part 7 big data.taxi economic impact. So part 7 big data.taxi economic impact. And then I'm going to add a -- supervise -- verbose. So we have more output than Spark will naturally give us, so that we see that the job is actually running. And then I'm going to pass just the Spark Essentials jar. And then I will need to pass in my 3 command line arguments. So the first command line argument is the location of the big taxi data frame. So that will be S3 // rock the JVM / New York City _taxi _ 2009-2016.parquet. The second command line argument is the location of the taxi zones. So it's S3 / rock the JVM / taxi _ zones.csv. The third command line argument is going to be the output data. So I'm going to store that in S3. So I'm going to say S3 / rock the JVM. Make sure I spell correctly my own S3 bucket. So rock the JVM / and I'm going to add a folder here. Let's call this economic impact. And that will be it. So let's hit enter and let's watch Spark do its thing. So we see here all the configurations and that Spark is actually starting up the job. Okay, so we have application report. This is started on Hadoop's Yarn job scheduler, but we don't really need to care that because Spark abstracts that away. So Spark will actually start to fetch the executors and will start actually executing the job, and it will start actually crunching the numbers. And good luck, Spark. I will see you in roughly 5 to 15 minutes. And shabam, we've traveled 15 minutes in time yet again, and our job has finished. All right, so Spark has crunched quite a bunch of numbers, and we should see the output here in the S3 file. So I'm going to hit refresh now, and I see here the folder economic impact, which is where the data frame for the economic impact is going to get stored. So if I click that, we see here a partition with the CSV. It has 27 bytes containing a very precious number. So if I download this and try to open it in whatever editor I want, and we see here the same number, 139,469,875 in this case. So we crunched 1.4 billion taxi rides and reduced them to this very precious number, which should probably be compelling to any kind of company that you would present such a project to. Now, one last thing that you need to do, so if you're following along, once you run your job on the Amazon cluster, make sure you do the termination of the cluster, because Amazon charges money for the instances that they provide to you regardless of whether you actually use the cluster or not. So click on the terminate so that you don't get charged any more real money. So congratulations on this amazing journey writing your first truly big data project. So think about it, we crunched 1.4 billion entries into a real life project that would hopefully be compelling and that will serve as an example for whatever big data projects you end up doing in your career. Congratulations! We've come a long way, and we've written a couple of thousand lines of code from scratch by now. I'm really proud of you. Just take a look at how far we've come, and you've done it all. So tell yourself you're awesome, and you can do anything. Until next time, I am Daniel, and I will say farewell, and thank you for watching.